Hello? 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 Can you hear me?
Hello, yes, we can hear you.
Thank you.
Could you
And
please share your screen? Have a test.
okay. Uh,
又是一样的问题。你这是在干嘛啦？你为什么会有
I'm sorry, I have to reopen the Zoom.
Take your time. We still have 12 minutes. 就是导单的画面，导单你这边显示的是用的好。
Okay.
Yes, we can see you.
Can you see it now? Okay, thank you.
Yes. Yes, looks
Okay.
good. Thank you.
Okay, thank you.
Welcome to non-interactive zero-knowledge session. We will have 3 talks in this session. And the first talk is unconditionally secure NIZK in the fine-grained setting by Yu Wang and Jiaxin Pan, and Yu is going to talk.
Okay. Thank you. Okay, so I'm starting the talk. Thanks for the introduction. Hello everyone, my name is Yu Wang. I'm from USDC. Our title is Unconditionally Secure NISC in the fine-grained setting. It's a joint work with Jiaxin Pan. Usually in the standard cryptography, we just require that the honest party can run in polynomial time and the scheme can be secure against polynomial time adversaries. By now, there have been many primitives proposed based on various assumptions. However, it's still unclear whether these assumptions hold. If, for example, we prove that some one-way function does not exist someday, then most primitives will not be secure anymore. So it's natural to ask whether we can propose schemes based on no assumption or just some mild complexity assumptions. However, it has turned out that this is quite difficult in the standard setting, so Marco initialized the study of fine-grained cryptography to approach this problem. In the fine-grained setting, we just require that the honest party runs in polynomial. The honest party uses less resources than the adversary, and the resources of the adversary can be prior bounded. Since the power of the adversary is limited, it's possible to propose schemes based on very mild assumptions or even no assumption in this setting. By now, there have been many fine-grained primitives proposed, and recently we proposed a NISC in the fine-grained setting, which runs in NC1 and secure against adversaries in NC1 under the assumption that NC1 is not equal to parity/poly. Although the underlying assumption of the previous fine-grained NISC is already very weak, it's still unclear whether we can construct unconditionally secure fine-grained NISC. And in this work, we solve this problem by proposing a fully fine-grained NISC for AC0 circuit satisfiability. In our construction, all the algorithms, including the CRS generator, the prover, the verifier, and the simulator run in AC0, and it has perfect soundness and composable zero knowledge against AC0. A dual mode has perfect zero knowledge and computational soundness against AC0 adversaries. It's under no assumption. Here by AC0, we mean the class of circuits with constant depth, polynomial size, and unbounded fine using AND or AND NOT gates. And we also note that a statement circuit we consider cannot go beyond AC0. Otherwise, even the honest prover in the AC0 cannot decide, even with the witness, whether the statement is true or not. But if we allow the prover to run in polynomial time, as in the previous fine-grained NISC proposed by Bo and others, our NISC can also support all the statements in NP. We can also extend our NISC to non-interactive ZAPs and also NISCs in the URS model. All of them are unconditionally secure in the AC0 fine-grained setting. As applications of our work, at first, our NISC can be used to provide unconditional security against adversaries with limited parallel running time. Also, it can be used in systems requiring online security, where the attacks are valid only if they succeed immediately. For example, our NISC with composable zero knowledge and perfect soundness can be used to protect the secrets only valuable in a short time. And its dual mode with computational soundness and perfect zero knowledge can protect the secrets perfectly and can guarantee security in the system, requiring the users to provide the proofs in a short time. If the users cannot provide the proofs in a short time, then we can just consider them as malicious ones and can just delete them. Next, I would like to briefly talk about the impact of our work. Before our work, it seemed that the assumptions implying PKE were necessary for NISC in the standard model, which means that NISC seemed to be in the land of cryptomania. But in the AC0 fine-grained setting, only the mini-crypt primitives such as one function are known to exist, while we achieve NISC. So our result may have provided evidence that NISC might be a mini-crypt primitive, and this may even hold in the standard model. and it would be interesting to prove it. Next, I will briefly talk about the definition of NISC. In the NISC, the prover wants to prove that some statement X is in some language L, which means that there exists some witness W such that X and W satisfy some relation. There are 5 algorithms. The first one is Jing, which outputs a binding CRS, and the second one is Tjing, which outputs a hiding CRS and a trapdoor. The prover on input the CRS X and W outputs a proof, and the simulator simulates the proof by making use of the trapdoor without knowing the witness. The verifier just checks whether the proof is valid. Completeness says that the honest proof must pass the verification, and we consider the perfect honest, which says that when the CRS is binding, then there exists no valid proof for any invalid statement. The composable zero knowledge says that a binding CRS and a hiding CRS are distinguishable, and when the CRS is hiding, the simulator can perfectly simulate the honest proofs. This is how we construct our NISC for AC0 circuit satisfiability. At first, we construct a simple NISC for linear languages and then compile it to an OR proof for multiple disjunction. Based on this OR proof, we achieve our target construction. To achieve our NISC for linear languages, we make use of 2 facts. The first one is that the inner product of 2 sparse vectors is computable in AC0. Here by sparse vector, we mean the vectors with constant Hamming weight. The second one is a well-known result, which says that the parity of a random vector is not computable in AC0. Next, we define a matrix E and a vector lowercase e. The matrix E is a constant matrix with all the row and column vectors being sparse, and the lowercase e has all the entries being 0 except for the last one. Then the second fact we talked about before implies that 2 distributions, D0 and D1, are indistinguishable against AC0 adversaries unconditionally. D0 is just the distribution of random vectors in the span of E, and D1 is the distribution of vectors in the form of ET plus the lowercase e. T is some random string. So D1 just output the vectors outside the span of E. And equivalently, D0 and D1 output the random vectors with the parity being 0 and 1 respectively. We can also see that both distributions are sampleable in AC0 since the row vectors in the matrix E are sparse. Next, I will talk about how we construct the NISC for linear languages. The prover wants to prove that for some matrix M with the column vectors being sparse, there exists some witness W such that the statement X is equal to MW. The CRS is just some binding CRS sampled in outside the span of E. The proof of our NISC consists of 2 matrices. The first one is C, which is equal to MRR, is just some random matrix. And the second one is D, which is equal to RW times A. And A is the transpose of the concatenation of E and R. The verifier just checks whether CX times A is equal to M times D. We can see that all the row vectors of M and all the column vectors of A are sparse, which means that all the multiplication involved can be performed in AC0. So both the prover and the verifier run in AC0. And we can see that when the CRSR is outside the span of E, then A is a full rank matrix, which means that for proof passing the verification, we have that CX is equal to MD times the inverse of A. So X must be in the span of M. Composable zero knowledge follows from that when we switch R, which is the CRS, to a random vector in the span of E, then there exists a simulator in AC0 that can perfectly simulate the prover. Specifically, the simulator generates the C by computing the multiplication of M and R minus X times the transpose of T, and D is equal to R times the transpose of E. Here notice that we are not computing the inner product of x and t, otherwise it will not be computable in AC0. Next, I will talk about how we compile this NISQ to an OR proof. For simplicity, I will first talk about how we achieve the OR proof for 1 out of 2 disjunction. In this construction, the prover wants to prove that for 2 matrices M0 and M1 and 2 statements X0 and X1, there exists some J which is 0 or 1 and some witness W such that Xj is equal to MJW. The CRS is the same as before. And to generate the proof, the prover first split the original CRS R into a binding CRS Rj and a hiding CRS R1 minus J, such that the sum of these 2 CRS is equal to the original one. And the trapdoor of the hiding CRS is T prime. Then the prover generates the proofs for Xj and X1 minus J with W and T prime respectively by making use of the prover and the simulator of the NISQ for the linear languages we talked about before. The sum is follows from that when the parity of R is 1, then either R0 and R1 has parity 1, which means that one of them must be binding. And the zero knowledge follows from that when the parity of R is 0, then both R0 and R1 will have parity 0, which means that both of them will be hiding. To convert this OR proof to an OR proof for 1 out of n disjunction, the natural idea is just to split the CRS in a more general way. At first, assuming the jth statement is true, at first we let the prover to split the original binding CRS R into n CRS such that the sum of them is equal to the original one, and only the jth CRS has the parity being 1. And the verifier will check whether the sum of all the CRS is equal to the original one. However, none of them can be performed in AC0. So our solution is to propose a double layer sampler to sample n CRS with the sum being R. And this sampler can be run in AC0. At the first layer, we just sample n trapdoors with the sum being the 0 vector. This can be easily done by sampling n bit strings with the parity being 0. Next, in the second layer, we just sample n hiding CRS, which are random vectors in the span of E. We will sample these vectors by making use of the trapdoors we talked about before. And now we can obtain n hiding CRS with the sum being 0. And next, we will add the jth CRS with the original CRS, which is R. And now we obtain n random CRS with the sum being R and the jth CRS being binding. And we can see that this sampler allows a prover to split the original CRS into n CRS, satisfying our requirement in AC0. And we also need an additional step for verification. Specifically, we use the NISQ for linear languages to prove that the sum of all the split CRS is equal to the original one. And by making use of this proof, the verifier can check the validity of the split CRS in AC0, since our NISQ for linear languages can be run in AC0. Here we need an AC0 extractor which can extract the witness from the n trapdoors we talked about before. And I will skip the details in this talk. Please see our paper for the details. Next, I will talk about how we convert this OR proof for multiple disjunction to the NISQ for AC0 circuit satisfiability. In our construction, the prover takes as input the witness and the statement circuit, which is in AC0. And it first extends the witness to contain the bits of all wires. If the witness is valid, then the output must be 1. And then the prover encodes each wire Wi as a random vector CTI with the parity being Wi. we can see that CTI is in the form that it is in the form of E times Ri plus the lowercase e times Wi, and Ri is just some random vector. And for each unbounded flying AND gate, we just use the OR proof for multiple disjunction to prove that either CTI minus E is in the span of E for all I, or CTJ and CTn plus n plus 1, which is the encoding for the output, are in the span of E for some j. And this is enough to ensure the consistency of the encoded wires. Here, there's a challenge that to get the witness, the prover has to decide which wire corresponds to 0 when the output is 0. And we can see that the prover cannot find such wire by searching each wire in order. Otherwise, the complexity will go beyond AC0. So we prove the existence of an AC0 algorithm that can output the index of the first 0 bit or 1 bit amongst n bits. And please see our paper for the details of the construction of this algorithm. And for the OR gates, we can prove the consistency in a similar way. And for the NOT gates, we just prove that the sum of E, the lowercase e, and the input and output encodings of the gate are in the span of E. So this is how we get the target construction of our NISQ. And we can also extend our NISQ to the non-interactive ZAPs, which just mean the NIW in the plane model. To achieve this converging, we just prove that our NISQs have the verifiable correlated key generation, and with this property, we can just use the GOS converging technique to transform our NISQ to non-interactive ZAPs. And we can also convert our NISQs to ones in the URS model. For doing this, we can just see that a random vector is a binding CRS and hiding a CRS with half-half probability, and by running our NISQ with the random CRS in parallel, we can just achieve our NISQ in the URS model. The zero knowledge of the resulting NISQ just follows from that of the underlying NISQ in the CRS model, and the statistical soundness just follows from that. For many random strings, at least one should be binding with overwhelming probability. So this is how we get the converging. And this is the conclusion of our work. We proposed fine-grained proof systems that are unconditionally secure against AC0 adversaries, and all of them can be run in AC0. The proof system includes NISQs for AC0 circuit satisfiability, non-interactive ZAPs, and NISQs in the URS model. Thank you. That's all.
Question?
Great talk. A quick question about how you sample in the OR composition construction. You said you sample T of these vectors that sum to 0. They have to be sparse, right? So how exactly do you
Yes.
sample those in AC0? N vectors that sum to 0?
Okay, let me see. So are you talking about these two distributions? Can you see the screen?
No, this
The
is in your
T0
OR
and
composition. This was in the OR composition construction. How you can't just split. You have to pick T1 through Tn such that they sum to 0.
Okay, I see. Actually, in the first step, we just sample n trapdoors, with the sum being a 0 vector, and this can be done in AC0 since we just make use of the D0 and D1, the D0 distribution we talked about before, and this is in AC0. And in the second layer, we just sample the NCRS by making use of the trapdoors we talked about before. And in this step, we just computing ET1 to ETN, and since E is sparse, so the multiplication can be performed in AC0. So this step can also be done in AC0. And we will also add the jth statement with R, which is the original CRS. And this step is also in AC0 since we just make an addition. So all of the steps can be done in AC0. And of course, we should also generate the proof of the needs for linear languages. And in this case, we have to extract a witness that can be used to prove that the sum of the split CRS is equal to the original one. And we can also do this by making use of the n-trapped loss we sampled in the first layer. So basically, all the multiplications just involves the involves the matrix E, which is sparse, and a random vector. So all of them can be computed in AC0.
Please ask a question. Sorry, so is there any question? From Zoom? No question, so let's thank the speaker again.
Thanks.
So the next talk is Triply Adaptive UC NIZK by Ran Canetti, Pratik Sakar, Xiaowan, and Pratik will give the talk.
Hi, can you hear me?
Yes.
Okay.
So you can start whenever you're ready.
Yeah, I'm ready. Okay. Hi, my name is Pratik, and today I'm going to talk about triply adaptive UC NIZK. So this is a joint work with Ran Canetti and Xia Wang. So I will first briefly introduce NIZK. So in a non-interactive zero knowledge, there's a prover P who has inputs NP statement X and the witness W, and the verifier has the same NP statement X, and they also have access to a setup which is a CRS, and then the prover computes a proof phi, attesting the fact that X is in the language L and W is a valid witness. So correctness says that if X is in the language and W is valid, then verifier output 1. Soundness says that if X is not in the language, then the verified output 0 with high probability. And then we have non-adaptive zero knowledge, which is as follows. So here the simulator first samples a CRS and the trapdoor, and the verifier obtains this CRS. The verifier has the NP statement, and the simulator also has an NP statement, and the simulator comes up with a simulated proof, and it sends the simulated proof to the verifier. And non-adaptive zero knowledge says that this simulated proof should be indistinguishable from a real proof. And then this is the non-interactive zero knowledge that we know. It satisfies these properties. So we introduce the notion of triply adaptive NIZK, which adds 3 additional properties on top of the previous properties. Mainly, we require adaptive soundness, adaptive zero knowledge, and adaptive security. So let me define these properties, and then I'm gonna talk why they are interesting. So adaptive soundness, there's a challenger who samples the CRS and provides it to the prover, and the corrupt prover now samples an NP statement and the proof to the challenger. And adaptive soundness says that if X is not in the language, then the challenger should output 0 with high probability, where the challenger runs the verified algorithm on the NP statement chosen by the prover and the proof. And note that adaptive soundness is stronger than like regular soundness. In fact, the Groth Ostrovsky Sahai or the GOS paper is sound but not adaptively sound. Then we have like adaptive zero knowledge, where the simulator samples the CRS and trapdoor, and it sends the CRS to the corrupt verifier. Now the verifier comes up with a samples X and W in the language after obtaining the CRS, and it sends the statement X to the simulator. So the statement X is adaptively chosen based on the CRS distribution. Now the simulator again computes a simulated proof and sends it to the corrupt verifier. And adaptive zero knowledge says that this simulated proof should be indistinguishable from a real proof, even though the statement is adaptively chosen based on the CRS. So this is adaptive zero knowledge. And finally, we need adaptive security against adaptive corruption. So here, suppose initially the prover is honest, and the simulator again samples the CRS and trapdoor. Now the verifier obtains the CRS and again samples the NP statement X and W in the language and sends the statement to the simulator. Now the simulator comes up with a simulated proof similar to the zero knowledge game and sends the simulated proof to the verifier. But now, suppose the prover gets adaptively corrupted after the protocol execution. In such a situation, the simulator has to come up with a randomness which is consistent with the witness W and the simulated proof. So security against adaptive corruption says that this simulated proof should be consistent with the witness, like the honest witness, and some randomness provided by the simulator. So if you have this indistinguishability, then you have security against adaptive corruption. So a triply adaptive NISIC is a type of NISIC which satisfies these three properties: adaptive soundness, adaptive zero knowledge, and adaptive security against corruption. That is, soundness and zero knowledge should hold even when the statements are chosen by the adversary based on the CRS distribution, and adaptive security is security against adaptive corruption of provers. So why is this interesting? Because this notion of triple adaptivity provides realistic security guarantees. Here the prover can basically use the same CRS to prove adaptively chosen statements, and we need security against adaptive corruption because this is very useful for real life MPC protocols where you are going to plug in your NISIC protocol inside a bigger MPC protocol. And finally, we also extend our NISIC to obtain UC security, and we also extend it to the reusable CRS model so that you can use the same CRS across multiple sessions between different parties. So this part is done using standard techniques from the literature. So let me now briefly describe the state of the art and how they compare with our main results. So the first work on adaptively secure NISIC was initiated by Groth Ashrafi Sahai, the GOS paper. So they constructed from pairings. They obtained adaptive security and adaptive zero knowledge, but they failed to get adaptive soundness. In fact, they obtained a weaker notion of soundness called adaptive culpable soundness because the real and ideal world CRS is just computationally indistinguishable because they are in the dual mode CRS setting. And then there was this work by Katsumata who extended the GOS work for compact NISIC. They also achieved similar notions of security in terms of triple adaptivity, and they're also based on pairing. And then there was a work by Abe and Fer. So they constructed the first triply adaptive NISIC, and their protocol relied on knowledge assumptions. So our task is to obtain triple adaptivity from standard notions where we don't need knowledge assumptions. Then there's a recent line of work which is based on correlation intractable hash functions. So this has been started by Kennedy et al., Piker et al., and Brzezinski et al. So they obtain adaptive soundness and adaptive zero knowledge, and they can instantiate their NISIC from LWE or DDH plus LPN. However, they fail to achieve adaptive security corruption. So our work is the first one which obtains triple adaptive security, and we obtain it from LWE and DDH plus LPN assumption. And we are also in the CI-based domain. So let's see some of the challenges and ideas. So our protocol is in the correlation intractable hash function based protocol domain. So the CI-based protocols actually require the interactive protocol to be statistically sound so that you can apply the CI argument. However, this contradicts adaptive security, as in security against adaptive corruption, since a statistically sound protocol cannot be equivocated upon adaptive corruption. Also, previous adaptively secure protocols like GOS switch the CRS mode to perform equivocation. As a result, they only achieve non-adaptive soundness. So you cannot achieve adaptive soundness if you switch the mode of the CRS. So we overcome these problems. So by showing that you can apply Fiat-Chemie for interactive arguments instead of an interactive proof system. So we do this by relying on CI in the hybrid. And our underlying proof system is an argument. As a result, it's computationally binding and hence equivocal. And this allows us to get adaptive security corruption. And finally, we perform our soundness argument without switching the mode of the CRS. As a result, we obtain full adaptive soundness. And now let me formally define our contributions. So we first define a new non-interactive UC commitment functionality, which we denoted as FNICOM. So the current UC commitment non-interactive UC commitment functionalities require interaction between the parties, even for like local commitment generation and verification, and that is very incompatible with MPC protocols. So we overcome that by introducing this non-interactive user commitment functionality. And here the parties can access the FNICOM locally for commitment verification, commitment generation and commitment verification. And our functionality also outputs the commitment string during the commit phase. So this models a non-interactive commitment mode, and also it's very friendly to MPC protocols. And then we introduce the notion of triply adaptive Sigma protocol in the FNICOM model. And then we show how to compile such Sigma protocols to obtain triply adaptive NISIC by using correlation intractable hash functions. And inside this compilation, we are actually applying correlation intractability for NISIC arguments. And finally, we instantiate our compiler by showing that most Sigma protocols are triply adaptive in the FNICOM model. And finally, we implement the FNICOM with commitment stream, with a kinetic fissioning commitment stream. And we can implement our like these two instantiations from LWE or DDH plus LPN. And we can extend our protocol to obtain UC security using standard tricks from the literature. Now let me briefly define this UC commitment functionality. So here the UC non-interactive commitment functionality is first initialized by the ideal world adversary with a simulation algorithm F. This algorithm is hard-coded inside the commitment functionality, and that helps us to generate commitment strings and verify. So now when a committer wants to commit to a message M, it invokes a commitment functionality with the message M, and it receives a commitment string C. And now the verifier obtains the string C from somewhere, maybe from an MPC protocol or directly from the prover, which we don't know. And now to verify, the verifier just needs to invoke the commitment functionality with the string C, and it obtains the output as 0 or 1, indicating verification has failed or verification has succeeded, and the verifier outputs the same bit. And we show that the kinetic fissioning commitment suffices to instantiate this commitment functionality. And if there exists an equivocal commitment scheme and a CCA2 secure public key encryption scheme with oblivious ciphertext sampling, then there exists a commitment scheme implementing this functionality. And we can build these from LWE or DDH. Now let me define the notion of triply adaptive Sigma protocol in the FNICOM model. But before that, let me briefly talk about what is a Sigma protocol. So in a Sigma protocol, it's a public coin 3-round protocol where the prover computes a first message A, which mainly consists of commitments. And now the verifier samples a random challenge and sends it to the prover, and the prover computes the response and sends it to the verifier. And now it should satisfy correctness, and it should satisfy some property called special soundness. That is, if a correct prover outputs two accepting proofs, AEZ and AE prime Z prime, that is, for the same first message A, if the prover has computed two valid responses for two different challenges, then you can extract a valid witness from the transcript, from the two accepting proofs. So this is special soundness. And then you require honest verifier zero knowledge, which says that there exists a simulator which, on obtaining a random challenge, can come up with a honest verifier zero knowledge proof, that is a simulated AEZ, which looks indistinguishable from a real proof. So this is the honest verifier zero knowledge. Now let me define the adaptively secure Sigma protocol in the FNICOM model. Here we assume that the prover and the verifier algorithm have access to the FNICOM functionality to compute this A and Z messages. So under the hood, it's like the prover can use the FNICOM to perform the commitments in A, and it can decommit it can compute the decommitments to Z and send it to the verifier, and the verifier can verify Z using the F9 com. And now it should satisfy correctness and special soundness, same as the Sigma protocol. In addition, we also need the honest verifier zero knowledge. Here again, we assume that there exists a simulator algorithm denoted as sim1, which has access to the simulation algorithm of the commitment string, and it can compute as honest verifier zero knowledge proof. And we also require adaptive corruption security. That is, suppose the prover gets corrupted after the protocol execution, then there exists a simulator algorithm, sim2, which upon obtaining the witness and the randomness of the first simulator can come up with a randomness which is consistent with the simulated proof and the witness. So to summarize, this is the type of security that we need, adaptive secure HVDK. And this is the adaptively secure Sigma protocol in the F9com model. Now, the next step is to compile it to an adaptively secure NISIC. So we are going to do this by using the correlation intractable hash functions. So before that, let me show the FHME transform. So suppose you have a Sigma protocol. To make it a NISIC, you use a hash function H, where the prover computes the first message A, and then it computes the challenge E by applying the hash function H on the message A. And you can sometimes you can also compute parameterize this with the statement X, but here we don't need that. And then you send compute the response Z and send A and Z as the proof to the verifier. Now the verifier can decompute the challenge and then perform the Sigma verification. And now this hash function can be instantiated using a correlation intractable hash function. So what is a correlation intractable hash function? So a hash family H is called correlation intractable for a sparse relation R. If given a hash function H from the hash family, it is infeasible to find X such that X comma H of X is in the relation. That is for all probabilistic polynomial time adversaries A. It's infeasible to compute X such that X comma H of X is in the relation for a random hash function from the hash family. And for a function F, we denote the relation R of F as X comma F of X. So now we can replace the previous hash function with a CI hash for relation R pi, where R pi consists of A comma E such that there exists a Z where verifier accepts X, E, and Z. So this is the correlation intractable hash function. And these are like standard, this is like very standard from the CI based literature. And this NISIC again has to satisfy correctness and soundness. But here in the zero knowledge setting, we assume that the simulator samples the hash function in the ideal world. Now that was prelims for FHME. Now we are going to show our triply adaptively secure NISIC protocol. So our NISIC protocol is as follows. So we have the prover X comma W, and it will compute the first message alpha and also the response gamma. So let's see how it computes this alpha. So first it computes two transcripts, A C0 and Z0 and A C1 and Z1 for the same first message for two different prover chosen challenges, C0 not equal to C1. So it computes the two different transcripts for two different challenges for the same first message A, and then it commits to the challenges using the F9com, and it commits to the responses Z0 and Z1 using the F9com. Then it considers the first message alpha as A and the three commitments, and then it constructs the challenge by invoking the hash function on alpha. So the hash function is a CI hash for the relation RF, where f is the function where f of alpha is equal to 0 if and only if the verified algorithm on A, C0 and Z0 is equal to 1, where these C0 and Z0 are extracted from this alpha, that is from capital C and Z0, using the simulator algorithm of the commitment scheme. So as you can see, this S algorithm is inside the CI hash. And now you construct the challenge, and finally the prover can compute the response as by decommitting to the challenges C0 and C1, and also to the response ZE corresponding to the bit E, and the decommitment to delta E. Now it sends, now the prover is going to send this response alpha, the first message alpha and the response gamma. And now the verifier is going to compute the challenge E by invoking the hash function. So this is going to be actually H of S, this is a typo. So this is, the verifier is going to compute the challenge by invoking the same hash function on alpha. And now it's going to verify the decommitments to the two challenges and ZE in gamma. And it also has to verify that the two challenges are different. This is because we allow the prover to come up with the two challenges. So if the two challenges are same, then the prover can always consider the two challenges to be the same batch challenge. So as a result, we need two different challenges, and the verifier checks that over here. And then the verifier just runs the Sigma protocol verification on A, C, E, and ZE. And as you can, and so this is our NISIC compiler from a triply adaptive Sigma protocol. From a adaptively secure Sigma protocol to an adaptively secure NISIC. And we can also argue that if the Sigma protocol is triply adaptive, then the NISIC is triply adaptive. And the adaptive security and adaptive zero knowledge of the NISIC follows from adaptive security of the Sigma protocol in the FNICOM model. And soundness of the protocol relies on special soundness of Sigma protocol in FNICOM model and the correlation interactability for the RF relation. Also, the soundness of this protocol is half. And so regarding the CI, we argue CI inside the hybrid. So we first show that in the FNICOM model, these commitments are statistically binding, and then in the next hybrid, by relying on special soundness, we argue that the Sigma protocol transcript is statistically binding, and then in the final hybrid, we rely on the statistical CI to argue soundness. And the CI hash in our protocol is statistically, is defined in the statistical mode in real world. So now let me talk about the instantiations. So we show that most Sigma protocols like Schnorr type protocols or the protocols in the Maurer framework are adaptively secure in the FNICOM model. The Gabel circuit based protocol of Hazai et al. Is also adaptively secure, and it avoids expensive CARP reductions. Even the protocols for graph Hamiltonicity are adaptively secure. And all of these can be implemented from LWE or DDH. And finally, we implement the kinetic fish link commitment and the equivocal commitments. Kinetic fish link commitment based on equivocal commitment and CC2 secure encryption scheme. And these can be instantiations from LWE or DDH. And note that for adaptive soundness, we need the CRS distribution of real and ideal world to be identical or statistically close for the commitment scheme. So to finally summarize our result, we proposed a new commitment functionality, which is more protocol friendly, and it has use cases beyond just NISIC. It can be useful for generic MPC. Then we proposed the definition and provide a generic compiler for adaptive, for using NISIC with triple adaptivity. Then we instantiated the FNICOM from CF01, and we instantiated our NISIC compiler based on LWE or DDH plus LPN by instantiating the underlying CI hash. So if you can obtain more instantiations of CI hash, then you can obtain more instantiations of our NISIC compiler. For example, you can also instantiate our NISIC from sub-exponential DDH by relying on the state-of-the-art CI hash function from sub-exponential DDH. So that's all. Thank you.
Jen?
Thanks for the great talk. And you said that the adaptive zero knowledge mainly came from the using ESC, but it looks that in the paper you also state that the CI hash with programmability. So I wonder where this programmability of CI hash is needed.
Okay, so we need the programmability of the CI hash in the hybrid to argue we don't need it for simulation, we need it for the reduction in the zero knowledge setting. So that's fine.
And okay, and as far as I remember, this programmability of CI hash is kind of one time. So, but it looks that you are reusing the CRS.
Right.
How is it possible to continue using the same CRS for many different theorems?
Right. So you can. So there are like a bunch of different transformations. So first we go from here to a short CRS model where we rely on the GOS result, and then we go to the result like we make it UC compatible by relying on the special commitment called simulation sound trapdoor commitment. So we rely on that to move to that setting, right? And the CI hash is programmed only for the reduction. We don't need it for simulation. So it's fine in that way. Does that make sense? So to go from like single session to multi-session, you can use some simulation sound extractable commitment schemes, which is there in the GOS paper, and also some signatures like one-time signatures. So that's like a very standard technique to uplift to UC security. So that is there in the GOS paper, and also the paper by Ran Cohen and Abhishelat and Daniel Wicks. Yeah.
So it's time to move to the next talk. So let's thank the speaker again.
Thank you. Yeah.
Testing. Can you hear me?
So the next talk is efficient NIZK from LWE via polynomial reconstruction and MPC in the head by Paul Lowe, Reddy Gosar, Amit Sahai, and Paul is going to talk.
All right. Hi, I'm Paul, and this will be efficient NIZX from LWE via polynomial reconstruction and MPC in the head. And this is joint work with Reddy Ghoshal and Amit Sahai. So our starting point is that prior to our work, all known NIZK arguments for NP from the hardness of learning with errors considered instantiating the Fiat-Shamir paradigm based on a parallel repetition of a public coin, honest verifier, zero knowledge, interactive proof. So and this is largely due to two works, CCH plus 19 and PS 19. So if you start with some NP language L and consider some statement X in the language, the way you would get a NIZK for L is first you'd apply the scarp reduction on your statement X to some NP complete language, such as graph Hamiltonicity. And the work of CCH plus 19 and PS 19 show us how to get a NIZK argument in the common random string model based off of some underlying protocol for Hamiltonicity, such as FLS 90. And the work of HLR21 shows how to extend this to any commit in open protocol, such as the 3-coloring protocol for GMW86. And in all these underlying protocols, you generally have a large proof size due to parallel repetition, which is performed to reduce the soundness error down to negligible. And in general, this carp reduction is computationally expensive, so you also have this overhead as well. And in our work, we give an efficient base NIZK construction for NP from LWE without parallel repetition and without carp reductions. And our tool of choice is MPC in the head, which was done by ICOS 07. Let me know if there's like some fluctuation in the volume. Okay, and in particular, this allows us to translate work done on efficiently, perfectly robust MPC protocols, which exist from several works, to efficient NISICs from LWE. So you can think of our work as initiating the study of efficient NISICs from the hardness of learning with errors. And our main informal theorem is assuming the hardness of LWE. There exists NISICs with computational soundness for all of NP, whose proof size is O of C plus Q times depth of C plus poly K field elements in some finite field F, where K is a security parameter, Q is quasi-linear in the security parameter, the size of the field is as large as 2 times Q, and C is an arithmetic circuit for the NP verification function for some NP language L. And here what we mean by base NISIC construction is that the work of GGI plus 15 show how to use fully homomorphic encryption to bootstrap an underlying NISIC to a NISIC whose proof size is effectively linear in the witness size. So you can think of our main theorem as providing a NISIC, a more efficient underlying NISIC from the hardness of learning with errors. As an overview of our technique, we're going to follow HLR21's coding theoretic approach to instantiating the Fiat-Shamir transform. And in particular, their work shows how to use list recoverable error correcting codes to address the case of exponentially many bad challenges, where the bad challenges have some product relation structure. And in this approach, the block size of this list recoverable error correcting code determines the efficiency of the proof. And here what we mean by efficiency, of course, is the proof size. And in particular, the list recoverable code they construct uses a Parvaresh-Vardy code concatenated with a single random code. And they achieve a block size of big O of k to the 1 plus epsilon for any small constant, positive constant epsilon. And you can ask, does the work of HLR21 generically apply to the setting of MPC in the head? And indeed it does, using the very specific properties of this Parvaresh-Vardy code. But we observe that this notion of general list recoverability doesn't take advantage of some structure that's actually present in the MPC in the head setting. And we can actually do much better. So we show that this yields less efficient proofs. And in our work, we observe that a modification of the original ICOS 07 protocol for MPC in the head allows us to use a strictly weaker notion of list recoverability, namely something we call recurrent list recoverability, which we'll define. And this allows us to use qualitatively simpler codes, namely Reed-Solomon codes concatenated with multiple random codes, and allows us to use aggregate size analysis and appeal to directly appeal to the polynomial reconstruction algorithm to achieve an improved block size of O tilde of k, so quasi-linear k. All right, so let's do a review of MPC in the head from ICOS 07. You have a prover and a verifier. And the prover, you want to build a ZK protocol or a HVZK protocol. And the prover in her head imagines carrying out an MPC protocol for some function f sub l, which is really the MP verification function for some MP language L, where the input here is the statement x, and a witness w, which I express here as Q secret shares with secret shares w sub I. And you can imagine Q parties who each get one share of the witness and the statement. And we say the view of this party is its inputs, its randomness, and its incoming messages, though without loss of generality, you can also think about including the messages it sends. And the prover will, in the first round, send a commitment to all these views. And note that these views also contain like randomness and inputs. And the verifier will then specify a random pair of parties, Pi, Pj. The prover will open to view I, view j. And the verifier will then just check the consistency of these views in the sense that the incoming messages and outgoing messages between these two views should be consistent. And this is a black box use of the MPC protocol. So let's unblack box this. So if we take a look at the view of, let's say, P1, who has input X, W1, and some randomness R, perhaps in the first round, P1 sent message 1 to P2 and received message 2 from P3. For us to compute the next round's messages, namely the messages that P1 will send out, there's a deterministic next message function next, which takes in the identity of the party, 1 in this case, its inputs, X and W1, its randomness R, and all its previously received messages, because you can always just recompute all the sent messages from the received messages. And it computes all the next round messages that this party would send out. So here in round 3, the next function would say that P1 sends M3 to P2 and M4 to P3. And this allows us, this non-black boxing of the MPC protocol allows us to define a modification of the ICOS protocol, which will be important for how we instantiate Fiat Shamir later on. In particular, what we're going to do is we're going to have the prover commit once to a transcript of the MPC protocol, including all the inputs and randomness. And now the verifier, instead of specifying a pair of parties, will just specify a single party P sub I. And the prover will open all the incident messages, the randomness, and the inputs for P sub I. And the verifier will now use this non-black box usage of the MPC protocol in that it's going to use the next function itself to check the consistency of these messages. And to boost soundness, you can specify that the verifier instead specifies up to XC many random parties in some set S. And this will boost the soundness, and you can specify as much up to the robustness parameter of the MPC protocol. And of course, MPC in the head directly computes the MP verification circuit, so we avoid any CARP reductions. Here it's not a parallel repetition. You only commit once to this transcript. And now each party's view is now independently verifiable, and this allows us to define a very clean bad challenge set structure, which I'll define in just a bit. So now here's how we're gonna follow HLR21's coding theoretic instantiation of Fiat Shamir. So recall that how we're gonna recall this works. You're gonna start with an interactive proof for some MP language L, which satisfies completeness, statistical soundness, honest verifier zero knowledge in a public coin property. And here you have the prover sending T rounds of messages, alpha 1 through alpha T, the verifier sending T rounds of challenges, beta 1 through beta T, and then there's openings gamma 1 through gamma T. And the Fiat Shamir paradigm shows us how to compress this into a non-interactive protocol via some hash function H. And we would like that this usage of the hash function H preserves soundness to some degree. Namely, we can ask that it preserves computational soundness. And this happens if H is sampled from some correlation tractable hash family for an appropriate relation R. And what relation do we consider? We consider the following naive relation. For any statement not in the language, we want to consider all pairs of first round and second round messages for which there does not exist a opening that would convince the verifier to wrongly accept the membership of the statement. And these beta 1 through beta T's are what we call bad challenges. Namely that these are challenges that would allow the prover to send a third round message that would fool the verifier into accepting the membership of the statement, which is not actually in the language. And the work of PS19 closes the case of this for using the hardness of LWE for the case of functions, namely circuits. And in particular, what I mean by that is if the relation is a function, meaning namely for every alpha 1 through alpha T, there's at most one bad challenge, beta 1 through beta T, then the work of PS19 addresses this case where we can instantiate a correlation tractable hash family for this relation from the hardness of LWE. And by guessing reduction, it also addresses the case of polynomially many bad challenges, where for every alpha 1 through alpha T first round message, there's only polynomially many beta 1 through beta T. And this is just by guessing. You incur polynomial loss by just guessing which of the tuples beta 1 through beta T is the correct one in some sense. But the moment you go to exponentially many bad challenges, you run into a problem because the guessing reduction will now fail. you'll incur an exponential loss. And the work of HLR21 says that for parallel repetition protocols, you have a nice product structure. So let's use this combinatorial structure to our advantage. So here's an alternate depiction of the exponentially bad challenge set. You just break it up into its T components, and each of these sets, so S1 is a set of all the beta 1s, like the projections, basically. And these are all polynomial size sets. And what you would, applying the principle of wishful thinking, you would like that these T polynomial size sets define another polynomial size set, this pink shaded set, for which we could have another relation for which we could instantiate the previous slide's CI hash function for. So this is exactly list recovery, which is observed by HLR21, so this is kind of miraculous. And what we can do, therefore, is use the list recoverable code and consider the following relation alpha 1 through alpha t and some r, and consider the relation where we just specify that the ith component of the encoding of r sits in the set Si. So this is a de-randomization this is a de-randomized relation, a relation for the de-randomized parallel repetition protocol. Okay. And in particular, what list recoverable code should we use? HLR21 says we can use Parvesh-Vardy code concatenated with a single random code. And let me tell you how this code concatenation works. You start with an algebraic code from some message space M to Z big Q to the T. And for when you send a message through, for every one of these T components, you're going to apply a random code on it. And this will give you, for each of these components, M Z little Q elements to get this, and therefore you get this code that goes from your message space M to Z little Q to the N, where N is M times T. And the list recovery just says that go the other way. You specify your sets S11 through S1M, apply list recovery to get some set S1, then apply this for all your T many random code recoveries, and then finally apply the list recovery for the algebraic code. And this gives you the set of all messages for which the code word sits in the the ijth component sits in the corresponding set. And HLR21 then showed this is a CI hash function for the desired relation. First, you have the PS19 CI hash for the encoding relation that we showed on the previous slide. Then you apply the list recoverable code. And just observe here that the block length of this list recoverable code affects the proof size. So here you start with the alpha 1 through alpha t's. After applying this new CI hash function, you get your beta 1 through beta t. And using a Parvesh-Vardy and single random code, you get a block size of size O to the k1 plus epsilon for epsilon greater than 0. And in general list recovery, you have to be worried on whether or not every one of these sets, S1 through ST, might be large. So you actually have to consider SI where SI may differ. And you may ask, is general list recoverability necessary for the setting of MPC in the head? And we actually observed that it's not necessary. Why is this the case? Well, in our modification of the ICOS protocol, we actually have a single bad challenge set, which is determined by this first round message commitment of tau, the commitment to the transcript, where scomp tau is just the set of all indices I for which UI is consistent, meaning that the prover could convince the verifier to accept incorrectly. So in the MPC, in the head protocol, we just have product sets S cross S cross S cross S, and this critically uses the idea that we have independent verifiability for each of these parties specified by the verifier. And this is a much simpler structure, and we'll show how to exploit this simpler structure. Right, so one may ask, does a simpler batch challenge structure allow the usage of a de-randomization technique both simpler and more efficient than general list recoverability? And the answer is yes. So here's a term we call recurrent list recoverability, a strictly weaker notion of general list recoverability, where instead of having arbitrary sets S11 through STM, you just have the same set reoccurring over and over again. And let's try to instantiate recurrent list recoverability with the simplest algebraic code we can think of. Let's just use the Reed-Solomon code. And we actually run into an issue for general list recoverability in the sense, or instantiating recurrent list recoverability in viewing it from the lens of general list recoverability, in the sense that list recoverability for a single code may result in an output set S tilde that's too large for the Reed-Solomon list recoverability. And for fixed random code, this happens with non-negligible probability over the prover's choice of S. It's not the verifier's choice, that's a typo. And in particular, to remedy this, we're going to make the following observation. The Reed-Solomon list decoding algorithm actually boils down to just polynomial reconstruction, which is a really simple algorithm given by Sudan 97 and Guruswamy Sudan 98. And polynomial reconstruction only relies on the aggregate list size, so the sum of all these S tildes. And we observe here that in the worst case, these S tildes could be as large as S times T, because a single set S tilde could be at least the size of, could be at least the size of S, because S could correspond to separate code words. Right, it could just correspond to separate code words. So when you do list recovery, you'll get as many messages as the number of code words there are. And our solution is therefore to use multiple random codes. If you use multiple random codes, then while some output sets S tilde 1 might be large, others may be small. So you might have S tilde T be very small. And we show that in this regime, the sum of the S tilde i's is actually about, we get the cost of T many output lists for the cost of effectively 1. We get the sum of the S tilde i's is less than O tilde of just S. And this allows us to show that polynomial reconstruction succeeds for every choice of the set S with all but negligible probability. So in summary, we modify the MPC in the head protocol so that it has a very nice bad challenge set structure, amenable to a strictly weaker notion of recurrent list recoverability. And we instantiate this recurrent list recoverable code using a Reed-Solomon code concatenated with multiple random codes. And finally, we show how to use aggregate size analysis to obtain something that's amenable to the polynomial reconstruction algorithm and achieves quasi-linear block length. And the final picture is effectively you take your PS19 hash, concatenated with a recurrent list recoverable code, which is actually Reed-Solomon plus multiple random codes. And finally, you get a reduced block length of just O tilde of K. And that's it. Thank you.
Any question? So I have one question.
Yeah.
So I think you give efficient instantiation for Fiat Shamir for MPC in the head, but if we don't care about the efficiency, is it easy to give a Fiat Shamir for MPC in the head by using the existing work of HLR?
Yes. So if you don't care about efficiency, you can directly use HLR21. The MPC in the head paradigm falls under the commit and open protocol.
I see. Thank you.
Oh, yeah. Yeah, I can hear you. Right.
The algebraic structure that you built?
Right. So this is, in a sense, we're using the work of PS19 and CCH plus 19 under the hood, right? Because
Underlying NISIC was you used FHE for. That's the only LWE.
oh, no. So we don't use FHE. We just note that there's an additional work that bootstraps any NISIC protocol to another NISIC protocol using FHE, whose proof size is just linear in the witness size. So, but what our work shows is that we're not actually assuming the existence of a NISIC in the first place. We're building it from scratch. So this is a base construction.
Oh, okay.
Yeah.
I think I misunderstood that part. Thanks.
Any other question? No questions. So let's thank the speaker again. So there's some announcement from Kai Ming.
Hi everyone, just two quick announcements. So the first is about the round session, which will happen tonight. So round session still accept submissions, and the deadline is at noon today. So please consider to submit. And if you want to submit, just go to the Asiacrypt website, and there's a round session item below the technical program. Click that, and then there's a submission button in the page. And the other is a reminder that every morning the coffee shop, there will be coffee served in the fourth floor, the area for the sponsor stands there before 8:30. So you can, if you arrive early, you can have a coffee there and then come back for the talks. Thanks.
Yes, we can see your slide now. Yes. Would you like to test the sound?
Yes, can you hear me?
Yes, no problem. Okay.
Okay,
It look.
great,
Yeah, it looks perfect. Okay.
wonderful.
Thank you.
Hi everyone. Before the session starts, just another quick announcement. So, in this hotel, there will be a fire alarm test in 5-10 minutes. So it will just be a test. So you might hear some alarm inside the room, but that's just for test. So just ignore the alarm. No panic. Yeah.
So, hi everyone. So my name is Marc Joie. I have the pleasure to chair this session. So this is the first one on practical cryptography. There will be 3 talks in this session, and the first one is on some preserving encryption, and talk will be given by Sarah. I see online, Sarah, can you hear us?
Yes, I can.
Perfect, so you can start whenever you want.
All right, well, thank you. So welcome everyone. So I'm going to talk about new algorithms and analysis for sum preserving encryption. And this is joint work with Scott Yellick. So I'm going to start by introducing the problem of sum preserving encryption. So the idea is we're going to create an encryption scheme where the ciphertext and plaintext are both going to be integer vectors, and they're going to have the same sum. So if we sum up all the points in the vector for the plaintext and the ciphertext, they're both going to have the same sum. In addition, each of the components of the vector are typically going to be bounded between 0 and some maximum of d. And this problem was introduced by Tajik et al. In 2019. And they looked at a particular application of sum preserving encryption, specifically thumbnail preserving encryption. So the idea is you want to create an encryption scheme where the thumbnail of the original image and the encrypted image are the same. So we're just to go over, we create the thumbnail by dividing an image into B by B blocks of pixels. And then we're going to replace each block by the mean pixel values, the average of all the pixel values within the block, to create a smaller image. So if we take each of these same blocks and we apply sum preserving encryption to the blocks, then the sum of the pixels in the original image and the encrypted image will be the same. Thus, the mean will be the same, and we've preserved the thumbnail between the original image and the encrypted image. All right, so I'm going to give a little background on this problem and then discuss our new algorithms. So you can think of sum preserving encryption as it's a special type of format preserving encryption. And there's been a lot of work on format preserving encryption. It was originally studied by Brightwell and Smith in '97. It was formally defined and analyzed by Belair, Ristenpart, Ragaway, and Stigers in '09. And they used a rank and cipher unrank construction, which I'll talk about further examples of that here today. And again, it's widely studied and even standardized. So Tajik et al. Introduced this idea of sum preserving encryption, as I said before, and they focused on the problem of creating a thumbnail encryption scheme. Okay, so I mentioned that this idea of rank and cipher unrank is going to be important, so let me just review that real quickly in case you haven't seen it. So the idea is we're going to start with a plain text, then we're going to apply a rank algorithm. So we're going to rank each possible plain text between 0 and n-1, where n is going to be the total number of possible plain texts. So we first start by ranking it, then we have an integer, and we can apply a standard cipher to get another integer, right? This is our encrypted integer, and then we apply an unrank algorithm to get back to a ciphertext. And this is a standard technique in format preserving encryption. So Tajik et al. Realized that we could use this approach for the problem of sum preserving encryption. And so they proposed this idea of representing a string, representing a vector as a string of ones and zeros. So this is the stars and bars construction from combinatorics, if you've seen that before. So we're basically going to, let's say, look at our example, the first number is 5, we're going to replace that with 5 ones and then a 0. So the zeros are going to serve as our separators. So we'll have one less 0 than there are points in our vector. And then our second number is 3, we would have 3 ones, followed by our separator, and then our final one. So if we represent our vectors of integers as binary strings in this fashion, then this is a regular language, and there's some known techniques we can use to turn this into an encryption scheme. However, this has high time complexity, and it's relatively impractical in this situation. However, Tajik et al. Realized that if we do this with just vectors that have 2 points, so if we just have link 2, then this is pretty straightforward. And if you've got some downtime during the next break between talks, you could work out how we could rank vectors of link 2 with a fixed sum. And so they used this idea to create a sum preserving encryption scheme. And it actually can be thought of as a Markov chain. And so I'm going to talk a little bit more about it from the Markov chain perspective in a little bit. So I'm going to present their algorithm, not exactly how they presented it, but as a Markov chain, which they did realize, they did point out that this is a Markov chain. So the idea is they're going to repeat this algorithm in multiple rounds. So they're going to start, again, you're starting from a vector of integers, and they're going to randomly shuffle those points. All right, so you randomly shuffle the points. And then we're going to pair adjacent points to get a perfect matching, right? Randomly shuffled, pair adjacent points to get a perfect matching. And then now within our matching, we have pairs of points, and I just mentioned that we could rank and cipher unrank these points. And so we're going to replace, using this rank and cipher unrank approach, we're going to replace each pair of integers uniformly at random from all the possible valid choices, right? So we have to preserve the sum, and we have to preserve that component bound, all right? So for each pair in our matching, we're going to replace uniformly at random from the possible choices, and then we get another vector that's going to have the same sum and respect those component bounds. All right, so today at our results, we give the first proof bounding the mixing time of the Tajik et al. Algorithm. So, you know, the natural question you might ask when presented with an algorithm like this is how many rounds is sufficient, right? How many times do we have to repeat this? So we give the first formal bound on the mixing time. And in addition, we give two practical rank and unrank algorithms that we can use for sum preserving encryption. And we also create prototype implementations with performance comparisons comparing these three different algorithms. All right, so in the rest of my talk today, I'm going to go over briefly our mixing time bound and some of the proof techniques behind it. And then I'll present the two rank, I'll describe at a high level the rank and unrank algorithms, and then show you briefly the performance comparisons. Okay, so we're going to ask this question for the mixing time bound of how many times do we need to repeat this algorithm. And Tajik et al. Gave a heuristic algorithms for what secure round choices would be, but no formal proof, and so that's what I'm going to present today. And they tested performance with 1,000, 3,000, and 5,000 rounds. Just to formalize, I'm going to talk about the mixing time, and here the mixing time is going to be the amount of time until the difference between the distribution at time t and the stationary distribution is less than epsilon. All right, so we're going to parameterize this by epsilon. All right, and we show that if n is the vector length, d is the component bound, and s is the fixed sum, then the mixing time is upper bounded by n log of the minimum of dn, 2s, and 1 over epsilon. All right, so how do we do this? Well, we're going to use a path coupling technique due to Dyer and Greenhill in '98, and this is a standard technique in the Markov chain community. So before I'm going to kind of give you a high-level view of what the proof looks like, and before I jump into that, though, let me just kind of tell you a little bit about the techniques that we use. I'm sure not everyone's familiar with them. So we use path coupling, which kind of followed on to coupling. So the idea of coupling is we're going to simulate two processes, X and Y, and each of them, if we view it in isolation, it looks just like that Markov chain. And so we're going to simulate these processes until they agree, and once they agree, they stay together. And it turns out if we can bound how long it takes before these processes agree, this is called the coupling time, and this will give us a bound on the mixing time. So we can use the coupling time to bound the mixing time. And how we do this is we generally show that at each step of the Markov chain, the distance between the two chains is getting closer in expectation. So the expected distance between the two chains X and Y is decreasing. And here, we're going to use the Manhattan distance. All right, so in coupling, again, we want to show that the expected change over one step from any arbitrary pair of configurations. So we have to show that this happens for any two configurations in our state space, any two possible, vectors. Path coupling makes this process a lot easier because we can just look at a restricted set of pairs of configurations. All right, so we don't have to look at all pairs, we can just look at a subset. And in this particular case, we're going to choose to only look at pairs that differ on exactly 2 points. So every single other pair in the vector is this every single, X and Y match on every single other point except for just 2. And so we only have to look at these special vectors that only differ on these 2 points. And just to kind of give you an idea why this works, if we show that you can find between any arbitrary pairs of configurations, you can find pairs that are in this special set, right, that only differ on 2 points. And so the expected change in distance between any two arbitrary configurations is bounded by the sum of the expected changes between those special pairs. And so we can use those to get a bound, to get our bound overall. Okay, so just to give you an idea how this works, so again, we're using the Manhattan distance, and we're looking at vectors that just differ on 2 points. So, right, so here there's, again, X and Y agree on everything else except for these two special points. And we want to show that after a single step of the Markov chain, the expected change in distance is going to, right, the distance is going to decrease. All right, so just to remember our Markov chain, right, it starts by randomly shuffling the points, and then it pairs adjacent points. So if after our random shuffling, if these 2 points that differ, if these happen to be adjacent, right, then our distance decreases to 0, right? That we can choose the same new pairs of points in each of our chain X and Y, and the distance decreases to 0. So this is the good case, right? This is going to solve everything. The downside, though, is that if these pairs of points, right, if these match with other points, then it's much trickier. And one of the things that makes this really tricky is that now if we look at the two chains X and Y, the sums are going to be different. And so that means that in many cases, the number of possible, right, remember we're choosing uniformly at random from all the possible ways to replace these points. And so they're going to have a different number of choices, which means that we're going to move to the different choices with different probabilities in the two chains. It turns out we can still show that the expected change in distance, that we can come up with a coupling, right? So we come up with a coupling and we show that the distance will always stay the same or decrease. But it's quite tricky and there's a lot of details that I'm hiding. So I'm not going to go into those details, but that's what makes it interesting, I guess, or tricky is that part. All right. Okay, so I told you we had kind of two types of results. One was this mixing time bound, and the other one was the rank and cipher unring. Okay, so we have two algorithms for ranking and unranking, and I'm going to talk about the first one just a little more quickly because it's not quite as interesting. So the first algorithm for ranking is going to rank the vectors directly using lexicographical order. And here we're going to build on algorithms for unranking that were developed by Stein for use in random sampling. So he's trying to do something different. And he gave an algorithm for unranking according to lexicographical order. And we came up with, added on to that one for ranking. This algorithm is going to rely heavily on a table, which we can pre-compute. And that's going to store, so every point in the table NS is going to store the number of vectors of length n with some s, and the table, all entries across the table will have the same component bound. And with this pre-computed information, we can rank according to lexicographical order, and if you're interested in the details, you can take a look at the paper. The other ranking algorithm is based on what's called, we call recursive block order. And as far as we know, this is not an ordering that has been used before. And so to describe this order, so if you want to order two vectors according to recursive block order, you're going to divide the vector in half, and you're going to look at the left sum and the right sum. And if the left sum is smaller, it's going to be smaller in the order. If the left sum is greater, it's going to be later in the order. And if they're equal, and this is where the recursive part comes in, if the left sums are equal, well, then we're going to take a look, and it's how the vectors relate depends recursively on how the left half relates to the right half according to recursive block order. All right, and so here's an example. So this is different than lexicographical order. Again, we're going to split the vector in half, and we're comparing the left sums to see where it falls, and if they're equal, then we repeat. All right, if we want to rank according to recursive block order, and I'm going to go through this a little bit quickly, so if we want to come up with a ranking based on this ordering, we need to determine, if we have a particular configuration, we need to determine how many configurations are smaller in the order. Right? And so there's basically three different ways that a configuration can be smaller in the order. And so we need to count how many there are in order to rank. And so we can do this using a combination of recursion and the table values that are stored. So if we look at this first, the piece in yellow, right, the number that have a smaller left sum, well, we can count this up using table values. The second one, if they have an equal left sum, but XL is less than YL, right, then we need to determine the rank of XL. And then for each of those, right, for everything that's smaller in rank, the number of configurations there are, right, we multiply the number of ways there are to fill in the right half. And then to get that final piece in green, we're going to take the rank of the right-hand side. And if we add these three things up, we get the rank of a configuration. And you can take that recurrence and turn it into an, it's pretty straightforward to go from there to an algorithm. The nice thing about recursive block order is if you see here, we're only looking at when we make recursive calls, we're dividing in half each time. So we actually only need to see we only need to compute two log n rows of that table versus lexicographical order. So we need much fewer rows, which is going to give us some performance improvements. So both of these algorithms rely on this C table. And so I'm just going to describe quickly, we come up with two different ways to fill this table. And the first one is similar to what Stein does, but in fact, so he doesn't frame it as dynamic programming, which is what I'm doing here, but it essentially is the same technique for filling the table. We actually use a cumulative sum instead of storing the C values directly because it leads to some improvements in the algorithm. And so you can come up with a recurrence for this table. The idea here is we're going to look at the very first vector, the very first point in our vector. And so if it starts with 0, we can count those recursively as shown on the slide. And if it starts with some number that's greater than 0, right? So if it starts with something that's greater than 0, then we can just look at the number of configurations within points and sum one less. And then we take each of those and we add 1, and that gives us something, right? That gives us something in the original C of NS. However, in some cases, we're going to be overcounting here because adding 1 to the first point in the vector might take us above our component bound, and so that's where this third term comes in. I mentioned that in the last, right, in our second ranking algorithm, we only need to look at log n rows of the table, or 2 log n at most, log n if it's a power of 2. But the dynamic programming version of filling the table, actually you would need to fill out all rows, right? And so you wouldn't get that improvement. So we also can fill the table using generating functions as well, and that allows us to only fill the rows that we need, and we can take advantage of the fact that we only need those log n rows of the table. Right, so in addition to the mixing time bound and the ranking algorithms, we did prototype implementations and compared the running time of these 3 different algorithms. I'm not going to go over the slide, that the numbers are up there. I will say that for the specific example of thumbnail preserving encryption, it seems like the ranking algorithms are going to get us an improvement. But again, which algorithm is better is going to depend on your particular choices of N, D, and S. And as we get to larger values of N, the ranking solutions struggle because we have to pre-compute this table, and that table starts to get really large. All right, so in summary, I showed you, well, I hand-waved a lot, a proof of the bounding the mixing time of the Chijik et al. Algorithm. And I showed you, or we gave 2 practical rank and unranked algorithms for sum preserving encryption, one based on lexicographical order and the other based on this new recursive block order. And we created prototype implementations with performance comparisons. That's it, thank you.
Thank you, Sarah. So do we have questions for the speaker? Okay, maybe online, I don't know. No? So maybe, I saw salary as one of the application. What is preserved in that case? I saw I saw in one of your slides that salaries was one of the application. So what do you preserve in that case? So the sum of the salaries?
Oh, yeah, we're preserving the sum. Yeah, so all of our work preserves the sum. I think you could definitely possibly generalize some of these methods if there was a different parameter that you wanted to preserve, but we only looked at sum preserving. A lot of the ranking algorithms are very specific to the sum.
And assume that someone new joined a company, and so in that case, so the sum will change, but then you can deduce the salary of that person. Is that correct? So assume that someone new joined a company.
Oh, yeah, the sum would change. You would have to, yeah,
Okay.
re-encrypt.
Okay. And just the last question. So is there a plan to make a product of what you presented?
Not as far as I know. I would love it if there was, but
Okay. Okay, so thank you.
yeah, thank you.
Yeah. Okay, so we can move to the next talk. Thank you, Sarah. So next talk will be on the Elizabeth string cipher, and the talk will be given by Aurel.
So hi everyone, thank you for the invitation. So this talk is going to be about hybrid homomorphic encryption, which from now on I will call HHE, which is a tool used in a fully homomorphic encryption to solve the problem caused by the expansion ratio. When you're doing FHE, you have to deal with a huge expansion ratio, so this is an illustration of it. So if you want to send some data on the network, and you have a small plain text, the corresponding ciphertext is going to be huge. We are going to try to use what comes with FHE to reduce this. So on the screen you have a usual setup of FHE, where someone is trying to send some data to a server to do some computation, but doesn't want to reveal them. And the server is going to compute homomorphically on them. But once again, sending this data requires a lot of bandwidth. So what we would like to do instead is use another crypto system, much lighter, with a small expansion ratio. And then, since the server can compute whatever he wants, he can also decrypt this small ciphertext to obtain the fully homomorphic encryption he would have had without that, and then compute whatever he wants. But to do so, it needs to have the secret key of the new scheme. So we also have to do one sending in fully homomorphic encryption at the setup, which contains a secret key. So several HHE schemes have appeared over the year, and they are trying to optimize different criteria. The main three being the economy in terms of boundaries in itself, and the other two being the latency and the throughput. And nobody really agrees on which one is the best. So the latency is the time you have to wait to go from a small symmetric scheme, so my gray box here, to a red one on the server, an operation that is called transciphering. And the throughput is the amortized time of the latency, so it's the time that it takes to transcipher only one bit. And it makes sense when you use packing in FHE, which is the ability to store several messages in a single ciphertext. So we wanted to, I'm here to introduce a new scheme called Elizabeth, which will be here on the scheme. But the main idea that we want to introduce is that it doesn't really make sense to compare all these schemes in terms of latency or throughput as standalone scheme, sorry. So in the current state of the art, schemes are designed to optimize some aspect of the HHE, so some aspect of the transciphering time. And then the comparison are done as if the scheme were standalone. And we don't think it makes sense in FHE, since it's losing sight of the fact that in FHE we want to compute something with the output of the HHE scheme. So what we did instead was to start by thinking in terms of use case, what we want to do once we have transciphered, and then design a scheme that will be optimal for that kind of use case. So to evaluate an FHE scheme with a use case, we need a use case. And we choose one that is very common in FHE, and it's machine learning. So it comes with its own set of constraints. First off, in machine learning, we want to use as many bits as possible because neural networks usually work with 32 or 64 bits input. And then we want to be able to compute fast because when you do machine learning, you don't want to wait a long time to have an answer on what you're trying to compute. And then FHE comes with its own set of constraints. So we choose to use TFHE, that is a state-of-the-art crypto system, fully homomorphic. And in TFHE, you don't have the ability to pack messages. So that was something that we knew we would have to deal with. And TFHE is useful when you want to do modular additions and evaluation of negacyclic lookup tables. That is lookup tables in which the second half of the values are the opposite of the first half. Another missing item on my slide is that in TFHE, you cannot store very large messages in a single ciphertext. So we knew that we would have to work with a few bits. So the trade-off was to use 4-bit messages. That was the best we could do to have a small crypto system, a fast crypto system to evaluate while storing as many bits as possible in a TFHE ciphertext. And for the fast evaluation, we made it so that our crypto system will be easy to evaluate on multiple threads at the same time. And regarding the constraint caused by TFHE, we just chose to call them a toolbox inside of constraints, and we use them to design the scheme. So now let's dive into how our scheme is done. So it's called Elizabeth, and it's thought as a successor for a crypto system called Philip, which as all state-of-the-art HHE scheme is based on the filter permutator paradigm introduced by Philip. So the idea is that when you want to generate a key stream, you start from an internal state, and then you do some computation over it. But when you do so in FHE, you add some noise in the output. And if you do it too much, at some point, your key stream will be so noisy that you won't be able to use it anymore. With the filter permutator paradigm, you start from an internal state, and you apply a key stream generator function. And you will always use the same function on the same internal state. So the bits that you produce will always contain a fixed amount of noise. So how are we going to do that? By adapting the filter permutator paradigm to the group filter permutator as a group filter permutator paradigm. So we start from a key register, and using a public PRNG, we are going to choose a subset in it and shuffle it, and then add some random noise in it. So all of these operations are noiseless because choosing a subset and shuffling it, it's not FHE, it's just moving blocks around. On the whitening, it's adding a clear text to a ciphertext, and it's noiseless. So at this point, nothing is noisy in what we did. And then we are going to apply a filter function, and only in the filter function will we add noise to our ciphertext. So in the end, Elizabeth is entirely defined by its filter. So here it is. I do realize there's a lot to see on the slide, so we're going to break it up. The first thing you have to notice is that there's only 3 different things on this. You have 5 input x1 to x5, modular additions, and 8 boxes S1 to S8 that are negatively lookup table, and that are computed through a bootstrap homomorphically. And these lookup tables are the costly part of the operation. Luckily, the first 4 can be computed separately because you don't need the output of each one to compute the others. So you can do that in a 4 separate thread. Then you have an addition, so you have to wait and synchronize. But the next 4 can also be done separately in 4 different threads. So in the end, to compute this box, you only have to pay for 2 bootstraps, and you can compute 8 of them. And this is just a part of the full filter, and the actual filter is this operation done 12 times in parallel. So the entire filter of Elizabeth consists in 96 bootstraps, but you only pay for 2 of them thanks to multi-thread. So now let's have a look at our use case. So this is a neural network that we used for the use case, which is rather small, I think. I was told so by people that do understand what machine learning is. And what it does is classifying pictures of clothes. And believe it or not, but this picture is actually too high def to be used in FHE because it uses 8 bits of gray, and we can only use 3. So why 3 and not 4, even so Elizabeth can store 4 bits messages? It's because to enable fast computation with TFHE, you need to set the most significant bit to 0. So we can only write in the 3 next bits. So by doing so, the neural network lose a bit of accuracy, so it can only answer correctly 90% of the time. But it's okay for us because we know that with FHE we are going to lose a bit of accuracy. So now regarding the timing of Elizabeth, it has been designed to be to use less constraining parameters than any use case that it could be used for. So actually in this table I'm only interested in these 3 values. So if you use Elizabeth with optimal parameters, it's going to be sufficiently efficient, so the timing doesn't mean much because it depends on what computer and hardware you're going to use. But what you can see is that if you use Elizabeth with a use case, then the timing are multiplied by a factor 5, and it comes from the fact that the parameters of the use case, are going to be much bigger than the parameters of Elizabeth. And for every different set of parameters that you want to use in FHE, you have to send another key to the server. So you could choose to use Elizabeth as a plug-and-play crypto system and send nothing to the server, and then the timing are going to be a bit big. But you could also choose to send its own set of parameters for Elizabeth and gain some time. So if you just do an inference, that is an evaluation of the neural network, in FHE without HHE, it's going to take 5 seconds. And if you use Elizabeth with the parameters of the neural network, it's going to be much larger. But once again, it can be much reduced if you use parameters for Elizabeth that are different than the one from the neural network. And in terms of efficiency bandwidth-wise, Elizabeth will reduce the bandwidth used since the very first inference. And if you choose to use the 2 sets of parameters, it's going to take a bit more inferences, so around 2,000 inferences, but it only takes 40 hours, so it's not much in FHE time. So from there, where do we want to go? Well, first off, we would like to be able to transcipher much bigger message at the same time, because with 4 bits, we have seen that there's not much that we can do. And we also think that we should look at that from the machine learning point of view, so without even using cryptography, how can we do better neural networks that are easier to evaluate with FHE? And lastly, we should look for more relevant use case because once again, we think it doesn't make sense to consider HHE without a use case, but we also think that we need to find use cases that are relevant to HHE. So we chose to use this use case because FMNIST is a very common dataset in machine learning, but maybe it's not what you want to do when you use HHE. And we think that people that do understand what is machine learning should look into HHE and find a relevant challenge that will help compare future schemes. Thank you very much for your attention, and if you have any question, I'd be happy to answer.
It does not drop out. Okay. Other questions? Remarks? Online, do you have questions? So you told us that Elizabeth was the successor of Philip.
Yes.
What's the main difference between the two ciphers?
Philip worked in 1-bit messages, and with Elizabeth, we are able to encrypt 4 bits at a time. So that's the main difference between Philip and Elizabeth, and actually between Elizabeth and most HHE schemes, is the ability to work on 4-bit messages rather than in just 1-bit messages. And there are some other HHE schemes that work with several bit messages, but then the output are in infinite field rather than in Z16. So it's less easier to do any computation on them afterward.
Okay, thank you. Okay, so if there are no more questions, so let's thank the speaker.
Thank you very much.
So next talk is on related key boomerang attacks on AES.
Okay, and here's the mic. Hello. So, hello everyone. Let's get started. So, as you can see here, this table summarizes the existing attack against AES 1 and 92. And note that here, by click is not really an attack. It just improves the exhaustive search with a complete loop on the key space. And the current bedtime complexity for an attack on route is 2 to 176 for a related key boomerang of Pirokov and Kovacevic. And in this work, we found a new related key boomerang attack. Its time complexity is 2 to 52 times lower than the best known attack. So here is the boomerang attack. In the left is the best known attack of Pirokov and Kovacevic, and in the right is our attack. Green by here is that means the known different, and we have our attack has the probability is 2 to minus 108 instead of 2 to minus 110. It's a bit better, but it's almost the same probability. Here is a zoom on both input of both attack. So in our attack, we have the more green by than the best known attack. That means we know much more information than the attack of Pirokov and Kovacevic. And in the rest of this talk, I will explain in detail how we found the attack. So anyone here knows the boomerang attack before? Raise your hand. Okay. FSE 1999, David Wagner was first introduced the boomerang attack, and what is studied here if the difference will be combined or not. So I will explain in a basic form of boomerang distinguisher had an attacker as the access for both encryption and decryption cipher. So first, the attacker picks the P1 at random and asks for the ciphertext C1. And secondly, he composed P2 by adding a different alpha and gets the ciphertext C2. And after that, he composed C3 and C4 by adding the different delta to C1 and C2. And next, he obtained the corresponding plaintext P3 and P4. And finally, he checks if P3 and P4 differ by the same different alpha or not. And if alpha come back more often than a random permutation, we will have a distinguisher. And for the original approach, the cipher E divided into two parts. E0 and E1, and we need the good differential for each path. And for the input difference alpha lead to the output difference beta with high probability P, and over E0, and the gamma lead to delta with the high probability Q over E1. And we need then the expected probability is P square Q square with the assumption that two shells are independent. But in practice, this assumption does not always correct. And in 2011, movie shows that the boomerang never come back. And the problem comes from the assumption of two shells that dependent may exist. So to handle the dependency, then my AI propose a sandwich attack. Now the cipher divided into 3 parts instead of 2 parts, E0 and E1 still here, but we have a new middle pass, the EM. And the EM with high probability R, and now the expected probability is P tin square, Q tin square, and R. And so how we can compute the property R of EM? In Asiacrypt 2018, CAR proposed the boomerang connectivity table that reduce the problem of computing the property of the boomerang switch to the one of computing it over XS box. And the BCTNG table here is the number of solutions that the boomerang come back. After that, at FSE 2019, Song and revisits the BCT and propose the BCT framework. This computes the property of boomerang distinguisher with considering the dependency. And to search for the boomerang attack, we typically use some automatic tool for search for the boomerang distinguisher. And CAN use MILP model to study the ladder switch to attack the Delphi. Liu and Sasaki use MILP model to direct research for the boomerang distinguisher on GIP. But this got only reject EM, just only one round. And recently, Delon and introduced a set of tables to calculate the probability of, and they use MILP, CP, and ad hoc approach to search for the boomerang distinguisher on skinny. And our work is based on this work. So this figure has to understand the notation used in the definition. To search for the boomerang characteristic, to search for the boomerang distinguisher, we need to be able to compose the property of the boomerang characteristic. To do that, BCT is not enough, so we need to merge the differential table. We need extra 3 tables here. We have the UBCT for the upper BCT, LBCT for the lower BCT, and EBCT for extended BCT. And so when given a boomerang characteristic, how to compute the probability that boomerang return? Just multiply the property of transition for each S box. But how we can compute the property of transition for one particular S box? That's use a differential table. So here we give an example of boomerang characteristic on 3 rounds. And we need to compute the probability of this boomerang characteristic that the boomerang return. What we need to do here is just look at where we have the boomerang upper shell and the boomerang lower shell with the input different and the output different. And we look at where the different where they are, is the input or the output, is the upper or the lower shell, and see which difference are set to 0 or 3 or specific value. And after that, we look at the summarized table here to see which property they correspond to. On this sample, with this particular box, and here for the upper shell, we have the input and the output difference are set to specific value, and for the lower shell, the input difference and the output difference set to 0, and this corresponds to PBDT. That means the probability of the transition D2. For another particular S block here, the input and the output of the upper shell are set to specific value, and for the input of the lower shell are set to 3, and the output of the lower shell are set to specific value, and it corresponds to the UBCT case. So we can compute the probability of UBCT for this transition, and that's all. So that table had to design a new MILP model to search for the truncated boomerang characteristic. Actually, it's the similar with search for the truncated reference characteristic. Just copy try one for the upper and one for the lower, and adding some new variable for the non-variable algorithm variable, and add some new constraint to new variable for the control of free variable, and there are some specific constraint for the related table to know which table are used in the computation of the probability. The objective is for search for truncated difference to characteristics that counting number of active books, and instead of that, it's counting how many different tables are used, how many tables are involved, how many tables are involved, so on, and with by the maximum probability exponential. One important property of this model is that no middle route is defined for this model. So that means this model is very generic. So we want to use this model to apply AES, to apply the AES. But first, why AES? AES is one of most encryption algorithms in the world. So a block size has the 128 bits. S can be viewed as the magic of 4 times 4 bytes. Big round of AES has the 4 operators. The add round key, stop by, shift row, and mid column, except the last round. There are 3 versions of the AES: AES 128, AES 192, and AES 256. And our model is general, but we use AES 192 as an example because we got a good result for this version. So here is AES 192 key schedule. The key schedule expands the master key into a plus round key, and problem here is that the key schedule is nonlinear, and you cannot control the difference on the key. That change a lot of things, and we need a new model. So what we have in the new model, to handle the nonlinear key schedule, we use related key conditional on the boomerang, and note that here a small change on the distinguisher may lead to a better attack. So we want to directly search for the attack, not only for the distinguisher. And actually, we cannot control the difference on the key, because if we force the difference for both input and output of an S box, then we will reject the possible value, and we look at the weak attack, and we don't want that. We don't want a weak attack. So we need a key generated by a boomerang with property 1, and for our attack, we use a related key with the different astro. In this figure, for the upper shell are above the lower shell. So for the new model, we define some new variable to know which difference are in the distinguisher or the key recover phase. We define a D variable if the variable belongs to the distinguisher, the Z variable if the difference is 0, and K variable if the difference is known, and S if the difference is set to a specific value. And we add some specific rule for both D and S, and there are some problems for the known variable in the key schedule because like when we search for the differential characteristic on AES, many of them are impossible because it does not satisfy the linear relation in the for the system of equation described AES. So actually we want there's such a function in our model, but it's too much for this time. So what we do here, what we need to do here is that use fallback of the Kurobi for each time when we found a solution, and we check if the solution is satisfies the constraint or not. So we're adding some lazy constraint to our model. That's done. So here is the if D equal to 1, that means D in the distinguisher and it will propagate like that. And for D 0, that means it's not in the distinguisher, it will propagate like that. So actually in our model it's more complicated than that. And so how to compose the probability? The probability depends on the trial variable for the upper and the lower trial for input and output different with the Z, K, and S variable. And in practice, we found the 59 possible K, and we need to compose the social probability for each K. And we found 11 possible probability, and we were able to include the value, the probability to our model by adding 5 binary variable and 33 inequality per each box. And we also add extra constraint to ensure that the probability of the distinguisher is greater than 2 to minus 127. And that's all. And for the objective function, we want to optimize the complexity of the attack, but it's quite hard to compute. So we will use an approximation. So what's the master to the complexity here? In our opinion, it's the vector space of the plain text and ciphertext and the property of the distinguisher. So we will maximize this function for the objective function. And actually, our model is very slow, and it's impossible to search for the better type. So we need to recheck the search space by recheck the number of active blocks per round. So for AES 256, we recheck the attack, but for AES 192, we found a better attack, and its time complexity is 2 to 52 times lower than the best known attack of Pirokov and Kovatovich. And here is our attack. So we use the same lower trail with the best known attack, but for the upper trail, it's a bit different for the position of active S box. And that's the reason why a small change in the distinguisher may lead to a better attack. So finally, I will summarize our work. We propose a new MILP model to search the boomerang attack to deal with nonlinear key schedule, and we found a new key attack against full AES 192. Its time complexity is 2 to 52 times lower than the best known attack of Pirokov and Kovatovich. And we also recover the attack on AES 256, and you can read more detail on our paper on AES on Asiacrypt. So for the attention. So do you have any question?
Questions? Okay, so then,
Can I ask, is it possible to apply your technique to AS128 or other AS-based cipher?
Thanks for the question. So actually, our model is inputs, but for AS190S, so it's our model is very slow, and we don't know how to recheck the search space to find the AS190S. So now, including we cannot find it, but we are in progress to improve this model because it's very simple.
Okay, so let's thank the speaker and all the speakers of this session.
I don't need to point. I'll just have a. Okay. Okay. And do I can keep my time. Okay. Okay. And then of course, Rachel will introduce the case. So how do I?
Okay, hello. It's time to start. Welcome to the session. This is session for Zero Knowledge 1. And we have 3 talks here. I'm Masayuki Abe, chairing this session. Okay, we start with short-lived zero knowledge proofs and signatures by Aras Arun.
Thank you for the introduction. So this is joint work. This is joint work with Joseph Bonneau and Jeremy Clark. So imagine you sign something on a piece of paper with disappearing ink. Whatever you signed would vanish after some time, right? You could write a proof on paper with disappearing ink and show it to someone, and it could vanish before they show it to someone else. So the goal of our work is to emulate this with in the cryptographic setting. In other words, what does it mean to make a digital signature or a digital proof vanish? Right. So the way we think about this is with making the soundness of the proof or the soundness of the signature disappear over time. So consider Alice, who signed something at time t is equal to 0, and we want the signature to be sound up to time t. But then after time t, it shouldn't be sound anymore. A verifier looking at the signature wouldn't be convinced that it's Alice's. So this also gives us a notion of deniability. If someone sees the signature after time t, Alice could possibly claim that she never signed it. It could have been made by someone who had no knowledge of her private key. Right. So how do we do this? The underlying technique behind all of our constructions is to allow for signatures to be forged through a slow computation. And similarly, proofs can be forged like that. So here we have a forger who does a long sequential computation of these steps and finally produces a forgery. And to any distinguisher seeing the real signature by Alice and the forged signature, they're indistinguishable. It's really hard to tell them apart. Right. All of this requires some notion of time. So someone getting a signature should know if it was made within the past t's time or not. And it's hard to timestamp every single signature. It's maybe not even possible. So without like a global clock or anything. So what we use instead are beacons. So consider like a global beacon over here, which emits some bits of randomness every delta steps or time over here. And this randomness is unpredictable, uncontrollable. So beacons have been made using randomness from stock prices, blockchain block hashes, and distributed protocols with multiple parties like DRAM and so on. So how would a solution with a beacon look like? If, say, the beacon value B was emitted at time 0, and we want the signature or proof or whatever was created to expire at time t after the beacon was released. So here, say Alice signed something after the beacon was released. The signing algorithm that Alice uses would specify the beacon value B in the protocol, and similarly for proof. And once time t is reached, regardless of when exactly Alice made her signature, the soundness would be lost over there. Right? So without a timestamping mechanism or a global clock, we can use beacons to make signatures expire after a fixed amount of time. Right. Yeah, so in the rest of this talk, I'll go over some applications of short-lived proofs and short-lived signatures. And I'll then go over constructions which use verifiable delay functions as a key tool, and I'll briefly go over the implementation. Okay, so in deniable email. So when email servers exchange emails, they sign outgoing emails to authenticate them. So this is required for security, and it's only really needed during transit. So when the second server receives the email and verifies the signature, it's no longer needed. But these signatures do last forever, and an undesirable side effect of this is that they can be used to validate links. So here's like a picture of a famous WikiLeaks email dump in 2016, where all of the emails were actually kept their Google signature with this. So this is called DKIM, Domain Keys Identified Mail. So this is not the intended use of these signatures, and this problem was popularized by Matthew Green, and where one solution he suggested was Google would like periodically release their signing keys every month or so. It'll be public, and so any signatures made under those keys would so short-lived signatures are like a natural solution to this problem, where when an email server wants to send an email, they sign it with a short signature. It'll be valid for like a few minutes until it's reached and verified, and so it serves its purpose. And then after that point, it becomes invalid. So over here, you could show the signature after time T to the whole world, and anyone could have made it. So it's no longer convincing. Right? And with this, the advantage here is that the signer no longer has to do any actions like releasing their key. They can keep one key, and they don't have to cycle keys or anything. So if you like your private key, you can keep your private key. If for short-lived proofs, an application like an e-voting system. So suppose someone makes a vote to like a ballot box, and the ballot box gives them their proof that their vote was included correctly. Right? An undesirable side effect of this is that this proof can be used to get like paid for their vote, because the proof lasts forever, and it's like a receipt of what they did. So e-voting systems want to have like a receipt-free property. So this you can use a short-lived proof. The proof lasts for a few minutes while they're in the ballot booth, and after that, it loses its meaning, so they can't be, it doesn't function as a receipt. So there have been lots of related work on this area of deniable cryptography. For example, like designated verifier proofs are proofs that make sense to one verifier but to no one else. But we move to like more of a time-based setting where it makes sense to everybody before time T and nobody after time T. Time signatures, I heard of time signatures or time capsule signatures. We gotta solve the inverse problem of this, where for them, signatures are like locked until time T and valid afterwards, where we want signatures to be valid before time T. Keyforge and Timeforge solve the deniable signature problem, where they opt to use actions from the signer or a third party to lose soundness and give deniability. Proof of work or knowledge also solve a problem where someone either knows the witness to a proof or did a long computation, but they use proof of work and it's parallelizable and not really a notion of time. Okay. So just a quick note on formalizing short. So in the rest of this talk, I'll stick with short-lived proofs. So in formalizing them, so they have like a prove algorithm and a verify algorithm. Additionally, they have a forge algorithm, and all of these take the beacon value of the inputs. And completeness is that the proving time should be less than T. For forgeability, the forging time should be just over T. Indistinguishability means that the proofs generated by prove and forge should be indistinguishable. And this gives us zero knowledge because forge can now double as a signature. And we need a new notion of soundness called T-soundness, where you can extract a witness from a prover that can produce proofs in time less than T. But after time T, this extraction guarantee is lost. So all of our constructions will be transformations from a generic or a signal protocol into the short-lived versions of we have 4 transformations for proofs in our paper and 2 more for signatures. I'll briefly go over the proofs here. And key tool in all of our constructions are verify-based. So a VDF is the function that takes a fixed number of sequential steps to compute. But once this computation is done, it's easy to convince a verifier that the computation was done correctly. So here, an example are repeated squaring VDFs, where the input is an element in a group of unknown order, and the output is y is equal to x plus 2 plus 2. And the fastest algorithm to do this is repeated squaring with T steps. But once these T steps are done, they can generate a proof that convinces the verifier that y is indeed equal to x plus 2. So the way these proofs are generated is Kozlowski VDF and Peter Daszak VDFs, which are ways to generate efficiently generate these proofs. I'm not going to get into it, but just suffices to know that a VDF is used. The security property underlying the VDF is that it's hard to convince a verifier without spending time. Okay, so the most straightforward construction to get a short-lived proof is just to take the OR of the whatever relation you want to prove and the VDF verifier. So here, if you have a relation R with input X and witness W, that's one branch of the OR, and the other branch is the VDF verifier, taking the beacon value as an input. Right, so this satisfies completeness because an honest prover can ignore the VDF branch and just satisfy the relation branch with knowing the witness. And a forger who doesn't know the witness will have to satisfy the VDF branch by actually computing the VDF. Right? And since the VDF takes T steps to do, you get T forgeability. Right? We also prove indistinguishability and soundness, which is used for the underlying physics and VDF. Right? Note here that only one person has to compute the VDF output and proof on the beacon value, and everybody can use their Y and pi to forge proofs on any relation. Right, so this stronger notion of forgeability we're calling reusable forgeability, where the first forger additionally produces an advice string that helps make more forgeries. So here, this is really good in practice because one long computation per beacon value can help generate multiple forgeries. And the more forgeries there are, the higher the deniability for a single forgery. Right? It enhances the deniability for you. For the remaining constructions, we are going to transform Sigma protocols. So just to establish encryption, you have a Sigma protocol for relation R with input X, and the first step of the Sigma protocol from A gets a challenge C and sends a response Z, so the proof is ACZ. And Sigma protocols have a simulate function where, without knowing the witness, you can simulate a realistic looking transcript that will make the verifier X. Right, so how do we make a Sigma protocol short-lived? So the first step over here, we're going to split the challenge into two, C1 and C2. And what we're going to do is use, what we're going to do is use C1 as a challenge for the relation Sigma protocol, and C2 as the challenge for the VDF verifier, where C2 XORed with the beacon value will be the VDF input. Right. So why does this work? The intuition is that the forger and the prover will each cheat on different branches of this and honestly complete the other branch. So the forger can simulate the relation branch, but then they'll have to honestly complete the VDF branch by solving the VDF. And the honest prover can cheat on the relation branch on the VDF branch by using pre-computed input, but then they'll have to honestly compute the relation branch, which they compute because they know the witness. So that's the intuition behind this. I won't get into the details of the protocol. Just want to note here that the input to the VDF verifier is not just B, but B XORed with the challenge. So we don't get reusable forgeability like in the previous case. So to get reusable forgeability, we design a new type of VDF called zero-knowledge VDFs, which are similar to VDFs, except that the output Y isn't revealed. You have, again, like if you're exploring VDFs, you have X and you compute Y, so you can explore 2 part T. But you just give a proof that you know Y. You don't have to reveal Y, and it convinces the verifier that you do know the output of the VDF. The neat thing here is that this can actually be represented as an efficient Sigma protocol with a first method C as a challenge and B as a response. And it has a nice simulate algorithm where, without knowing the Y, the output Y, you can simulate a realistic looking transcript for this VDF. Right. We build efficient zero-knowledge VDFs using the proof of knowledge of experiment and unknown orbital from Bonnet Bun's first paper. So now that we have a ZK VDF as a Sigma protocol, we can use the classic Sigma OR composition of the relation Sigma protocol and now the ZK VDF Sigma protocol. And just like Sigma OR compositions, you can simulate one branch and honestly compute the other branch. So the prover can simulate the ZK VDF branch without actually computing the VDF. And they can run the Sigma or the relation Sigma protocol using the witness. But the forger, since they don't know the witness, they'll have to simulate the relations branch and then honestly compute the VDF. So we get complete. Of course, and the neat thing here is that the VDF branch is just the beacon value, so it helps that only one person has to compute the VDF on a beacon input, and it makes other forgeries. We have more efficient constructions, particular for signatures, which use different BDFs called like trapdoor BDFs and watermark BDFs, one of which has reusable forgeability as well. Just briefly going over the implementation, we use Veselowski VDFs, which with RSA 2048 groups, which are pretty large. But even with that, the overhead for transforming Sigma protocol into a short-lived Sigma protocol is pretty low. It's only like half a kilobyte for the proofs and even less than that for RSA signatures. And the prover time overhead is 120 milliseconds for the prover, which is not that much, and much lower for the signature algorithm. So just wanted to highlight here that these transformations are pretty practical and efficient. Right. So with that, I'd like to conclude, and I'd be happy to take any questions. Thank you.
Any questions? So I have one. How fine grain can you control the period of the time?
Yeah.
Is that purely depend on the beacon?
It's actually dependent on the VDF. So here our VDF is y is equal to x power 2 power t, and it takes exactly t steps to compute. So the practical time would depend on the proving hardware and all that, but the VDFs are becoming very standardized with like a specific ASICs to compute this. So it's likely that it won't get any faster beyond a point. Like there will be fast hardware that does it really fast, so we'll have to, that'll probably be the benchmark for the actual physical time that it takes. But yeah, this number of theoretical steps is fixed, but the hardware depends on the hardware.
Other questions? Any?
Hi, thanks for your talk. So I just have a quick question. So are there any technical difficulties when extending from Sigma protocols to multi-round protocols?
Yeah, we haven't thought about that, but yeah, that would be interesting because for us, if they can be composed, like if they have a composition available, I think it would be easy to do. So that might be the underlying thing. You can always try to compose with the VDF and the original Sigma protocol. So that's, I think it will come down to that.
Okay, thanks.
Yeah, that's interesting. We think about it.
Okay, so let's thank the speaker again. The second talk in this session is rotatable zero-knowledge sets, post-compromise secure, auditable dictionaries with application to key transparency. And the speaker is Eli Goldin. Please go ahead.
Hello, everyone. I'm Eli, and I'm going to be talking about rotatable zero-knowledge sets. This is joint work between Zoom, NYU, and Microsoft Research with Brian Chen, Evgeny Dodis, Isha Ghosh, myself, Balachandar Kasavan, Antonio Marcedon, and Mariam Bermau. Our motivation is for end-to-end encrypted communication systems, whereby parties want to communicate securely with each other, but all messages must pass through some untrusted server. This is typically done using public key encryption, but the problem is that users need some way to agree on each other's public keys. If, for example, the user were to host a database of public keys, if, for example, the server were to host a database of public keys, then this could lead to man-in-the-middle attacks, whereby the server could respond with a compromised public key. To prevent this, the most common solution is to use security codes, whereby users will send each other directly a QR code that can be used to verify that the public key returned by the server is in fact correct. This is tedious and requires manual verification, and so can be automated with something called a key transparency system, otherwise known as an auditable dictionary. In a key transparency system, the server will provide a commitment COM to the database of public keys, and whenever a public key is queried, the server will, in addition to the public key, provide a proof pi that the given identity public key pair is in fact in the committed database. Note that we also require a uniqueness property That is, for every identity, there should be at most one public key that can be proved to be stored in the database. Then, as long as all users agree on the commitment, man-in-the-middle attacks can be detected by users verifying that their public key is stored correctly. The database may also update, and perhaps frequently, as users update their public keys. And we would not necessarily want users to have to check that their public key is stored correctly for each commitment. So, every time the server updates the commitment, it will also produce a proof pi that the update has been done consistently, which can be independently audited, not by the users themselves, but by some trusted third parties. And this increases the efficiency as users no longer need to check that their public key is correct every single update. By default, this does not preserve privacy. That is, the proofs may leak information about the database. But there are privacy-preserving solutions for key transparency, namely Connix and Seamless as examples. I will be focusing on Seamless, since that is what our contribution builds off of. Seamless achieves private key transparency using a primitive that they call append-only zero-knowledge sets. An append-only zero-knowledge set, or AZKS, is essentially a key transparency system, but for generalized databases for any label value pairs. The consistency property that the proofs verify is that the database is append-only. That is, the proof, the update proof shows that no database entries have been either deleted or changed. The proofs in AZKS are privacy preserving, that is, they are zero knowledge. The proofs, both query and update proofs, reveal no more information than necessary. And it turns out that to achieve AZKS, the construction in the Seamless paper, really requires some sort of secret key, public key primitive, and that is the database. The server storing the database will also have some secret key that they will use to hide the data, and there will be a published public key that will be used to verify the proofs. Note that Seamless and neither Connix or any existing key transparency system satisfies post-compromise security. That is, if the secret key is revealed during, say, commitment 1, then for all label value pairs, including those added in later generations, privacy will still be lost. Our contribution is to add post-compromise security to private key transparency systems. In particular, we define a new primitive called a rotatable zero-knowledge set, which is the same as an append-only zero-knowledge set with an addition of a rotate operation, which will change the public key and provide a proof that the rotation has been done correctly. The idea is that even if the old secret key is compromised, all label value pairs under the new private key will maintain private. Let me begin by talking about a basic construction of key transparency systems without the privacy guarantee, and I'll show that how Seamless extends upon this to add privacy, and then our contribution on top of that. So the basic contribution is that the commitment to the database will be the root of some sparse Merkle tree, where for every label value pair in the database, there will be a leaf corresponding to the value at the point indexed by the tree path corresponding to its label. Then a label value pair can be proven to be stored in the commitment just by giving the Merkle opening. Note that this does not maintain privacy, as if, for example, the Merkle opening contains some other leaf, some adjacent leaf, then it will reveal the fact that the corresponding adjacent label value pair is stored in the database. To add some privacy onto this, the first thing Seamless does is replaces the value stored at the leaf with a commitment to the values. This then does hide the privacy of the values, and in fact, and so now the new opening for the commitment will be the Merkle opening, as well as an opening for the leaf, the commitment on the leaf. But note that this still does not achieve total privacy, since if there is an adjacent leaf, it will reveal the fact that the adjacent label is stored in the database for some value, even though it doesn't leak the value itself. So we know that we need to, so the first approach, the approach that Seamless will use, is to replace the label indexing the leaf with some other value associated with the label. Note that this cannot be deterministic, as then it will leak too much information about the label. But we may hope that, okay, what if we replace this path with, say, a commitment to the label? This is getting close. This does preserve the privacy, but the problem is now we lose the uniqueness property. That is, for one label, there may be two commitments that correspond to that label. And so therefore, if there are two commitments, then there may be two values stored in the database corresponding to the same commitment, which would be a problem. So we know that we want some randomness in this path, but we need also uniqueness. So the correct approach, it turns out, is to use something like a PRF, which will guarantee that there is only one PRF output for each label, but will still maintain the privacy of the label itself. The problem here, the problem with just using a PRF directly, is that there is no way for verifiers to tell that the Merkle opening, in fact, corresponds to the label. That is, there is no way to associate the output of the PRF on a label with its input. So the key trick that Seamless uses is to index instead with the VRF, with a VRF applied to the label, or a verifiable random function. Intuitively, VRF is just a PRF where you can prove that an output corresponds with its input. More formally, a VRF is a triplet of algorithms, keygen, query, and verify, where keygen outputs a secret key, public key pair. Query takes in a secret key and some input and gives an output and a proof pi. Here I'm going to call the output of the VRF the box containing X for visual reasons. And finally, verify will take in the public key, an input and an output, and a proof, and output 0 or 1. The two security properties we require are uniqueness, that verify should output 1 if and only if Y is in fact the box containing X, and pseudo-randomness, that is the box containing X should look random as long as the secret key is not revealed. Note that pseudo-randomness should still hold even if query proofs for some other inputs are given. So, to add key rotation onto Seamless, we are going to do the simplest possible thing, which is we will come up with a new secret key and public key and completely rebuild the Merkle tree from scratch. This works since new label value pairs are going to be under some new, completely new secret public key pair. But it remains to be shown how to prove that this rotation is done consistently without revealing information about the database. What this boils down to is that we have two sets of VRF outputs, and we need some way to prove that they come from the same set of inputs. And so to do this, what we do is we define a new primitive called a rotatable VRF, which will have this property that you can produce these rotation proofs, and we will show how to construct it. More formally, a rotatable VRF will be a VRF with two additional algorithms, rotate and verrotate. Rotate will take in a secret key, as well as some set of inputs, produce a new secret key public key pair, as well as a proof of rotation. And verrotate will take in two public keys and two sets of outputs under the corresponding public keys, and output 0 or 1. Intuitively, we want verrotate to succeed if and only if for each I, yi corresponds to, say, the blue box containing xi, and yi prime corresponds to the green box containing xi. And also, we want to model post-compromise security. That is, the green box containing x should be pseudo-random even given the old secret key. To model more formally our security, we're going to strengthen the security of the underlying VRF and build up on top of that, just because the stronger security requirements on VRF will make it easier to add more complicated definitions or more advanced definitions. We're going to strengthen uniqueness and extractability condition, which I will not talk in detail about here. And we're also going to strengthen the pseudo-randomness requirement for VRFs to a zero knowledge condition. That is, the proofs for the VRF should be simulatable, even if the output of the VRF is replaced with the output of a truly random function. Then, to define rotatable VRF security, we're just going to combine this post-compromise security property into the zero knowledge requirement. More formally, we're going to model zero knowledge as the idea that a real and ideal game are indistinguishable. And in the real world, we can imagine some Alice interacting with a server hosting a VRF as follows. Alice will receive a public key at the beginning and can make any number of queries to the VRF. Alice may ask also that the server prove that some correct input-output pairs of the VRF are in fact correct, and may ask for rotation proofs, where Alice will pass in some set of inputs, and the server will provide the new public key, as well as a proof that the rotation was correct. Note that implicitly the server will also receive the VRF outputs on both the old public key and the new public key. And finally, to model post-compromise security, we allow Alice to make corruption queries, which will return the current secret key. In addition, we also model some idealized object for perhaps a random oracle or generic group, and we allow Alice to make queries to the idealized object. To define zero knowledge will state that this world is indistinguishable from the world where all these oracles are replaced with a simulator, even when the VRF outputs are all replaced with the outputs of a truly random function indexed by the public key. Note that to model that rotate proofs do not reveal anything about the inputs. We require that the rotate proofs be simulatable, only given the VRF outputs under both the new and old public keys. To make this possible, the simulator has three capabilities. First, it can control the initialization of the public key. It has full control over the idealized object, that is, it can program the random oracle. And finally, whenever a corrupt query is made, the simulator will gain access to all queries made to the random function. This is to model the idea that once the secret key is revealed, the VRF should no longer be pseudo-random. Before I get to our construction, I'll give a brief preliminary on DDH tuples. A DDH tuple is a 4-tuple of group elements, G, H, G to the A, H to the A, where the last two elements are the first two elements raised to the same exponent. Chom, Peterson, and 93 show how to give a zero-knowledge proof that a given tuple is a DDH tuple, and this can be made non-interactive with the Fiat-Shamir transform. Our construction for rotatable VRFs will be based on a standardized construction of VRFs pushed forward by both Seamless and NIST. This is an efficient and simple construction, and our addition will be also simple, so this really is useful for practical purposes. In this simple standardized construction, there will be a random oracle F from the message space to some group, as well as a group generator little g. And how the construction will work is that keygen will sample secret key uniformly at random, and the public key will be equal to g raised to the power of the secret key. Then the VRF output on some input x will be the random oracle applied to x raised to the power of the secret key. To give a query proof, to give a proof that some given output corresponds to its input, all that will be necessary is to give a proof that g f of x pk y is a DDH tuple. Why does this work? Well, if this is a DDH tuple and the public key is equal to g to the secret key, then that definitely means that the output y will be equal to f of x to the sk, which is exactly the same as saying that y is the VRF applied to x. This satisfies all the VRF requirements and satisfies both uniqueness and pseudo-randomness and works totally. To add on to this, we then define the rotate algorithm to simply sample the new secret key and public key uniformly at random. That is, the secret key will be sampled uniformly at random, and the public key will be set to g to the sk, just as before. We will model this for purposes of the proof by saying that the new secret key will be the old secret key times some randomized exponent a. And the reason that this is nice is because this means that the new public key will be equal to the old public key raised to the a. But this is exactly the same as just sampling the secret key uniformly at random. Then, to provide a rotate proof, all that we do is provide a proof that the public key, as well as the first output, and the second public key and the second output, is a DDH tuple. And why does this work? Well, if the first output is the output of the VRF under the first secret key, that is if y equals f of x to the sk, and if the second public key is the first public key raised to the a, that is if pk prime equals pk to the a, then that means that y prime must be y to the a, which is the same thing as the random oracle raised to the secret key times a. But since the new secret key is the old secret key times a, this is exactly the same as saying that y prime is the VRF applied to x under the new secret key. And ignoring rotations under the DDH assumption in a programmable random oracle model, this VRF is zero knowledge, satisfies zero knowledge. And the idea behind this proof is that you can program the random oracle so that the randomized output y equals f of x to the sk. So once we know the randomized output and the secret key, we can choose f of x so that this all works out. But the problem is that this proof approach no longer works once we bring in rotations. And the reason for this is that if we, say, publish two public keys, pk and pk prime, we are going to informationally, theoretically, commit to two secret keys. Then, after we publish these public keys, we may get some input x queried to the random function. And so we'll get some uniformly at random chosen y and y prime. And we're going to need f of x to satisfy both the equation f of x to the sk equals y and f of x to the sk prime equals y prime. Since the public key information theoretically commits to the secret key, and x is going to be chosen after the public keys are chosen, these equations may be impossible to satisfy just by programming the random oracle. So what does this mean? This means that the proof approach for the standardized VRF does not apply when we're dealing with rotations, but that doesn't necessarily mean it leads to an attack. And we tried for a bit and we could not find anything. So what we managed to do is we show that this rotatable VRF is in fact zero knowledge under a stronger idealized model, namely Shoup's generic group model. In Shoup's generic group model, our parties are given access to a random oracle EXP modeling group exponentiation, as well as an addition oracle star, which takes two outputs of the EXP oracle and multiplies them as if it were actually group exponentiation. Importantly, we allow our simulator to program the generic group, just as it could a random oracle. The key trick is that in the generic group model, giving out the public key does not necessarily commit to its discrete log. That is, we don't need to define discrete logs until a corruption happens. And when a corruption happens, all queries are revealed to the simulator. This means that we can choose the secret keys after we find out the uniformly random y and y prime. Now I'll go through a little bit more formally what exactly the simulator do when keeping track of the generic group. So we can think of this EXP oracle as really a table of group elements in discrete logs, where each group element corresponds to some value tracked by the distinguisher Alice. So what our simulator do, the key trick, is that we'll replace the discrete logs with a uniformly random number with polynomials and some special variables. And in particular, discrete logs will be stored this way for group elements that do not come from the EXP oracle, like the output of the random oracle and the public keys themselves. So the variables that we will use is we will set that the output of the random oracle will always have discrete log, a variable corresponding to its input. That is, the output of the random oracle, f of x, the group element corresponding to that, will have discrete log, a variable b of x. And similarly, we will create new variables for each of the a's from the rotation proofs. And in particular, pki will have discrete log, the product of a1 through ai. Then, once we have set the public keys and random oracles to have these discrete logs, we can make sure that the output of the VRF has corresponding discrete logs. That is, the output of the VRF under some public key and some input should have discrete log equal to the product of the discrete log of the public key and the discrete log of the random oracle of that input. We can then define all other addition queries made by the distinguisher to be consistent with what we set the discrete logs to be for these other variables. Then, when a corrupt query is made, we will simply replace each of these AIs with a value chosen uniformly at random. And then we will return that the secret key that has been corrupted will just be the discrete log of the current public key. And what this guarantees is that the output y that is supposed to correspond to VRF of the secret key on x will be equal to f of x to the sk for all sk and x. The key idea here is that the degree of these polynomials only increases on rotation. And since the only issue that could occur really is that sampling these AIs induces a collision on the polynomials, and since the polynomials have bounded degree, the Schwartz-Zippel lemma tells us that a collision will happen with negligible probability, and so this works. So in conclusion, using this generic group model polynomial programming technique, we show that rotatable VRFs satisfy zero knowledge. Rotatable VRFs then give us post-compromise secure auditable dictionaries, in particular RZKS as we define it. There are many additional subtleties and small improvements in both parts. So for more details, read our paper or feel free to come talk to me afterwards. Thank you.
Questions?
Hey, have you thought about like how this would work for pairing-based VRFs?
For pairing-based?
For
pairing-based VRFs?
Yeah, you can kind of use the same construction as a VRF with a pairing group, and then you kind of verify with the pairing.
I have not thought about it at all, but come talk to me afterwards and we can discuss.
Yeah.
Okay, then let's thank the speaker again. Okay, the final talk in this session is by online. Okay. The title of the talk is DAG Sigma, a DAG-based Sigma protocol for relations in CNF. The speaker is Gonjan Zhen. Gonjan,
okay.
Are you ready?
Yeah, I'm ready. Can you hear me?
Please proceed. Yes, we can hear you.
Okay, please allow me start it. Okay, thank you for attending this talk. This is Gongxian Zheng. Today, I would like to present my paper, DAG Sigma, a DAG-based Sigma protocol for relations in CNF. Other co-authors are Junzuo Lai, Zheng Huang, Yu Wang, and Zhiming Zheng. The presentation will cover the following aspects: the background and the motivation, then the contributions of this paper. After that, I will introduce the main idea of the construction. So let me introduce the backgrounds and show you what problem we have studied and why we studied. Sigma protocols are popular and widely used as a building block in many cryptographic protocols. Given a binary and a polynomial time relation and an instance xy belonging to R, the Sigma protocol is run between the prover and the verifier in 3 steps. A commitment, a challenge, and a response are sent in time by the prover and the verifier, where the challenge is randomly picked by the verifier. Finally, the verifier checks whether the transcript is valid or not. Sigma protocols have been designed to prove kinds of relations. Among these relations, K out of M partial knowledge is well studied. As early as 1994, Kramer, Deng, and Shoemaker showed a general method. In 2015, Gross and Kovacs showed how to achieve logarithmic communication when K equals 1. Very recently, Atema, Grammar, and Fair achieved logarithmic communication for general K and N in the discrete logarithm setting. A relation about K out of M partial knowledge can be expressed in disjunctive normal formula, and we call it complete K-DNF relations, since the number of the clauses is a binomial coefficient K over M. It's natural to consider some extensions. The first one is to reduce the number of clauses, and we call such relations incomplete K-DNF relations. The second one is to reverse the symbol of logic AND and logic OR, and then we get a relation in conjunctive normal formula. So we call such relations K-CNF relations. Our paper mainly focuses on K-CNF relations in the discrete logarithm setting. Relations expressed in CNF are an important correction of relations in practice. For example, many access control policies are naturally set in CNF, and they have been discussed in some ABE schemes. In addition, the instance of the K-set problem are expressed in CNF. We also provide a potential application here. A startup company wants to show the investors a business plan which is about building at least a shopping mall in every K neighboring blocks. The startup company also wants to show it in a zero-knowledge way in order to avoid the exact business roadmap being leaked. You can find the relation is also in CNF. To the best of our knowledge, we find the following schemes working for KCNF relations. The first one is proposed by Kramer et al. Here we call it CDS 94. However, it may lead to super polynomial communication cost. The second one is a cyclicity program proposed by Aber et al. But it is designed for non-interactive zero-knowledge proofs, and it seems impossible to transfer a cyclicity program into a standard Sigma protocol. So it loses some advantages of Sigma protocols. For example, low stubbornness error by design, high efficiency, and more flexibility. Therefore, a question is raised naturally. Is it possible to construct a more efficient sigma protocol for KCF relations? Our paper gives an affirmative answer to this question in the discrete logarithm setting. Next, we are going to introduce contributions of this paper. The contributions of this paper are listed as follows. First of all, we formally define the partial knowledge of KCF relations. We also propose a construction in the discrete logarithm setting by transferring the KCF relations to directed acyclic graphics. That's why we call our method DAG sigma protocol. Secondly, we apply our DAG sigma protocols to construct sigma protocols for incomplete K-DNF relations. Due to the time limitation, we will not talk the details here. Finally, we provide an implementation based on elliptic curve groups. It shows that when proving the example relations in our experiments and combined with CDS94, our DAG sigma protocols saves more than 95% communication cost and more than 90% running time. Here is our theoretical comparison. To save time, here I only picked the comparison about KCF relations. You can see that the communication cost of our skin is big O n minus K element in group G and the big O absolute V element in group JP star. Note that big V denotes the vertices of the graph in our DAG sigma protocol. A discussion on upper bound of the number of the vertices shows that the size of our solution is smaller. Actually, is much smaller than that of CDS94, which implies our skin enjoys a better performance. Here are the experimental results. We firstly show the experimental result when K equals 4. The ratio shows how much communication cost and the running time our skin saves. It's clear that there is a remarkable improvement. These figures are the experimental result about different values of K. According to this experimental result, we can draw such a conclusion that when combined with CDS94, our skin achieves a remarkable performance improvement on proving KCF relations, no matter from the view of communication cost or running time. Next, let me introduce the main idea of our construction. Here is a formal definition of KCF relations. In short, every clause contains K different statements with logic OR. Then we combine these clauses with logic AND. A valid witness statement pair for such relation requires that every clause contains at least a true statement. In other words, for every clause, among the K statements, the prover knows at least one witness of them. Then we are going to introduce two building blocks. The first one is an algorithm, KCF to DAG. As the name implies, the algorithm is to transfer a KCF relation to a DAG. There are two properties of the DAG output by this algorithm. The properties guarantees the correctness of our skin. Firstly, every node in some path maps to a statement in some corresponding clause. Secondly, the number of passes with length K equals the number of the clauses. We take relation R1, for example. It contains 4 clauses, and each clause has 3 statements. Figure 5 shows a simple idea to transfer the relation R1, and you can find that there are 4 passes, and each pass maps to a clause in R1. In figure 6, we introduce 3 kinds of states with respect to the in degree and out degree of the nodes, and they are denoted as A, B, and E. We can merge those nodes which represent the same statement and have the same state. As a result, it's clear that finger 6 contains less nodes than finger 5. But the simple operation shown in finger 6 cannot work for some relations. For example, we present another relation R2. Combined with R1, R2 has one more cross. Here we marked it in red. Using the same method of finger 6, we get a result in finger 7. And the cross marked in red is transferred to the path with dotted lines. More exactly, the path is A4, B3, and E1. Then you can find that there is a crossing in finger 7. More exactly, there is a crossing in node B3. Then you can find other new passes, for example, A4, B3, and E2, which should map to a cross sigma 2, sigma 3, and sigma 4. However, we cannot find such a cross in relation R2. Therefore, the number of passes in finger 7 is not equal to the numbers of crosses of relation R2. Then it's contradictory to the properties we mentioned before. A solution is shown in finger 8. More exactly, the node B3 is divided into two nodes, B31 and B32. The example tells us that the DAG output by KCF2 DAG should not contain any crossings. In fact, the algorithm KCF2 DAG is simple and only contains 3 steps: preparing node, merging prefixes, and merging suffixes. For the details of the algorithm, please refer to our paper. Here, we take the relation R2 for example and show how the algorithm works. Finger 9 shows the first step. More exactly, for each cross in R2, we generate a path. Then in finger 10, we show how we merge prefixes. Here, node A51 and node A52 are merged into one node A5. Similarly, node A41 and node A42 are merged into node A4. Finger 11 and finger 12 show how to merge suffixes. Similarly, node E11, E12, and E13 are merged into node E1. After that, the suffixes of the node B21 and the node B22 are the same. In other words, the suffixes are node E1. Then we can merge node B21 and the node B22 into node B2. Finally, we get a DAG, and we can check that the DAG satisfies the properties we want. Here is the upper bound of the number of vertices. We can know one item is the binomial coefficient d divided by 2 of n. Note that in the original expression of a KCF relation, the number of statements can be k times number, where number denotes the number of clauses. The maximum of the number is the binomial coefficient k over n. Therefore, the theory implies that our method can achieve a good improvement. We also provide another method to analyze the upper bound in our full paper. Maybe it's easier for you to understand. First, we prepare two same subgraphies. The length of the passes in the subgraphies is k divided by 2. And the number of the passes in each subgraphy is the binomial coefficient k divided by 2 of n. Then for each cross, we divide the cross into two parts. For each part, we find the corresponding passage in the corresponding subgraphy, and we add an arrow between the two passes. Finally, we remove those passes with length k divided by 2. We can check that the DAG satisfies the properties we defined before, and is easier to get that the number of vertices is k times the binomial efficient k divided by 2 over n, which is similar to the result in our theory. You can find that in some cases, the result in our theory is a tighter bound. Next, we introduce another building block. is a sigma protocol for 1 out of k partial knowledge in the discrete logarithm. The relation is shown in equation 3. In short, the prover knows at least one discrete logarithm of them. Then we recall the chameleon mode of the Snor sigma protocol. Note that in the standard model, the prover in the first step picks a random number r and computes the commitment using r. It's different in the chameleon mode. More exactly, the prover in the first steps calls us the simulator to generate the commitment. In other words, besides a random number r, the prover also computes the commitment using another random challenge, C pi. Here is our sigma protocol for 1 out of k partial knowledge based on Snor's sigma protocol. The main idea is that for each statement, we compute the hash value of its commitment, and the hash value is the challenge for the next statement, such that we can call the simulator to generate the commitment for the next statement. One of the advantages is that the prover only needs to send one commitment of the k statements to the verifier. In other words, we only need to send A1 to the verifier. Therefore, we can reduce the communication cost a lot. Finally, we show our DAG sigma protocol in the discrete logarithm using the above two building blocks. Here is the KCF relation in the discrete logarithm setting. And our DAG sigma has two steps. The first step is to run the algorithm KCF to DAG and get a DAG. We can know that the length of each path in the DAG is k. So the second step is that for each path in the DAG, we run a proving algorithm, which is similar to that of 1 out of k partial knowledge. There are some differences between our scheme and the protocol for 1 out of k partial knowledge. In the 1 out of k partial knowledge, the relation is translated into one path with length k. The hash function only takes one commitment as input, as the corresponding node has only one arrow pointing to it. However, it becomes a bit complicated in the KCF relations. We're taking the relation R1, for example, and its corresponding DAG is shown here. We can find that there are two arrows pointing to node B2. Then, using the same method, we can know that the challenge for node B2 will be influenced by two commitments. In other words, it will be influenced by the commitment of node A3 and node A4. So the hash function takes as input the commitment of node A3 and node A4. Finally, in our paper, we proved that the DAG sigma protocol provides computational knowledge soundness and is spatial HVZK. For the communication complexity, we proved that it depends on the number of the vertices of the DAG. And we show that from the view of the communication complexity, our scheme is better than CDS 94. Here are some references of this presentation. That's all for my presentation. Thank you.
Thanks for the talk. Any questions? Okay, so it looks at when your protocol is turned into a non-interactive using a standard Fiat-Shamir heuristics, it looks like very similar to the one that you introduced in the early part of your talk, which is acyclicity programming approach. How do you compare those two approaches with respect to the non-interactive case?
Yes, exactly. Our method is similar to the acyclicity program. In fact, we combined it with our method in our papers, and the acyclicity program is designed for non-interactive zero knowledge, and we try to convert it into a standard Sigma protocol. However, we failed, so that we proposed the DAG Sigma protocol.
Okay.
Okay, thank you very much.
Any other comments, questions? Then let's thank the speakers and all speakers in this session. Thanks.
Thank you very much.
Any housekeeping announcement? No? Nothing? Okay, then let's go for lunch then.
So the microphone is already on. Okay. Yes. The microphone, the switch is over here, so it's you have the pointer if you like. But it's very difficult. I don't. It's very difficult to type. Yeah, and the page. Yeah, it's from the job. Okay.
Good afternoon. I request everybody to please have a seat. It gives me great pleasure to invite you to the first invited talk of the conference. The talk will be by Jian Guo on evolution of cryptanalysis, security updates on SHA-3 and AES hashing. About our speaker, Jian Guo is currently a faculty member at the Nanyang Technological University in Singapore. He's been working on symmetric key cryptography dedicatedly and has published over 40 papers with IACR since 2007. He co-designed several symmetric key primitives, including the lightweight block cipher LED, the lightweight hash function photon, and continuously provides updated security evaluations to important symmetric key designs such as SHA-2, SHA-3, and AES. He serves the research community actively as General Co-Chair of FSC 2013, Asiacrypt 2021, a member of the IACR Board of Directors since 2020, a member of the Asiacrypt Steering Committee since 2017, and a PC member of multiple IACR conferences and workshops. He has also co-founded the Asian Workshop on Symmetric Key Cryptography in 2011. Let's all welcome our speaker.
Thanks for the introduction and thanks for the invitation. It's my honor to present a talk here. So today I will present a topic on evolution of cryptanalysis, security updates on SHA-3 and AES hashing. So I have to acknowledge all my collaborators on these two topics. They are my ex-PhD supervisors, colleagues, postdoc students, and friends. So today I will try to give the talk in 5 parts. First, I will give the introduction on hash function and cryptanalysis. Then I will move to developments of cryptanalysis, followed by the security status of AES and AES hashing. Then I will summarize. So first of all, I have to emphasize that the talk is educational. So I tend to give the talk to general audience, including people outside of the symmetric key field. So it will not contain too much technical details, but to cover the most updated security status on the field. So starting with the definition of a hash function. Hash function is a function mapping a bit string of arbitrary length to a fixed length digest. So usually we use H to denote the function and N to denote the size of digest. The core security has to offer collision resistance, preimage resistance, and second preimage resistance. Collision resistance refers to the property that it should be computationally difficult to find two different messages such that the digests are the same. So the key here is that there's no restriction on the selection of either message. The attacker, or people who want to analyze it, has the full degree of freedom to choose X and X prime. The second security is preimage resistance. So given a target T, it is computationally difficult to find a message X such that the digest of X is T. And second preimage resistance is very related to preimage resistance. Rather than the digest, the attacker is given a message. And that goal is to find another message such that the digests are the same. It has many significant applications. So, for example, digital signature, we can use the hash and sign approach to generate the signature. Password storage usually comes with a sort together with the password before the hashing. Checksum, so this is used quite often for large file downloading. So to ensure you have a correct file downloaded, usually what we do is to check the checksum against the one provided. If they are consistent, then it's very likely that the file is correctly downloaded. And message authentication code in the way of hashing of a key and message, such as HMAC and NMAC. So SHA-3 was triggered by the broken of SHA-1 in 2005 by Chinese researcher Xiaoyun Wang and her team. Then NIST organized this SHA-3 competition in 2008, October 64 submission received, 2009 July 14 selected for round 2, 2010 December 5 selected for round 3, and 2012 October Kechak was announced as a winner, decided by a group of people from Belgium. Actually, Gia is here. There. 3 years later, the Kechak was formally standardized as SHA-3. It has 4 major digest sizes, 224, 256, 384, and 512. And later on, 2 extendable digest sizes are added. They are named Shake 128 and Shake 256. It has a very different design strategy from SHA-1 and SHA-2. It consists of 24 rounds, and the designer also proposed a Kangaroo 12 with 12 rounds. I will come back to this later. So another major instance of hashing is what we call AES hashing. So AES hashing is a hash function designed from AES. Because AES was so widely used, it will cause a marginal additional cost to implement a hash function if the AES itself is already implemented. So about AES, so it was the successor of DES, and there was the attack by Masri-san, so I think he's also here. I saw him yesterday, at least. So NIST organized this AES competition in 1998, June 15 submission received. The next year, August 5 selected for round 2. 2000 October, Rhino was announced the winner, designed by John and Vincent. And the year after, it was formally standardized, the AES. Supports 3 different keys, 128, 192, and 256. It uses the white chair strategy to resist differential curve analysis because differential curve analysis and linear curve analysis were the major curve analysis technique invented before AES, and it was the major threat to DES. And so the number of rounds are 10, 12, 14, respectively for the 3 different variants of keys. It can be converted to hash function by modes such as Davis-Meyer. So this is one example. So if we use the message as the key and hash the previous chaining value plus the key again, we'll get the updated chaining, and this will be the compression function. So as we know, curve analysis is the major energy consuming, human power consuming parts in the whole symmetric key design cycle. It will take a lot of time, actually lots of design parameters depends on the curve analysis results. So now it serves as tool to trade off between the simplicity, efficiency, and security for designs through round numbers. Okay, so meaning that if usually the design is iterative with the similar round function repeated several times. When we have more rounds, it means we have a larger security margin, but lower efficiency. If we have lesser rounds, we will have higher efficiency, but lesser security margin. So curve analysis methods is try to make the best trade-off between the security and the efficiency so that we get an efficient one, yet not broken. Yeah. The major curve analysis method developed in the past 2 decades includes differential curve analysis, linear curve analysis, integral curve analysis, and meets in the middle attacks, boomerang attack, cube attack, etc. So take differential curve analysis as an example. The major portion of differential curve analysis is to find a good differential path. Good means high probability, yeah, and evolved from hand finding differential paths by hand, and people believe that the Bogan of Shawan was actually done by hand in 2005. And after that, people will write a dedicated program to search for differential paths according to their experiences. Like for lower number of rounds, what are the good ones, and try to propagate to larger number of rounds. Starting from 2011, people started to utilize set-like solvers. From 2019, machine learning also found its application in curve analysis. So the problem is that, so we are given inputs output differences and the number of rounds we want to attack. Then people have to find the intermediate differences so that the overall differential probability is high or optimum. So the approaches are, before we have all the tools, is mainly about human experiences to narrow down the search space. So for example, we know for low number of rounds, 2 or 3, we know how to do it by hand. And if we are to build larger number of rounds differential paths, we repeat them, or we try to add additional rounds on top of the shorter differential passes. Yeah. We also have the meets in the middle approach, meaning that if we have 2 shorter differential passes, we try to connect them by matching the inputs and the outputs of the two parsers. Yeah. So that's what we have done for many, many years. So before we find useful tools like SET and machine learning. So in 2011, SET-like solvers were introduced to cryptanalysis. One of the issues is that it's difficult to predict the solving time, meaning that the only thing we can do now is to try and see whether it gives us the results. If it doesn't, we don't know whether it's not solvable in real time or the model itself has some problem. Yeah. So either yes or no. Machine learning is similarly, so we are constrained by the practical complexity, meaning that once we have the model fixed, we have to train the model in practical time. If that model cannot be done in practical time, we cannot be sure whether the model is working or not. Yeah. So yes, both have this constraint of practical complexity. So for SET-like solvers, it's hard to achieve optimality for any. So it's hard to achieve optimality for any cryptanalysis attacks, which are usually tunable by various parameters. So SET-like solvers are here to help for better optimization. Here I list a simple example. So if we have a list of constraints with inequalities, and we define an objective function, either we want to minimize something or maximize something. So this is a very a simple example of MILP. We can directly input this into the MIP solver, and you will be able to output us the optimum or suboptimum solution. So in this case, it's 1, 2, and the objective is 3, which is maximum. Yeah. So for cryptanalysis, we can actually convert all the constraints into inequalities like this and fit into the solver. Once the solver gives us some solution, then it means a solution to the cryptanalysis results. Yeah? So for example, the differential path search, the constraints are simply we have to make sure the differences, intermediate differences are compatible in each round. So they form a complete and compatible differential path, and the optimal goal is the overall probability, which is dependent on the choices of the intermediate differences. Yeah. With quantum computer in light, we also consider the cryptanalysis under quantum setting. There are two major algorithms available, which are different from the classical ones. So the Grover algorithm, which is also called the quantum search algorithm, it takes the square root n time versus n in the classical computer to do the brute force search. Yeah. So the immediate impact of this is that the security strength of block ciphers is halved. So 128-bit key becomes insufficient because 2 to the 64 is very close to practical time. And second, preimage and preimage resistance of a hash function is also halved, yeah, because of this brute force search. Another algorithm useful for us is the Simon's algorithm. So if the function f is periodic, means that fx is fx plus p for all x in the domain. So it costs polynomial time to find the period p. Yeah. So the immediate application of the Grover algorithm is application to quantum collision finding. So traditionally, quantum attack in classical setting, it will cost birthday time, which is square root of the search space. Yeah? And this can be done simply by selecting 2 to the power of n different values and store the digest in the hash table. And roughly with a probability about half, we'll be able to find the repeated digest. We do the same for quantum setting, except that now we only need to store 2 to the n over 3 because now the search is done by Grover, which can be done in square roots of the search space. So if you have 2 to the n over 3 values available in the space, and the entire space is 2 to the n, the ratio will be 2 to the 2n over 3, and the time to do a search in this ratio is simply 2 to the n over 2 n over 3. Yeah. So the overall time complexity for collision finding in quantum setting is 2 to the n over 3. So it means that if the digest size is 128 bits, it only offers 2 to the 42.7 security, which is insufficient. Yeah. Another impact on differential-based collision attack is that the lowest useful probability changes from 2 to the n over 2 from the classical setting to 2 to the negative 2n over 3 in the quantum setting. Yeah, because with this probability, we only need to do the search in time 2 to the n over 3 in order to find one colliding pair. So in quantum setting, there are potentially much larger search space, and also potentially result in longer attack rounds. Yeah. So with all this in mind, meaning that with the development of the cryptanalysis method from the traditional ones to the solver added ones, and in the setting of classical and quantum, we'll look at the security of SHA-3 and AES hashing. So SHA-3 was following the sponge construction. The design is simple, so the internal function is a permutation f, and it starts with the initial value. So top part R bits is called rate. So at each iteration, R bits of a message is added to the states at the beginning, and this was fed into the permutation f, and this was repeated until all the message bits was processed. Then it goes to the squeezing phase, which outputs R bits at each iteration until you get sufficient many bits needed. So SHA-3, there are four major instances, but they share the same permutation f, meaning that the only difference between the four instances are the parameters R and C. Yeah. It can be organized in a cube. 5 times 5 times 64 cube. It has 24 rounds. Each round consists of 5 steps, and out of the 5, there are only one nonlinear operation. The first step is called theta, which adds the parity of 2 columns into the current bit. So there was the notation of a column parity kernel, means that if all the parity of the columns are 0, then this forms in the CP kernel, and it has some special property because in this case, theta becomes the identity. Yeah, means it does nothing. And so we have the row, which is the lane level rotation. So we have 5 by 5, 25 rows, and each row rotates by a different value of offset according to this table. Pi is the permutation of the lanes according to this formula. So meaning that we just shuffle the position of the lanes. And chi is the only non-linear operation, which is a simple circuit design, actually. We have a value here. It goes through the negation, and together with the next value, go to the AND operation and add this value as itself, so that it updates the speeds. So this applies to every bit. We can easily see that the edge break degree of chi is 2, because there's only one non-gate, and the inverse it has edge break degree 3, which is very low compared to AES. Iota is adding a constant, round dependent constant to the state. So this is to destroy the symmetry. So overall, we can see that the iota destroy the symmetry, and it does nothing else. So in our differential attack, we can simply ignore this one. The first three are linear operations, and the chi is the nonlinear part. So we can actually combine the first three operations to form a big linear operation. The overall attack framework is something look like this. So there are two parts. The left part is what we call connector. The left parts are the differential trail. So again, involve the high probability differential trail search. Yeah, if we have one, yet fulfill the constraint that is this collision, means that the first D bits which is outputted has zero difference, so there's no difference here. If this is the case, then we can ensure it is a collision, and then the first portion is try to connect the initial value with the input difference, which is delta Si. Okay? Hmm? Good. So this portion actually tries to connect the initial value to the input difference here. So we call it connector. So the parts we can control is the rates, because message is added here. So we can choose the correct message we wanted to change the value to what we want freely. But this portion capacity is fixed to 0, so there's no way for us to change it. So the value is 0, the difference is also 0. So there's nothing we can do here. So we only have the degree of freedom of this R bit. Try to connect it to the delta in here after a few rounds. So there's a series of developments work on this. In FSC 2013, the connector was 1 round, and in Asiacrypt 2017, we tried to expand it to 2 rounds by having a fully linearized rounds. Means that here we will have a layer of all S boxes active and try to linearize it. Linearize it means that we try to fix some values of the S box so that the S box becomes a linear operation. Yeah. And at Crypto 2017, we extended this to a partial 3-round connector. Means that we cannot fully control all the defenses, but part of them we can do, so that we leave some of them to be probabilistic matching this data scene, and the rest are by the connector. Yeah. Hmm? 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 I cannot control it. Okay, so the result was at the very beginning, only 3 rounds SHA-3 and 4 rounds SHA-3 can be done. And only 3 round version SHA-3 can be done practically. In 2017, we extended this to 5 rounds practical attacks on SHA-128 and SHA-3 And later, in a journal version of this paper, of these 2 papers, we also extended the practical SHA-3 collision result to be practical. Yeah. Yeah. So that's the original idea without the set. Okay. So as we can see here, we actually involve 3 parts of the attack. The first part is to come up with a good differential path with high probability. The second part is to come up with the connector, which offers sufficient number of solutions for this differential part. And the overall goal is to have an optimum complexity. So 3 parts are done independently before, and they were searched by dedicated programs. And so we can see each part can be replaced by a set-like solver. Yeah? So we did that and combine all these steps together to achieve global optimum. So what we got to are 6 rounds attacks in quantum and classical setting. So my colleague Guozhen will present this paper. I think this is the last talk of today on this portion, how this was done. Right. So that's about SHA-3. So on AES, there are 10, 12, 14 rounds of AES respectively for 3 different key instances. And the round function looks like this. It consists of 4 operations. First is the sub-byte, which replaces each byte by the substitution of S box of its value, followed by the shift row. So you shift left cyclically by 0, 1, 2, and 3 positions. Mixed column operates on the columns, so you multiply MDS matrix with the column and update it. And finally, we have the add key, so which is the round key. And this is the key schedule for AES 128. Yeah. So the major collision attack on AES hashing is by the rebound attack. It also involves the high probability differentials. Yeah. So the idea is that if we have 2 high probability differential, we can chop the entire cipher into 3 portions. So the first one is what we call FBW, backwards, and the last portion is FW, forward, and the middle portion. So what we want is that the probability falls in this the first and last portion are high, so that when it comes to the brute force search stage, it will cost less time, and we want the F-in to connect these 2 portions and offer enough number of candidates for the brute force stage. Yeah, and this rebound attack was introduced in FSC 2009 by Mendel et al. And the first application was to WIPO and Lane. Actually, Lane was removed by this attack. Yeah. And it relies on high probability differentials of these 2 portions. So you can see that where the set-like solvers come to play. The constraint is simply the middle has to match in the state and key if in use through the F-in portion. And the overall goal for optimization is the overall complexity. Means that the overall, which is highly determined by the probability of the first and last portion. Yeah? So the collision attack on AES hashing in the classical setting is reaching 7 rounds with complexity 2 to the 56. So in order for us to have collision, first of all, it has to satisfy the condition that the input difference and the output difference is possible to cancel each other. Yeah, so you can see the pattern in data P and the pattern in data C are the same. Only then it will be possible to generate collision. And then the dotted line is what we have for F in, the middle portion. Yeah, the middle portion. We should be able to solve it by utilizing the degree of freedom from the key. Yeah, and out of that, the first 2.5 rounds is the F in. Yeah, so in the real attack, after the inbound phase, it actually propagates backwards in this way. So the probability we are calculating here is simply we have a mixed column of 4 to 1 here. So here is 1 to 4, that's with probability 1, so we don't pay anything. So it's just here, 4 to 1. Similarly, the last round, we have this for free because there's no more mixed column. Yeah. So the only probability we have to pay is here, and the price that this and this has to match. Yeah. So we have 3 bytes condition here and 4 bytes condition here. So in total, 7 byte condition, which is 2 to the 56. Yeah. This was not possible using the original method because previously the 2 steps were done also independently, meaning that the high probability differential of the forward and backwards portion are searched independently. And the matching was done in the second step. So although each step you might reach the optimum, but globally it may not be the optimum. Yeah. So after we actually consider the 2 steps in one and put them into one solver, so it then be able to give us this new result together with the triangulation algorithm. And in the content setting, as I mentioned, in the content setting for collision, we can go for the probability as low as 2 to the 2n over 3. We are able to extend this attack to 8 rounds. So again, in order for us to have collision, we have to ensure that the pattern, which is 8 bytes active here, and outputs are the same. Yeah, so they are possible to cancel each other, and we are able to solve a very big inbound phase, which covers 5 rounds here. So from here to here, we cost nothing because it is 1 to 4. Yeah, and from here to here, we cost nothing because it is 1 to 4. Yeah. So in the end, the only price we have to pay is this one matching this one. Yeah. And it costs 2 to the 34 in content setting. So we can see in content setting, this is a very low complexity. So if quantum computer comes to reality, this might be the first targets we can actually implement and carry out the finding. So overall, for AES hashing, classically we can reach 7 rounds, and in content setting we can reach 8 rounds. In total, there are 10 rounds, so the security margin is is becoming small. Yeah. So in summary, we've seen some developments of CUP analysis method from the traditional methods to the ones by dedicated search programs to the ones aided by set-like solvers. And now, starting from 2019, we see CUP analysis methods aided by machine learning. So the idea is to mimic the differential-based key recovery attack by machine. Yeah. So we first train the machine to distinguish the reduced rounds with high probability differential from random ones. Means that as long as we know there's a high differential probability covering the entire portion of the attacked cipher, the machine should be able to detect it, yeah, by calculating the number of output differences satisfying this high probability differential, yeah. And then to launch the key recovery attack utilizing such differentials. So these two steps were done by hand before, and now it can be mimicked by machine. Yeah. The first attempt was done by Gore at Crypto 2019 with application to Simon, and the second attempt was by my team. I guess you have heard the talk yesterday by Zhen with all the details. So it was the first time achieving a complexity which is better than man-made attacks. So Simon was actually analyzed quite intensively since the proposal was made public in 2014, and it was actually unexpected that machine can actually do better than what we did, because we have accumulated like decades of experience on differential-based key recovery attacks. Yeah. However, the limitation of machine learning is that it's limited by practical complexity, meaning that when the model gives you results, that means the model is working and it gives you results, and the result should be right. If it doesn't give you the results, there will be two possibilities. Either the model is wrong, or the model simply takes too long to output the results. Yeah? By our experiences so far, the application of machine learning-based CUP analysis is capable to apply to very short block size block ciphers. So Simon has the major targets we tried here are 32-bit block size, yeah, which is very small. Once it scales up to 64 or 128, the model becomes very, very slow and takes too much memory to do the training, and it won't be able to output us the results in practical time. Another difficulty is that there's currently no theoretical treatment of this machine learning-based CUP analysis. So for for traditional differential CUP analysis, we can do projection. Yeah. So if we can carry out the practical key recovery attack based on differential, then we can do a projection by adding up the number of rounds, because we know adding this much of rounds, the differential probability will drop by this much. This is predictable, yeah? And the complexity of the final key recovery will also scale up accordingly. However, in machine learning, there's no such thing, okay? Because we have to ensure we get a distinguisher before we can do key recovery. And we can only guarantee us we get a distinguisher by the result the practical results so far. Yeah. When the block size scale up or the number of rounds scale up, the machine is no longer able to distinguish the target and the random oracle. We are not able to tell whether this is due to our limited amount of resources or due to the fact that it becomes indistinguishable. Yeah. So a theoretical model to treat this machine learning is in urgent need, so that we can try to scale up the text to larger block sizes and larger number of rounds. In conclusion, so far, collision attacks of SHA-3 is up to 6 rounds. So there are lots of security margin left, because the SHA-3 in total have 24 rounds. So we are only attacking 25%, leaving 75% as the security margin. So maybe Kangaroo 12 is a good idea, because it has only 12 rounds, means it can be twice as fast as SHA-3, and still we have 50% security margin left. For AES, we can do up to 7 or 8 rounds in classical and quantum setting. It's still usable because we have 20-30% security margin. But in quantum setting, it becomes very risky to use AES in hashing mode, because it has 128 bits block size, offering maximum 2 to the n/3, which is 2 to the 43 collision resistance in theory. Yeah. So even there's no attack, I guess very soon we'll be able to see brute force search on 128 bits collision. Yeah. So it's not advisable. So to resist quantum attacks, people should really think about block ciphers with larger block size, such as 256. Yeah. So what to expect from future developments of cryptanalysis? We really want to have a deeper look at the core algorithms under the solver and machine learning. So for both, as I mentioned, for both solver-based and machine learning-based cryptanalysis, the bottleneck is that we are limited by practical time, practical resources. And when the model doesn't output us anything, we don't know whether it is due to the model or due to the fact that it becomes infeasible to attack. Yeah. So we really want to figure out how to project this so that we can scale up our algorithms and the text to a larger space. Yeah. And another reason is to having this, it is possible for us to select according to the performance of the underlying solver or machine learning the best strategy to model the attack. Yeah. So that you actually reduce the practical solving time. Yeah. Yeah, that's my talk. Thank you.
Any questions?
Thank you for the nice talk to the collision search on the hash function and the AES. My question is, you mentioned that the break quantum, I mean that the classical and the quantum setting. What's the difference? I mean that I interpret that when you search, you will use classical searching over global search. That is the difference. What is the difference?
Here.
Okay, that is you're using global search.
Yeah, global search.
So how do you assume that the complexity of global search? Just classical searching is very simple, right?
Yeah.
So how can you estimate the complexity of global search?
Yeah, so the current global search complexity is assumed to be the square root of the search space.
Okay.
So of course, I don't have a quantum computer. I cannot
Okay,
ensure
okay,
it
I see.
practically, but that's the everybody
This
has.
is, okay. I can understand. That is a theoretical.
Yeah, that's theoretical. Yeah.
Okay,
So-
another question, maybe I can challenge later.
Mm.
Is it possible to break by quantum machine learning?
Quantum machine learning.
Yes.
This break what?
Maybe next year.
Okay, so there are two things which is constraining us from using machine learning for cryptanalysis. One is time, the other is memory. I think the most constrained resources is the memory so far, because to train a very large block cipher, especially with 64 or even 128 bits block ciphers, the amount of data increase exponentially. So it becomes impossible for the machine model to accommodate so many data in memory. Yeah. However, for time, I think we can use up a supercomputer to parallelize all the computations. Yeah. Yeah, in that sense, I think it's difficult, especially given that the quantum memory is much harder to achieve than classical memory. Yeah.
Thank you.
Any more questions? All right, let's thank the speaker again.
Hello, Morgan, can you hear me?
Hello?
Hello, yes, we
Hi.
can hear
Yes. Great.
you. Yes, yeah.
And let me see if the screen share is working.
Let's see. Okay, perfect.
And it'll go through the slides. Okay, looks
Okay.
good.
Looks good. Thanks.
Oh, okay, thanks. Okay. All right. The session will start in 2 minutes. So.
you know if I'm supposed to keep track of whether okay, I want maybe you are more familiar with me than me. Have you seen the saxophone speaker? You don't see the name? No. Okay. Yeah, okay, I'll try to, when you're speaking out, maybe try to find it. All right, welcome to the Asiacrypt session on multi-computation tool. The first talk is concurrently composable, non-interactive secure computation, and Andrew Morgan will give the talk.
Thank you for the introduction. So yes, this talk is based on work done jointly with my advisor, Rafael Paz. We both regret that we're unable to make it to the conference in person, but we're happy to have the opportunity to present our work remotely. So to get right into it, in the setting of two-party computation, which we consider in this work, we have a receiver and a sender, both with private inputs, who wish to jointly compute some functionality f on their respective inputs, in such a way that a potentially malicious party participating in the protocol wouldn't learn anything about the other party's input besides what they could logically infer from the output of the protocol anyway. So formally, we call this notion simulation-based security, where a computationally bounded adversary should be unable to distinguish between their view of the real execution of the protocol and their view of an idealized execution with a trusted third party and simulated messages which are independent of the honest party's input. We note that secure computation was originally studied in an honest but curious or semi-honest setting where the adversary had to follow the protocol but could attempt to learn additional information. But in this work, we consider fully malicious adversaries which can deviate arbitrarily from the protocol. If we consider one-sided functionality, where only a single party needs to receive the output, a minimum of 2 single message rounds of communication is necessary to avoid residual attacks. Protocols achieving this minimum are referred to as non-interactive secure computation, or NISC. NISC protocols with trusted setup are well known. In the plain model, it is just as well known that 4 single message rounds are both necessary and sufficient for maliciously secure two-party computation under standard simulation-based security. So, to construct NISC in the plain model, it is necessary to use a standard relaxation of security known as super polynomial time simulation, or SPS, where the simulator is allowed to run in slightly super polynomial time. If we relax our security definition to SPS, it turns out that NISC with malicious SPS security in the plain model is possible and can be constructed based on sub-exponential versions of standard assumptions such as decisional Diffie-Hellman, residuosity, or learning with errors. However, for a lot of potential applications of secure computation, we need stronger security properties than are guaranteed by standard simulation-based security. In practice, protocols can be run concurrently with many simultaneously active instances and an adversary able to adaptively observe the results of certain interactions and use them to influence others. And also, protocols can be run as a sub-protocol in a larger composition of protocols, where we would intuitively wish to guarantee that a composition of provably secure protocols is likewise secure. Neither of these two properties are implied by the most basic definitions of simulation-based security, which we henceforth refer to as standalone security. Some of the classical definitions of simulation-based security did consider a composability property, but the first framework to guarantee both concurrent and composable security is the well-known Universal Composability Framework, or UC, proposed by Canetti in 2001. To prove that a protocol is UC secure, one needs to show an analog of simulation-based security, but against a much stronger external party than a classical adversary, an environment which can invoke many concurrent instances of a protocol, corrupt potentially many parties, and observe and control corrupted parties' communication. As such, it's a strictly stronger notion and thus more difficult to prove than classical simulation-based security, but correspondingly provides stronger security guarantees. Of course, because it is strictly stronger, UC-secure two-party computation with polynomial time simulation is subject to the same impossibilities in the plane model as standalone security. So to even consider building UC-secure NISQ, we need an analog of SPS security. Simply allowing superpolynomial time simulation in the standard definition of UC security doesn't preserve composability. So instead, in this work, we consider a notion of angel-based or oracle-aided UC security, where the environment and simulator both have access to a specific superpolynomial time helper oracle, or angel H, but are otherwise restricted to polynomial time. The added strength of UC security in comparison to standalone security also means that historically we have a far more limited space of results for UC secure two-party computation than we have for standalone security. As I mentioned earlier, standalone SPS secure NISQ is already a solved problem, but even considering concurrent security without composability, the most efficient two-party computation protocols prior to our work are protocols where all parties receive the output and thus require 2 rounds of simultaneous broadcast where every party sends a message simultaneously, and thus these protocols would require 3 single message rounds for two-party computation in the single message setting we consider. Furthermore, if we want both concurrently and composably secure protocols, the best known constructions prior to our work require an unspecified constant number of rounds of communication. So it's remained an open question whether concurrently and composably secure NISQ, or for that matter, even concurrently secure NISQ for general functionalities, can be constructed with malicious SPS security in the plane model. So our work answers that question in the positive by providing a construction of NISQ that does achieve angel-based UC security, and shows that the minimum of 2 single message rounds for two-party computation can be achieved for this considerably strengthened definition of security. Specifically, our construction of UC secure NISQ, which we dedicate the majority of our paper to presenting and proving formally, requires 2 key building blocks: a standalone sub-exponentially SPS secure NISQ and sub-exponentially secure non-interactive CCA secure commitments. Concerning the realizability of the assumptions, the standalone SPS secure NISQ is, as I've mentioned, well known from sub-exponential versions of standard assumptions. Non-interactive CCA secure commitments, on the other hand, are considerably more involved, and I'll turn to a brief discussion of those now. So these are tag-based commitments, which are non-interactive in that committing to a value requires a single commitment algorithm rather than an interactive process. And they satisfy a binding property that a commitment can't be open to 2 distinct values, and most notably, a strengthened notion of chosen ciphertext hiding, analogous to the notion of chosen ciphertext security for encryption, which is defined by a security game where an adversary is allowed adaptive query access to a decommitment oracle, which we call O star, which on receiving a commitment returns the corresponding value in randomness usable to produce that commitment. So the adversary will then interact with a challenger C, giving it an adaptively chosen tag and 2 values to commit to, and the challenger C will respond with a commitment to a random one of the 2 values. So the adversary then breaks security if it can correctly guess which value the challenger committed with probability significantly greater than 1/2, and without having queried the decommitment oracle in any commitment that has the same tag as the challenge. In this work, we also consider a relaxation of CCA security, which we call weak CCA security, where the oracle in response to a query returns only the value committed rather than both the value and the randomness. As it turns out, this relaxation is sufficient for our NISQ construction. Unfortunately, the known constructions of non-interactive CCA secure commitments thus far do require more sophisticated assumptions compared to our other building blocks, standalone secure NISQ. Their original construction relied on adaptive one-way permutations, a strong non-falsifiable assumption, and more recent constructions have been proven based on sub-exponential security of a variety of sets of assumptions, such as hinting pseudo-random generators, keyless collision-resistant hash functions, and time-lock puzzles, though the authors of this work remark that the former of these, hinting PRGs, can be based on standard assumptions such as sub-exponential CDH and learning with errors. Given this, it might be a natural question to ask whether we can potentially bypass the requirement for non-interactive CCA secure commitments and base concurrently composable SPS secure NISQ on a weaker set of assumptions closer to the standard assumptions required for the base standalone NISQ protocol in our construction. However, in a second key theorem in our work, we answer that question in the negative. We show that the implication from our first construction is basically bidirectional, and that non-interactive weakly CCA secure commitments are both sufficient and necessary to construct UC secure NISC. Specifically, alongside our initial theorem constructing the NISC protocol, we have a second theorem showing that given a UC secure NISC protocol such as the one we construct, we can build a non-interactive weakly CCA secure commitment scheme. This, combined with the fact that, of course, our Oracle-aided UC secure NISC is a strictly stronger definition, trivially implies standalone SPS secure NISC, will imply that our construction in the first theorem is based on nearly minimal assumptions. There's a minor gap, which is that our NISC construction requires sub-exponentially secure primitives, while the primitives implied by UC secure NISC only have polynomial time security. For the sake of time, I'll defer the details of our second theorem to our paper, and I'll spend the rest of this presentation providing some insight into some of our ideas behind Theorem 1 and our construction of NISC. So, we begin by leveraging the properties of the underlying NISC to perform the computation of the joint functionality F, as might be expected. Of course, we need to guarantee UC security, which is not provided by the underlying NISC. And in technical terms, this will require the simulator we construct for a definition of simulation-based security to be able to extract a corrupt party's input from the message they send in order to deliver it to the ideal functionality in our idealized interaction. And of course, because the simulator we construct for Oracle-aided UC security is by definition restricted to polynomial time, as might be expected, we can't just leverage the super polynomial time simulator from the underlying NISC to do our work for us, since it's super polynomial time. So instead, we rely on the super polynomial time helper functionality H, which we're given by our definition of Oracle-aided UC security. In our case, this helper will implement the CCA decommitment Oracle O star, and it will extract inputs from commitments to messages that will be sent alongside the internal NISC. The tag-based security of the CCA secure commitment scheme we require will effectively guarantee that we can implement this helper functionality to only decommit commitments with corrupted parties' tags. And this will ensure the adversary and environment, which are also given access to this helper functionality, can't just trivially break security by decommitting honest parties' commitments. So, starting with the underlying NISC, I'll build up our protocol on the right side of the slides while discussing at a high level the steps we take to implement UC security as we add them to the protocol. So I'll start by considering the malicious receiver case. As I just discussed, we add the extractability necessary to provide simulation-based security by having the receiver commit to their input X and send it to the sender in the first round along with their internal NISC message. Of course, with that, we need to guarantee that the malicious receiver commits to the same X they input to the underlying NISC. And so we add functionality to the NISC to implement what can be thought of as interactive witness encryption. So the receiver provides the randomness that they use to commit to X. The sender provides the commitment they receive from the receiver, and the NISC verifies that the commitment is valid and rejects it not. So this ensures that a malicious receiver can't receive the output from the functionality unless they sent a valid commitment to the sender in the first round. While we now have extractability for the receiver's input, there's another issue, which is that the simulator in this case needs to be able to simulate the sender's message in the interaction to send it back to the corrupted receiver. And what's more, looking ahead to the corrupted sender case, we'll also need a way to verify the correctness of the sender's input. And to do that without requiring an additional round, we'll require a super polynomial time simulatable zero knowledge argument to verify that the sender's NISC message is generated properly with respect to some private witness, which in this case is the input Y and the randomness the sender uses. This will also need to be simulated in the corrupted receiver case, which is why I'm bringing that up now. And this is in fact non-trivial because the simulator doesn't know the sender's input Y, only the result output by the ideal functionality. So in order to simulate both the NISC message and the zero knowledge argument independently of the sender's input, what we'll do is we'll add a second track to the functionality of both the NISC and the zero knowledge argument. So the receiver will now generate a random trapdoor T and commit to it alongside its input X, and it'll verify it within the internal NISC similarly to X. The sender now has the option to input the trapdoor into the NISC, as well as proving in zero knowledge that they did so rather than providing their input Y. And if they choose to do so, if they choose the second track and provide the correct trapdoor, they can input an additional value Z and program the output of the NISC by fixing it to Z. So what does this accomplish for us? Well, in the real execution of the protocol with an honest sender, this doesn't make a difference. The sender will just input Y into the NISC and a zero knowledge argument like they did before and complete the execution that way. But now in our idealized interaction with the simulator and a malicious receiver, the simulator can use the helper H to extract the trapdoor T from the receiver's message, use the trapdoor instead of Y, which they don't know, to complete the NISC and zero knowledge argument, and program the output of the NISC to whatever is returned from the ideal functionality to complete the interaction. That completes the case of a corrupted receiver. In fact, we're almost done with the corrupted sender case as well, since we already added a zero knowledge argument to verify the sender's message. There's one thing that remains, which is to provide a commitment to the sender's input Y so that we get the same extractability property as we added earlier for the receiver's input X. And to do this, we augment the zero knowledge argument by adding commitments to the respective witnesses for each track. And we additionally prove that those commitments are valid. This serves a double purpose. So first of all, like I was just discussing, this adds extractability for the sender's input Y in the corrupted sender case. And what's more, it adds an argument of knowledge property to the zero knowledge argument where the sender intuitively proves not only that their witness exists, but also that they know it. So what we get out of this is ensuring that the corrupted sender can't provide a valid witness to the second track of the functionality without having actually recovered the correct trapdoor T and broken the CCA security of the commitment scheme, since in this case, the trapdoor T was committed to by an honest party. So actually at this point, we now have the finished protocol, and to recap and illustrate, I'll briefly go over how we construct our simulators for the proof of security. So first, recall it as our simulator is restricted to helper-aided polynomial time. We'll have to avoid using the simulators for the underlying NISC and zero knowledge argument because they specifically require super polynomial time. Instead, we need to rely on the decommitment helper H to provide the extractability property. So in the corrupted receiver case, the simulator will begin by receiving the first message from the adversary, and it will use this helper functionality to decommit the commitments to X and T and retrieve the input X and trapdoor T. And of course, recall that if those commitments aren't generated properly and consistently with the receiver's inputs, the internal NISC will just reject anyway. So next, it sends the extracted input X to the ideal functionality, which will return the result Z star of F applied to X and the honest sender's input Y. And then finally, it'll complete the interaction using the second track of the NISC and zero knowledge functionality by inputting the extracted trapdoor T and hard coding the NISC output to the result Z star that it got back from the ideal functionality. This ensures that the corrupted receiver receives a final message that opens to the correct output of the functionality, while also ensuring via security of the NISC and zero knowledge argument that the adversary can't distinguish this final message from a message in a real interaction that would use the first track. So in the corrupted sender case, the simulator doesn't know the true receiver's input X, and it begins by sending a simulated first message which commits to a dummy value, 0, instead of X, but is indistinguishable due to CCA security of our commitment scheme. It then receives a response from the adversary and aborts if the NISC or ZK reject. Since the adversary is unable to retrieve the trapdoor T without breaking CCA security of the commitment scheme, what that means is it's overwhelmingly likely that if it submitted an accepting zero knowledge argument, it must have used a valid witness and commitment to the first track, which by definition must include an input Y consistent with the sender's input. So in that case, the simulator will retrieve the commitment to the first track witness from the sender's message, use the helper to retrieve the sender's input Y from that, and in turn send it to the ideal functionality, which computes F and Y in the honest receiver's input X and returns the correct result to the honest receiver to conclude the protocol. So, with my discussion of the protocol and simulators complete, to summarize, we present the first known round, minimal, or non-interactive two-party computation protocol, which satisfies a strengthened definition of concurrent and composable security. Specifically, it satisfies Oracle-aided or Angel-based UC security against malicious adversaries in the plain model. And it's constructed based on standalone SPS secure NISC and CCA secure non-interactive commitments. Furthermore, as an additional result, we show that these assumptions are not only sufficient, but also necessary to construct UC secure NISC. While the details of the second theorem were omitted from this talk due to time constraints, we do formally present and prove that theorem and its respective construction in the paper, along with the details and formal proof of our main results. And with that, I'll conclude. Thanks for attending, and I will take questions with what time we have left.
Thank you, Andrew. Do you have any questions from the audience here in the room? Okay, I don't think we have questions from the room here, and there's no question in the Zoom chat. I just had a quick question. You mentioned that you needed this non-interactive zero-knowledge functionality, and it follows from the NISC protocol.
Yes.
Are you assuming that the underlying NISC is semi-honest security or
malicious?
I see. Okay, but in a standalone setting or right? Okay.
Yes. So the underlying NISC is standalone, maliciously superpolynomial time simulatable secure.
I see. But for the NISC, you only need it to be standalone secure. Then you don't need the NISC to be concurrently
right.
secure. I see.
Yeah, it's just standalone secure. So we can implement it using. We can implement it using the standalone secure NISC that we assume for the basis of our construction.
Okay, great. Thanks. And any questions? Okay. I think there are no other questions. So let's thank the speaker.
Thank you.
So our next talk is attaining guarantee output delivery beyond honest majority with friends and foes. And I think Pratik Paul might be giving the talk, or there might be some special arrangements.
Hi, is it possible to play the recorded video? Hello? Thank you.
Presenting our work Attaining GOD Beyond Honest Majority with Friends and Foes. This is a joint work with Aditya Hegde, Nishad Koti, Varsha Bhatkukala, Arpita Patra, and Pratik Paul. Let me begin by defining secure multiparty computation, also known as MPC. MPC allows n mutually distrusting parties, say P1 to Pn, each holding a private input, to compute a joint function of their inputs. This distrust among parties is modeled as a centralized adversary which can corrupt up to T out of the n parties. Now, any MPC protocol is required to satisfy the following properties: correctness of the output computed and privacy, that is, nothing beyond the function output should be revealed to the adversary. Now, although the classical definition of security for MPC does talk about what is revealed to the adversary, it does not take into account the leakage of information towards the honest parties. That is, an adversary can actually leak information towards honest parties by sending across its entire view to them, and this wouldn't be considered as a breach of privacy. In fact, several protocols in the literature actually leverage this loophole in the privacy definition in order to achieve the strongest security of guaranteed output delivery, or GOD, which allows the honest parties to receive their output irrespective of the adversary's strategy. The way these protocols achieve it is that they require all the parties to send their private inputs to a designated party which is identified to be honest, or a trusted party, TTP, which computes the function and returns back the output to these parties. Now, although this allows you to achieve GOD, in practical scenarios where the MPC protocol is deployed, these parties may be actually servers owned by different companies. In such a case, even though the servers are honest, leakage of information to each other may not be a feasible solution. This is where the notion of friends and foes security, or FAF security, defined in the work of Elon et al. Comes into the picture. Here, instead of modeling every party as purely honest, it tries to model them to be at least semi-honest. For this, in addition to considering a malicious adversary, which can corrupt up to T of the parties, it also considers an additional adversary, which can corrupt up to H star of the remaining parties in a semi-honest manner. To capture the view leakage from an adversary, it allows the malicious adversary to send its entire view to the semi-honest one. Now, the security is required to hold in the face of both these adversaries. That is, the private inputs of n minus t parties not under the control of the malicious adversary are required to be secure. Additionally, the inputs of the n minus t minus h star parties not under the control of either of these adversaries are also required to be private. Given that this friends and foes notion is more practically relevant, in this work we focus on constructing FAF secure protocols. Our contribution here is twofold. On the theoretical side, we prove the necessity of oblivious transfer, OT, for constructing a generic T, H star FAF secure protocol when n is lesser than or equal to 2T plus 2H star. This subsumes the optimal corruption threshold of achieving fair or God MPC in this model when n is lesser than 2T plus H star as defined in the work of Elon et al. Given this, we focus our attention to the small population MPC protocols and construct a protocol Quad Squad, which is a 4-party protocol which can tackle one malicious and one semi-honest corruption. Our protocol has two variants, fair as well as God. Note that in the 4-party setting, this is the optimal corruption threshold as defined in the work of Elon et al. To ensure efficiency, we operate in the pre-processing paradigm, which consists of two phases, an input-independent but a function-dependent pre-processing phase, where most of the computationally intensive tasks are carried on, and an online phase, which is input-dependent. Also, we construct our protocol over rings in order to leverage the CPU architecture. Finally, we show the applicability of our protocol in the domain of privacy-preserving machine learning, PPML, to show its practical relevance. Coming to our theoretical result, the necessity of OT, we prove this by reducing a T, H star FAF protocol, say PyF, to a 2-party semi-honest OT protocol, PyOT. For the sake of this presentation, I'll assume n equal to 2T plus 2H star. However, in the paper, we show this reduction for all n lesser than or equal to 2T plus 2H star. So consider the protocol PyF for the following functionality. Party P1 has input as two messages, say M0 and M1, and party Pn has an input bit P. The remaining parties do not have any input to the functionality. The output of the functionality is as follows. All the parties excluding Pn receive a bot, whereas the party Pn receives message MB. Now, in order to reduce this protocol to an OT protocol consisting of a sender and a receiver, we do the following. The first T plus H star parties are emulated by the sender of the OT protocol, say PS, and the remaining T plus H star parties are emulated by the receiver PR. Note that the sender in the OT protocol has an input of two messages, which corresponds to the input of P1 in the protocol PyF. And similarly, a receiver in an OT protocol has an output message, say MB, and an input bit B, which corresponds to the input and output of the party Pn. Now we note that whenever a sender is corrupt, it corresponds to a corruption of T plus H star parties in the underlying FAF secure protocol. And given that this corruption is semi-honest, since we consider a semi-honest OT protocol, the corruption in the corresponding protocol PyF is also semi-honest for these T plus H star parties. And this is exactly the idea that we use in order to prove the security of the OT protocol. Moving on to our practical results, before actually going into the construction of our protocol, I will go over the communication costs and its comparison with the existing works. So in the paper, we have compared our protocol quad squad to the state-of-the-art fourth-party protocols in the honest majority as well as the dishonest majority setting. And here, we have reported the communication costs in terms of field or ring elements, depending on what is the underlying structure that the protocols use. And also the cost is reported per a multiplication gate. And we note here that our FAIR as well as GOD protocol have a comparable online cost to that of the state-of-the-art honest majority protocols of Tetrad and Fantastic 4. Although the pre-processing cost in our case is higher, this is justified by the necessity of OT, which we have already proven. And additionally, our protocol also tackles a stronger adversary compared to the honest majority. That is, it has one additional semi-honest corruption which it can handle. On the other hand, our protocol completely outperforms the dishonest majority protocol of Mascot, both in the pre-processing as well as the online phase, while improving the security guarantee from abort to FAIR and GOD. It is also important to note here that we achieve our GOD protocol with the same online cost as our FAIR protocol. Moving on to the approach that we take in our case. So we view the function as a circuit, which is evaluated in a topological order. Now at a very high level, this evaluation occurs in three phases: input sharing, the actual evaluation of the addition and multiplication gates, and output reconstruction. For the sake of this talk, I will be focusing on only the evaluation phase, wherein addition happens locally, so we'll be focusing more on the multiplication. For every subprotocol that we design for each of these phases, we follow the following idea, high-level idea. So either each subprotocol will complete successfully, or we identify, in case of a malicious behavior, we identify a dispute pair which is guaranteed to include the malicious party. So if we stop at this phase of dispute identification, then what we get is a FAIR variant of our protocol. And to improve the security guarantee to GOD, we run a semi-honest 2PC amongst the parties outside the dispute pair. Note that since the dispute pair already includes the corrupt party, a semi-honest 2PC protocol is sufficient. Finally, in order to maintain the same online cost from the FAIR to the GOD protocol, we use the segmented evaluation approach, wherein we break down the entire circuit into chunks of segments which are evaluated sequentially. Before going to the protocol construction itself, I'll briefly describe the challenges involved in moving from FAIR to GOD MPC. So consider two segments, SM-1, whose outputs are given as inputs to the segment SM. Now, in the case when we are running the 4PC protocol which we have designed, both these outputs and the inputs are in the 4PC sharing semantics. Now consider the case when the segment SM-1 completes a successful evaluation and its outputs are in the 4PC sharing semantics. However, when we now come to segment SM, some malicious behavior is detected here and we end up identifying a dispute pair. This segment has to now be rerun with the 2PC amongst the parties outside the dispute pair. So what we have now is the segment SM-1 with its output in the 4PC sharing semantics. And we require the segment SM to be rerun with the inputs being in the 2PC sharing semantics. This requires a share conversion to be in between these two phases. Now, in the honest majority setting, such a share conversion can be done in a non-interactive manner due to the high redundancy involved in the sharing. However, in our case, since we are tackling a stronger adversary, our sharing semantics inherently have this higher threshold of sharing, which we will see in the following slides, due to which the redundancy is lower. This requires our share conversion to be actually interactive. So note that once we execute the segment SM with 2PC, all the following segments will be run only with 2PC. So the only rerun that we have done here is for this particular segment SM, which allows us to retain the cost from FAIR to GOD protocol. Let me begin describing our protocol hotspot, starting with the sharing semantics. To ensure efficiency by operating over rings, we rely on replicated secret sharing, also known as RSS. Here, in order to tackle the corruption of one malicious and one semi-honest, with the view leakage which is possible, we consider a threshold of corruption of 2, which leads us to 4,2 RSS sharing. This implies that a secret is divided into 6 components in such a way that every pair of parties holds a common component. Say party P1 and P2, for example, hold the component S12. In contrast to the honest and dishonest majority setting, we have a higher number of share components, which poses a challenge in ensuring efficiency in our protocol. Instead of considering a replicated secret sharing of a value directly as described, we tweak the sharing slightly in order to achieve a better efficiency in the preprocessing paradigm. And for this, to share a value, we consider 2 components of sharing. One is a mask, say alpha x, which is replicated secret shared as described before. In addition, we consider a masked value, which forms the second component of the sharing, say beta x, which is equal to the actual value x plus the mask alpha x. Now, this can actually be viewed as RSS sharing of the value x itself as follows. The way this helps us is that the first component of the sharing, alpha x, can be computed during the preprocessing phase, whereas the second component, beta x, can be made available during the online phase. As mentioned, I won't be describing the input sharing in the output reconstruction phase. Instead, I'll directly go to the multiplication protocol in our case. So consider a multiplication gate with inputs x and y and output z. Now, the goal of a multiplication protocol is the following. Given the sharing of the input wires x and y, which consists of the 2 components I described before, the goal is to compute the sharing of the output wire, say z. Now, using known techniques in the literature, it is already known that this can be reduced to a reconstruction of one element, which is beta z in our case, in the online phase, and a computation of the multiplication triple, which corresponds to alpha x, alpha y, and alpha x times alpha y in our case, in the preprocessing phase. So this is exactly what we do in our protocol, and I'll detail these reconstruction and the triple generation in the subsequent slides. Coming to the reconstruction protocol, we see that in the sharing of any value, say z for example, any party misses 3 components of the sharing of the mask, that is alpha z in this case. For example, consider party P1, it misses the shares alpha z23, alpha z24 and alpha z34. Now each of these components is actually held by 2 other parties. For example, alpha z23 is held by party P2 and P3. However, requiring the parties to simply send across this value to P1 does not suffice. Consider the case when one of these parties is malicious. It can send an incorrect value to P1 and P1 wouldn't be able to identify the correct value out of these 2. For this, we use a primitive called as the joint message passing or jump primitive defined in the work of Coty et al. This primitive allows 2 parties holding a common message to send the message to 1 or 2 other parties in such a way that either the send is successful and the parties receive the common message, or a dispute pair is identified. So the way we approach our reconstruction is as following. Every pair of parties holding the component which is missing for party P1 sends it across to P1 using the joint message passing or jump primitive. Now the communication cost in this case for a jump primitive is 1 element if you're trying to reconstruct to a single party. So a reconstruction towards one party in the following manner would require 3 elements of communication, which corresponds to 12 elements of communication when you're trying to reconstruct the beta z towards every party. So given this, we reduce our communication cost for multiplication, which in turn requires this reconstruction, from 12 elements to 7 elements using some optimization which requires 3 rounds in total. Moving on to the multiplication triple generation. Note here that we are trying to compute the sharing of alpha x times alpha y, given the sharing of alpha x and alpha y. We note that writing alpha x alpha y in terms of the shares of alpha x and alpha y results in 36 summons. We categorize these 36 summons into 3 types based on the number of parties which can compute them locally. For example, we have summons of type S2, which can be computed by 2 parties locally, summons of type S1, which can be computed by a single party locally, and summons of type S0, which cannot be computed by any party locally. For summons of type S0, we use OTs in order to perform this computation. For summons of type S2, two parties compute these values locally and complete the sharing. For summons of type S1, we note that 6 summons each can be computed by 1 party. So we make this party compute the sharing of these summons and finally give a zero knowledge proof that they have indeed done this computation in a correct manner. So this summarizes the 2 components of our multiplication. Summarizing the cost of our protocol again, we see that the online communication of 7 elements actually corresponds to the 7 element reconstruction, which I just described, which happens in 3 rounds. And the retaining the cost from FAIR to GOD protocol for the online case comes from the segmented evaluation approach. Finally, coming to the PPML benchmarks, we have benchmarked the neural network inference task over the MNIST dataset by instantiating servers across different continents using Google Cloud Platform. Now we note that although the total communication cost of our protocol, the FAIR as well as the GOD variant, is comparatively higher than that of the honest majority protocols, the online communication cost is indeed comparable. Given that our protocol tackles a stronger adversarial model, which is practically relevant, it becomes a very much feasible option to be used in practice. The code for our protocol is available publicly at the link provided. Thank you.
Hello everyone, my name is Shashali. I'm going to introduce our paper in Asiacrypt 2000.
Do we have any questions for the audience? We usually say to thank the speaker, but it's a pre-recorded talk, and I think the speaker is not in the Zoom room. So. But any questions for one of the co-authors for the paper? All right, I guess we should thank them for the pre-recorded talk. Maybe we can move on to our next speaker then. Okay, all right, so our final talk for the session is towards practical topology hiding computation by Shuai Li.
Hello everyone. Can you hear my PPT? Can you see my PPT? Hello everyone. Can you hear me?
Yes, we can hear you.
Okay. I'm sorry. Okay. Can you see my PPT? Okay, hello everyone. My name is Shuai Li. I'm going to introduce our paper in Asiacrypt 2022. The title of our paper is Towards Practical Topology Hiding Computation. Secure multi-party computation allows n parties to securely compute some function without leaking additional information about the inputs. Classical MPC assumes that either two parties can communicate directly, namely, the communication graph is complete. So what if the communication graph is incomplete and even sensitive? Moran, Odlov, and Richardson formalized the concept of topology hiding computation. Informally speaking, a THC protocol is an MPC protocol over incomplete graph, which doesn't leak any information about the communication graph. In the setting that an adversary may statically, passively corrupt any number of parties, THC has been shown to be feasible on any graph. Alcavier, Lovini, and Moran showed that THB is feasible over general graphs. This implies that any function can be topology hidingly computed over any graph. The reason is that if there exists a topology hiding broadcast for some graph class and a PKE scheme, then THC exists for the same graph class. We know that MPC computing any function exists. To construct a THC protocol for computing some function f, we just use THB and PKE to simulate point-to-point channels in an MPC protocol computing f. Assume that Pi wants to send X to PG. They do the following. Firstly, PG uses THB to broadcast its public key. Then, Pi encrypts the message X using the public key of PG, and then uses THB to broadcast the resulting ciphertext. Finally, PG can decrypt the received ciphertext to get X. Other parties know nothing about X because they do not know the decryption key. A key true in existing THC protocols is PKCR encryption. This is a special PKE scheme. With PKCR, one can add or delete a public key layer to or from a ciphertext. Namely, with PK and an encryption of X and key, one can generate an encryption of X and key times PK, and an encryption of X and K times the inverse of PK. In some of our protocols, we require the PKCR to be linearly homomorphic. We refer to the paper for more details. Although THC has been shown to be feasible, existing THC protocols are not practical. In this paper, our goal is to improve the efficiency of several existing THC protocols on circles and general graphs. Firstly, we consider the broadcast functionality. The AM and ALM protocols are the state-of-the-art THB protocols on circles and general graphs respectively. They are designed for broadcasting a single bit and built by first presenting a topology hiding all protocol, and then letting the broadcaster take the broadcast bit as input, and each other party take 0 as input. The AM and ALM protocols can be described in the same framework. This framework contains two phases, the aggregate phase and the decrypt phase. The aggregate phase takes T rounds, T equals n-1 in AM, and 8 times the third power of n times kappa in ALM. At the first round, for each party Pi and each of its neighbor D, Pi encrypts its input bit to C and a fresh public key PK, and sends PK and C to its neighbor D. At each following round, each party Pi chooses a permutation sigma of the set of its neighbors. AM uses the only non-identity permutation, and ALM uses a fresh random permutation. Then, for each ciphertext received from neighbor D, Pi adds a public key layer and homomorphically adds its input bit to this ciphertext, and then sends the resulting ciphertext to neighbor sigma D. The decrypt phase also takes T rounds at the end of the aggregate phase. Each received ciphertext has been the all of all the inputs. To decrypt these ciphertexts, the parties send each ciphertext back through the same work it traversed during the aggregate phase, and each party deletes its own public key layer in the reversed work. Now we saw how to improve the AM and ALM protocols. Octavia, Levine, and Moran observed that computing an inclusion of A or B from A and an inclusion of B does not require any homomorphic property of PKCR. If A equals 1, then the computing party outputs an inclusion of 1. Otherwise, it outputs an inclusion of B. Our observation is that computing all is okay for broadcast. If we only consider broadcast, then we let the parties do the following. If the computing party is the broadcaster, output an inclusion of A. Otherwise, output an inclusion of B. In this way, the broadcast value does not need to be a bit, namely, any plain text can be broadcast. In the original AM and ALM protocols, each party needs to send a ciphertext to each neighbor and each round for broadcasting just a single bit. Note that a ciphertext is of length at least all kappa bits. With optimization, if we instantiate PKCR with egomorph scheme, then we can set the plain text length to kappa bits and the ciphertext length to 2 times kappa bits. Namely, kappa bits can be broadcast with each party sending a ciphertext of length of kappa bits to each neighbor at each round. Therefore, the communication costs for both the AM and ALM protocols for broadcasting kappa bits are reduced by a factor of O kappa. Now we consider the sum functionality. The only topology hiding sum protocol on circles is compiled from the AM protocol. Using additively homomorphic inclusion, a secure sum protocol can be constructed as follows. Firstly, each party encrypts its input and sends the resulting ciphertext to P1. Then, P1 homomorphically adds all the ciphertexts. Finally, the parties distributedly decrypt the final ciphertext. As we stated in our paper, this protocol has linear communication cost, On times kappa bits. Recall that topology hidingly sending a single bit using the AM protocol will cost O n squared times kappa bits. By compiling this sum protocol into a THC protocol, we obtain a topology hiding sum protocol with the communication cost O the third power of n times kappa squared bits. Our idea is that instead of compiling black box from THB, we modify the AM protocol to be a topology hiding sum protocol. To achieve this, we require the parties to know the value of n and the PKCR to be additively homomorphic. Note that the AM protocol only assumes that the parties know an upper bound of n, and so does the THS protocol compared from the AM protocol. In the AM protocol, each party homomorphically or its input bit to each received ciphertext. Instead, we let each party homomorphically add its input value to each received ciphertext. The efficiency of this THS protocol has the same asymptotic communication cost as the AM protocol, namely On squared times kappa bits. Now, let us consider the general computation functionality. As before, the only general topology hiding computation protocol on circles is compiled from the AM protocol. We consider a general computation protocol based on additively secret sharing, which contains 3 phases. In the input sharing phase, each party additively shares its input, which requires to send On share. The total communication cost of the input sharing phase is On squared times kappa bits. In the circuit evaluation phase, the parties compute the circuit gate by gate. Addition gates can be computed locally. The parties can compute a multiplication gate using linearly homomorphic encryption, resulting in n times kappa bits communication. The total communication cost of the circuit evaluation phase is O C times n times kappa bits. In the output recovery phase, each party sends its share to P1, and then P1 computes the sum of all the shares. The total communication cost of the output recovery phase is On times kappa bits. By compiling this MPC protocol into a THC protocol, we obtain a general topology hiding computation protocol with communication cost O the first power of n times kappa squared plus c times the third power of n times kappa squared bits. Now, we saw how to share the inputs and recover the output more efficiently using our THS protocol. To share an input X, the input owner Pi samples a random value R, and each other party Pj samples a random share Xj. Then, the parties execute our THS protocol, where Pi takes plus R as input, and each other party takes Pj takes minus Xj as input. All parties will get the output, which equals X plus R minus the sum of all other shares. Finally, Pi takes Z minus R as its share. The total communication cost of sharing n inputs will be the third power of n times kappa bits. To recover the output, the parties execute our THS protocol, where each party takes its share as input. The communication cost of recovering the output will be O n squared times kappa bits. Now, we consider the circuit evaluation phase. The key point of circuit evaluation is to realize the multiplication functionality, which receives additive sharings of X and Y, and returns an additive sharing of X times Y. Our starting point is that a sharing of X times Y can be computed as follows. Firstly, the parties generate a sharing of a random value R. Then the parties execute a protocol to let all parties securely get the value X times Y minus R. Finally, the parties can locally compute a sharing of X times Y. Note that a sharing of a random value R can be generated locally by letting each party sample a random value Ri and setting R to be the sum of all the Ris. The left goal is to publish the value X times Y minus R. To achieve this, we require the parties to know the value n and the PKCR to be linearly homomorphic. To publish the value X times Y minus R, we divide the aggregate phase into two subphases where each takes n minus 1 rounds. In the first subphase, each party homomorphically adds its share of X to each received ciphertext. At the end of the first subphase, the parties have encryptions of X. In the second subphase, each party Pi first computes an encryption of X times Yi minus Ri, and then homomorphically adds this ciphertext to the received ciphertext. At the end of the second subphase, each party has the encryptions of X times Y minus R. Finally, the parties execute the decrypt phase as in the AM protocol. The efficiency of our topology hiding multiplication protocol is O n squared times kappa bits. Our final result is an optimization for the LZM3T protocol of Lavini et al. This protocol is an FHE-based general topology hiding computation protocol on general graphs. In the aggregate phase of this protocol, each party Pi appends the ciphertext of its input Xi and its ID, IDI to each received ciphertext. At the end of the aggregate phase, each party Pi will receive T pairs of ciphertexts. The corresponding plain texts can be parsed as encryptions of all the inputs, and the parties can homomorphically compute the given function. In the aggregate phase of the LZM3T protocol, each party sends a ciphertext vector of length OT to each neighbor at the Tth round. Note that the total number of rounds is O the third power of n times kappa. Hence, the number of the ciphertexts sent by the party is O the 8th power of n times kappa squared during the aggregate phase. We give an optimization for the aggregate phase to reduce the communication. Our idea is that in the aggregate phase, each party sends ciphertext vectors of length n at each round, and for the ith entry of the ciphertext vectors, The parties act exactly as in our optimized ALM protocol, with PI being the broadcaster and the input of PI being the broadcast value. This way, at the end of the aggregate phase, the last party in each work will get a ciphertext vector containing the encryptions of all the inputs. Our optimized aggregate phase only requires the parties to send all the sixth power of n times cap ciphertexts. This is a presentation of our paper. Thank you for listening.
Yeah, audience in the room.
What?
Oh yeah. Sorry, I heard a voice. Questions? Oh, I'm sorry. Confused. Oh, sorry. All right. Actually, if there are no questions here, let's just take all the questions online and let's thank all the speakers in the session.
Okay, thank you.
Okay. Okay, good afternoon, and welcome to today's last section. It's quantum algorithm section, and I'm Seung-Wan Hong, and I'll be chairing this section. So there will be 3 talks today, and 2 in person and 1 online. So let's start with the first talk with title Nostradamus Goes Quantum, so which will be presented by Barbara Giabao Benedict.
Hello, everybody. My name is Barbara, and today I'm talking about our paper Nostradamus Goes Quantum. But first, I want to say thank you for the introduction and thank you for you all being here after such a long day. Our paper Nostradamus Goes Quantum analyzes the Nostradamus attack on hash functions in the quantum setting. And this paper is a joint work together with Mark Fischlin and Moritz Suppert. Originally, Nostradamus was the name of a well-known pharmacist of the 16th century who published poems in order to predict the future. In 2006, Kalsey and Kono, they introduced a modern Nostradamus who wants to prove his prior knowledge about a specific event. For example, the lottery draw next Saturday. So this modern Nostradamus wants to use cryptography instead of poetry. And therefore, he commits to a hash value by target before the event, and afterwards he publishes a document containing the correct prediction and having this hash value by target. So you can imagine someone who says, hey, I'm kind of a prophet and I know the lottery numbers, but I cannot tell you them because then you could cheat the lottery. But what I can tell you is the hash value of my prediction, which I would send you afterwards. And you also don't need to try to guess the lottery numbers based on this value by target, because I add somehow a kind of a secret signature at the end. And of course, this is just a picture you can keep in mind of this modern Nostradamus. But nonetheless, it is a desirable security property for hash functions, that this can only be possible if someone really knows the lottery number. So this is kind of a pre-image resistance. And everyone else who does not know the lottery numbers but try to publish a hash value, we call him the Nostradamus attacker. In case that the hash function fulfills an iterative property, which I want to explain later, we can specify the time complexity of such a Nostradamus attack. So someone who's not a prophet or a magician and only wants to pretend his prior knowledge. Our contribution is the development of a quantum Nostradamus attack, which proves that the time complexity can be reduced significantly. You can see it if you compare the factor before n. It decreases from 2/3 in the classical setting to 3/7 in the quantum setting. And moreover, we have found a lower bound, which proves that our attack is essentially optimal. And this is what I want to do today. First, I want to explain our quantum attack, and then I will show you the proof idea of our lower bound. Okay, so as I said, the Nostradamus attack is only applicable to a special class of hash functions, the iterated hash functions. These are functions which process the input message block by block in order to compute the hash value. As a simplification, I only will consider for my talk Merkle-Darmstadt constructions without padding, like it is shown here on this slide. Nonetheless, our attack is also applicable in case of padding, like SHA-2, or to sponge-based hash functions like SHA-3 or shake. And if you're interested how we deal with these functions, I would like to invite you to read our full version, which can be found on ePrint. And Also, what I want to mention on this slide is that we do not need further properties of the hash functions besides some regularity assumptions, because the attack is a generic attack. This means we do not exploit any concrete details like a bit flip at a specific position of the function. And this is also the reason why our attack is applicable to random compression functions. So this H in this box we also call compression function with high probability. Now I want to introduce some notions by showing you the formal definition of the Nostradamus attack. As you have seen in my introduction, there are mainly two attack phases, one before the event and one afterwards. These phases are represented by the algorithms A1 and A2. A1 outputs the target value, which he sends to the challenger, and a state, which then can be used by algorithm A2 to compute the final document. The event itself is represented by a message P, which is sampled uniformly at random by the challenger. We call this message P also prefix, since the final document should start with this message. In the second phase, A2 outputs a message S based on the state, the target value, and the prefix. And this message we also call suffix. And the algorithm or the adversary wins this game if the document containing prefix and suffix has the hash value y target. In the classical attack of Kalse and Kono, this state is the so-called diamond structure. And this diamond structure we also want to construct in our quantum attack, so I will explain this in more details. This diamond is a binary directed tree, and each node is representing a hash state and each edge a message block. And this graph fulfills a special property. If one edge directs from one node to another, this means that we can get from the first state to the other via the message block, so this M, which is represented by the connecting edge. And the algorithm A1 outputs then the root of the diamond as the target value. In the second phase, the algorithm A2 uses the diamond structure to compute the suffix. So this is the same picture as before, but we rotate the graph, the diamond, 90 degrees. And what the algorithm is doing for this is, first it computes the final hash value, hash of P, where P is a prefix given by the challenger. And then he searched for a so-called linking message, which connects hash of P with one of the leaf nodes of the diamond. And then the suffix is simply this message mlink, this linking message, concatenated with all message blocks along the path from the leaf node to the root. And note that every other path with the corresponding linking message would be a valid suffix as well. And as I already mentioned, our quantum attack basically works in the same way, but we want to use quantum algorithm instead of classical one in order to construct this diamond structure and also to find this linking message. And basically, these both tasks are about finding special message blocks. And for this, Grover's algorithm is very, very useful. In case that we can define a set of message blocks, we call them the suitable ones. So these are the message blocks what we are looking for. Then we can use Grover's algorithm, and it outputs one of the suitable message blocks after O of square root of P to the -1 valuations. And P is the probability that if I have a random message block, that this is suitable as well. So in case that there are a lot of suitable message blocks, we can find them faster because then the value p, the probability is bigger. And in this context, valuation means the check of a message block if it is a suitable one or not. And in the context of the Nostradamus attack, it's a evaluation of the compression function. So how can we apply it in order to do the Nostradamus attack? First, I want to show you how we can use Grover's algorithm to find the linking message. Because this is an easier case, since when we have this diamond structure given, so then we know the leaf nodes, and it's very easy to define the suitable message block. So every message block which connects hash of p with one of the leaf nodes. And then it's obvious that in case we have more leaf nodes, there are more suitable message blocks. And the effort which is connected with this task of finding this linking message is directly related with the size or the height of this diamond. Now I want to show you how we can construct the diamond itself. The construction starts with sampling the leaf nodes uniformly at random, and then we build the diamond level by level. So it's enough to consider how we can build one of the level because it works the same for the others. And the naive approach to do this would be to take all the leaf nodes and divide them in pairs, and then use the collision finding algorithm of Brassard et al. Therefore, we try a lot of message blocks for one node per pair, so that we have a lot of suitable message blocks how we can connect this first pair. This allows us to use Grover's algorithm in an efficient way to connect the first pair. And in this manner, we would process with each pair. But this approach has a big disadvantage because we need a lot of evaluation per pair. And this observation leads us directly to our enhanced approach, where we can reuse the pre-computed values across the connection steps. So as before, we're doing this pre-computation, we try a lot of message blocks, but this time we don't divide the leaf nodes in pairs, we divide them in the upper and the lower half, and the pre-computations, we spread them equally over the upper half. And after each application of Grover to find these pairs, we will pre-compute new values in order to have the same amount of suitable message blocks as before. So in this picture, the new pre-computed values are the one which are represented by the dashed arrows. And this strategy has a big advantage because it needs fewer evaluations on average for each pair. Because most of the pre-computations we can reuse and use to find more than one pair. And this table shows the time complexities of the algorithms A1, A2, and also the complete attack with the optimized diamond size. And this table shows it in the classical setting and the quantum setting as well. So the second and the third columns are the one in the quantum setting. And if we compare the first and the second column, we can see that our naive approach already achieves a significant improvement. If we look into the algorithm A1, and look into the factor before n, then it decreases from 1/2 to 1/3. And for A2, we can also observe something similar. The factor before n decreases from 1 to 1/2. And the main difference between the naive and the enhanced approach is when we look in the first line for A1, that the factor before the k decreases from 1 to 2/3, what gives us a significantly improvement of the complete attack. So the factor decreases from 4/n to 3/7. And what is also worth to note at this point is that we have done some Qiskit experiments, and we succeeded in showing this speed up between naive and enhanced approach. But now I want to show you why our enhanced attack is essentially optimal. And when I say optimal, what I mean with this is that there is no way to do the Nostradamus better if we want to use these diamond structures. And in case we want to get faster, we need other strategies. And to prove our lower bound, we need a result of Leo and Zandri. And please don't be afraid of this formula. We are only interested in the case where C equals 3, and then the exponent is just 3/7 times n. And the theorem says the following. In case we have given a random function f, there is a minimum number of evaluations which are needed to find a C collision. And a C collision is defined as a tuple which consists of C different elements, which all maps to the same value under the function f. And why this result is interesting? The reason is that we can use the Nostradamus attacker A1 and A2 to find a 3 collision. And to understand this proof, it is first important to note, when we go back to the time complexities, that it doesn't matter if we use A1 to construct a diamond structure of height k or k+1. So we can instruct A1 to construct the bigger diamond and A2 to find a collision with level k, so that we have found a 3 collision. And then Leo and Zandri tell us that this cannot be done faster than 2 to the 3n/7. So we cannot do our Nostradamus attacker faster than this bound. And this shows that our attack is optimal since it essentially achieved this bound. And in case we want to get faster and get beyond this bound, we need other strategies. We will leave it as an open question if these strategies exist or how they might look like. But what we can tell you is that there is a bound as well. In our paper, we show that any Nostradamus attacker, so possibly someone who is not using this diamond structure, needs at least 2 to the 3n/7 minus s evaluations of the compression function. And s is a maximal block length of the suffix s. And this is a very interesting result, since it means that we cannot get faster if our suffixes are short. And we need to look for longer suffixes instead of short ones. And this brings me to the end of my talk, where I want to sum up everything quickly. So we have seen the quantum Nostradamus attack, as well as its time complexity and its lower bounds in the case of using the diamond structure and also in the general case. Thank you for the attention.
Okay. Thank you for the good presentation. So, does anybody have a question? Okay, no, thanks again for the good presentation. And yeah, let's move on to the next talk. Yeah. Okay, the next speaker is Zhenyu Huang, who will give the presentation with title Synthesizing Quantum Circuits of AES with lower T-depth and less qubits. Okay.
Hello. Can you see my screen?
Yes.
Okay.
Okay.
Hello, everyone. I'm Zhenyu Huang. The title of this talk is Synthesizing Quantum Circuits of AES with lower T-depth and less qubits. This is a joint work with Su-Wei. This talk has 5 parts: the motivation, some new general structures, and the techniques for design compact quantum circuits and their applications in AES. First, let me introduce the motivation of our work. In quantum cryptanalysis of symmetric ciphers to apply quantum attack, the attacker needs to construct an attack circuit based on quantum gates. For example, if the attacker wants to apply a quantum key search attack by Grover's algorithm, the attacker needs to construct a Grover oracle. If the attacker wants to apply attacks based on Simon's algorithm or offline Simon's algorithm, a quantum encryption oracle is needed. The quantum circuit for the encryption process is a part of the Grover oracle or the quantum encryption oracle. Moreover, in its core 4 proposals of PQC, the complexity of quantum key search circuit for AES is used as a baseline to categorize the post-quantum public key schemes. For these reasons, accurately estimating the lowest cost of quantum circuits for the encryption process is important for both quantum attacker and post-quantum design. Hence, our work is focused on reducing the cost of these encryption circuits, especially the cost of AES circuit. To implement a classical function by a quantum circuit, one can follow the following 2 steps. First, convert a classical circuit that consists of XOR, NOT, and AND gates into a reversible circuit that consists of CNT gates, which are C0 gate, NOT gate, which is equivalent to poly-X gate, and TOP gate. Then decompose TOP gates into Clifford plus T gates, and finally obtain a Clifford plus T implementation. Then we are trying to optimize different metrics: the width, which is the number of qubits, the gate count, and the depth. Here, depth means the number of layers of circuit. When we assume gates acting on disjoint set of qubits can be applied in parallel. Moreover, in most fault-tolerant quantum computation, the cost of a T-gate is greatly higher than that of a Clifford gate, and the running time of a circuit is dominated by the T-depth. Now let me introduce our first contribution, which is a generic structure for constructing the encryption circuit of iterative primitives. First of all, let's review 2 structures used in previous works: the pipeline structure and the zigzag structure. These 2 structures both use out-of-place circuits of round transformations as sub-circuits. Here, out-of-place means the output of the round function, ORI, is stored in some different qubits than the input. Due to the use of these out-of-place circuits, the pipeline structure has redundant outputs after each round. In this figure, these redundant outputs are labeled by the red color. Then, the zigzag structure was proposed to reduce the number of qubits by cleaning some redundant outputs with the reverse circuits of some rounds. Here, R dagger is the reverse circuit. However, there are still some redundant outputs in the zigzag structure. Hence, the width of the circuit still increases as the number of rounds increases. Actually, for symmetric ciphers, each round is invertible. So theoretically, there is an in-place quantum circuit for each round. Here, in-place means the output of the round function stored in the qubits, which were used by the input. However, directly abandoning such in-place circuit is very hard. Here, we present a method to construct an in-place round circuit from two out-of-place subcircuits. This is our structure. In this figure, UR is a circuit for the round transformation R, which computes T x k. Then this is a swap gate. Here, UR inverse is a circuit for T prime, which is the inverse of T. It's obvious that by this structure, we can implement each round in place. Then we have the following structure for the whole encryption circuit. We call this structure the OP-based round in place structure. Here, OP-based is short for out-of-place based. It's easy to see that in this structure, the width of the circuit does not increase after each round. Here is a comparison of our new structure with other structures. We assume they use the same out-of-place round circuits as their main components. Then we can see that the width of our circuit is lowest. And for different oracles, the depth results are different. For encryption oracles, the depth of our structure is same as the pirate structure and is lower than that of the zigzag structure. And for the DW cost, which is the depth times width cost, our structure is lowest if the number of rounds is not very small. Okay, let's move to the next part. In this part, we will introduce some new generic techniques for implementing linear and nonlinear transformations. First, we consider the problem of implementing invertible linear transformations. An invertible linear transformation maps the computational basis x1 to xn into n linear expressions L1 to Ln. And it is well known that an invertible linear transformation with n variables can be implemented in place by a CNOT circuit with n qubits. Since a CNOT gate can be seen as a row addition elementary matrix, we can achieve such CNOT circuits by PLU decomposition. But by this way, the number of gates is large. We can use some heuristic algorithm to reduce the number of gates, but the result is still not optimal. In this paper, we propose a new set-based method for implementing linear transformation with the minimal number of CNOT gates. The idea of our method is encoding the problem of finding a circuit with k gates into a set problem, then solve it by a set solver. For example, the cryptonet set. Then if the problem for k-1 is unsatisfiable and the problem for k is satisfiable, we can know that using k gates is optimal. And then we can obtain an optimal circuit from the set result. So the key problem is how to encoding the circuit problem into a set problem. Here we sketch our way of encoding. We generate some variable sets B, C, F, and psi. Here B and C is used to describe the control wire and the target wire of each CNOT gate. And F is used to describe order of the outputs. And psi is used to describe the Boolean expression that is the normal form of each wires after each gate. Here is how these equations look like. And our experiments show that by our method, problems with size less than 9 bits can be solved in a reasonable time. Okay, that's all for the linear problem. Our next problem is implementing nonlinear transformations in place. First of all, we introduce some new terminologies. Given an out-of-place circuit of function f, we call it a C0 circuit if it works when the output wires are initialized to 0. While we call it a C star circuit if it works when the output wires are initialized to any value. It is easy to see that a C star circuit is always a C0 circuit, and building a C0 circuit is much easier than building a C star circuit since there are fewer constraints for the input and output. To save the cost of qubits, some circuits may use the output wires as temporary storage space, and in this case, these circuits are C0 circuits, but may not be C star circuits. For example, the ASS box circuit proposed in some previous works are all C0 circuits, but not C star circuits. Now we show how to construct in-place circuits for nonlinear transformations based on these two kinds of out-of-place circuits. First, we classify the nonlinear transformations into two kinds. The first one is the Vestal-like transformation, which frequently appears in Vestal ciphers and FSR-based designs and key schedule algorithm of block ciphers. It is easy to see that to implement the transformation T in place, we only need to design a C-star circuit of F. Second one is the substitution-like transformation. Similar as the round transformation discussed before, it can be implemented in place by the OP-based in-place structure we introduced before. And this is the structure. So to implement UT, apparently we need a C0 circuit of S. And to implement UT inverse, it seems that the output of the wires are initialized to non-zero. Here they are initialized to X. So maybe we should need a C-star circuit of S prime, but actually this is an overshoot. If we denote SXY by Z, then UT inverse maps ZY S prime to ZY0. And this is the reverse circuit of a C0 circuit for S prime. So we only need to design a C0 circuit of S prime, which costs less quantum resource. Then we can use its reverse circuit. Now we can focus on the problem of designing these out-of-place circuits. In this paper, we propose some criteria for efficiently designing C-star circuits. And under this criteria, a C-star circuit can be constructed from a special C0 circuit called the simplex C0 circuit. A simplex C0 circuit is sure a C0 circuit. And if the output wires is initialized to Y, then the output will be AY plus FX. Here, A is a linear function. So by adding a C0 circuit for A inverse at the beginning, we can construct a C-star circuit from a simplex C0 circuit as shown in this figure. And in most time, this C0 circuit uses no more than 8 qubits, hence can be optimized by our set-based algorithm introduced before. So by this method, we can construct a C-star circuit of AES box, which is used in the key schedule from the C0 circuit proposed in previous works, without increasing the number of qubits and Toffoli gates. This table shows the comparison of our C-star circuit with the one proposed in Asiacrypt 2020. We can see that our circuit has lower values for all metrics. Okay, let's go to the next part. Our next problem is constructing low depth circuits. Especially we want to reduce the T-depth of nonlinear components, since T-depth determines the running time. For our problem, T-gates only appear in the decomposition of Toffoli gates, quantum AND gates, and their adjoints. If quantum AND gates is proposed in Asiacrypt 2020, it is a C0 circuit of the AND operation. For all these gates, they have T-depth 1 implementations. Then we consider the following question. Given a classical circuit with n-depth k, a classical circuit is n-depth, or sometimes called its multiplicative depth, is the largest number of AND gates in all its parts. In this classical circuit, if we simply replace each AND gate with a Toffoli gate or a quantum AND gate, then we can always obtain a T-depth k quantum implementation. The answer is no. This figure shows a simple example from a n-depth 1 classical circuit. We may obtain a T-depth 2 quantum circuit. Another example is the AES box circuit proposed in Asiacrypt 2020. This quantum circuit is derived from a classical circuit with n-depth 4, but it has T-depth 6. This paper will prove the following result. Given a classical circuit with n-depth S, the T-depth of the quantum circuit implementing all the nodes of the classical circuit is not smaller than S. Moreover, with sufficiently many acidia, we can construct a quantum circuit implementing all the nodes of the classical circuit with T-depth S. And the constructive proof of this theorem gives us a way to achieve this lowest T-depth circuit. So by this way, based on Boya and Parata's classical circuit for ASS box, we achieve a T-depth 4 content circuit for ASS box. Furthermore, in this paper, we construct a new improved classical circuit for ASS box with n depth 3. And then we can ban a T-depth 3 content circuit. Note that the output of ASS box has algebraic degree 7. Hence, we need at least 3 multiplication layers to generate a polynomial with degree 7. This can be explained simply. Since the input has degree 1, then after 1 multiplication layer, we have polynomials with degree 2. Then after the second multiplication layer, we have polynomials with degree at most 4. Hence, we need at least 3 multiplication layers. This means T-depth 3 is optimal if we follow the way that design content circuits from classical circuits. In the last part, we show the applications of our techniques in AS. First, we show how to construct low-width circuits for AS. This is the circuit for the key schedule. Since it's a Festo-like transformation, it can be implemented by using a C-star circuit of sub-byte, which consists of 4 S-boxes. And this is the round circuit. Here we use OP-based in-place structure. If we want to implement a Grove oracle, round 0 and round 1 can be implemented together as shown in this figure. Then by changing the number of S-box applied in parallel, we can append different AS circuits. Here we compare some of them with the one proposed in Asiacrypt 2020. We can see that for all metrics, our circuits has lower values. Our second application is constructing low-depth circuits for AS. For this problem, we can apply our T-depth 4 and T-depth 3 S-box circuits in the pipeline structure. This figure shows the circuit for each round. We can see that comparing to the circuit proposed in Asiacrypt 2020, our circuits has lower T-depth and lower full depth. And note that these values are for implementing AES and AES dagger. If we only implement the forward circuit for AES, that is the circuit which computes the ciphertext without cloning the redundant outputs, these T-depths will be 60, 14, and 30 respectively. Since T-depth 3 is a minimal value for a S-box, hence we conjecture that T-depth 30 is a minimal value for 10 rounds of AES. If we don't across the hierarchical boundaries formed by the round function. At last, by combining different S-box circuits with different generic structures, we have 6 design strategies. Then, by changing the number of S-boxes applied in parallel, we can obtain some T-depth and with trade-off curves, as shown in this figure. And these colored points are the results in previous works. Okay, that's all for my talk. Thank you for your attention.
Okay. Any questions from the audience? Okay. Yeah. Thank you for the good presentation. Yeah. So our last presentation is exploring SAT for cryptanalysis, quantum collision attacks against 6 rounds SHA-3. The speaker is Gojen Liu.
Thanks for the introduction. It is a great honor to share our work on the collision attacks of SHA-3 with you. So I'll first review the previous collision attacks and then present our contribution. Sorry, there is a missing figure. Let's have a look at the SHA-3 hash family. There are 6 instances. Each is based on the sponge construction. And the underlying permutation is K-check-F. The K-check-F is famous for its huge state size. And the round functions are 4 linear operations and 1 nonlinear operations. So in all those years, the collision attacks cover at most 5 rounds. And it's the first time that 6 round collisions are presented. The collision attacks take a 3-step framework. We first generate the truncated differential trails with the d-beta digest collision. And we call such trails the colliding trail. And based on which we can construct the connectors that link the sponge construction and the colliding trail. We call trails in the connector as connecting trails. And the last step is exhaustive search to search for colliding message pairs. And one may ask, is it possible to extend the 5-round attacks to more rounds, or at least by 1 round? So we can answer this question from 2 aspects. In the colliding trail search, the strategy is direct. It's a naive exhaustive search method. With the truncated differential trails at hand, they simply extend the trails backward and forward by 1 round to search for the possible digest collision and the better connector difference. So there are 2 problems in this strategy. One is that we do not have that much computing resources to do the exhaustive search. And the other is that it highly dependent on the general truncated differential trail search, which is a difficult problem itself. So with this strategy, it's difficult to search colliding trails with better probability of covering more round. And in the connector construction phase, one problem is that with the target difference algorithm, it's difficult to generate connecting trails that cover more round because the degree of freedom of the difference decreases significantly. And with the same reason, even we generate the connecting trail, it's difficult to construct the connector successfully because the degree of freedom of values also decrease significantly. So the main obstacle lies in the fact that we do not have efficient trail search strategy. So in this work, we propose a set-based trail search strategy that will overcome the limitations we have discussed. And with the automatic trail search toolkit, we can generate a better colliding trail and the connecting trail, and based on which we can extend the 5-round collision attack to 6 rounds. The set implementation is similar to other tool-based automatic trail search method like MILP. We first need to model the trail search problem to the mathematical problem, and then we translate the mathematical problem to the languages that the solver can understand, and the solver will do all the work for us and give us the solutions we expect. So the set solver can understand the CNFs, and we generally try several solvers to select one with the best search efficiency. In this set implementation, we choose a crypto mini set as the underlying solver. it's not only efficient, but also accept the XOR clauses, and that allow us to concentrate on the collision attack. So the set implementation include describing the propagation of the differential trail to and the objective function to the CNFs, and then add to the solver. So this is a difference propagation model of one round. The input difference alpha r is propagated to beta r and alpha r plus 1 through the round function. And the difference bit is represented with variables. So the linear operations are simply described with adding the XOR clauses to the solver. And for the nonlinear kind, we use a logic Friday to translate the DDT of each box to CNFs, and then we add those CNFs to the solver. For the objective function, we use the sequential encoding method to translate the cardinality constraint with CNFs. This will introduce auxiliary variables and also add the big O number of clauses. So the objective function of the set implementation could be either the constraint on the number of active S-box or the constraint on the propagation weight of the differential trail. For either objective function, before we add the CNFs of the cardinality constraint to the server, we should also describe the relation between the difference and the variables that stand for the constraint. And here we use a 4-round differential trail to demonstrate the set implementation of the truncated differential trail search. So we use the trail call to represent the 4-round trail. And the set implementation includes first, we add the description of the differential trail to the solver, and then we add the description of the constraint on propagation weight to the solver. And the search efficiency of truncated differential trail is quite satisfying considering the huge state size. We have consistent 3-round trail search result with a dedicated algorithm. And we also get 2 4-round truncated trail with the best propagation weight. Sorry. The set implementation of the gliding trail search is similar, only that before we adding the description of the gliding trail and the constraint on propagation weight, we should also add the constraint on the digest collision. We use the same logical Friday to translate those conditions with CNFs and add to the solver. So this table shows the comparison of the efficiency. And we can see there is great improvement. So the first round of the 4-round gliding trail is not determined yet, and we fix it in the connecting trail search. To generate the beta 1 and the beta 2 trail, we simply add the description of the trail and the description of the constraint to the solver. And to determine beta 0, except for the description of the propagation and the constraint, we will also need to introduce more variables and clauses to make sure that beta 0 is a valid connector. And that's how we implement the set-based trail search toolkit. So with this set toolkit, we can generate a 4-round gliding trail with the propagation weight equal or greater than 141. And we can also generate the connecting trails that provide significant gain on the degree of freedom, and that will allow us to construct better connectors. Sorry. So in the connector construction phase, we need to construct either 2 or 3 round connectors. To construct a connector means to describe the propagation of messages through those connecting trails, meaning that we should list linear equations on the messages. Let's take the 2 round connector as an example to explain the idea. So for this 2 round connector, in the first round, we should list the equations on the condition on capacity and padding, and also on the chi-0 propagation. And we get a system of linear equations on y0, and that is ay0. And to bypass the first round and link to the second round, we need to fully linearize chi0 and then transfer ey0 to ey1. And for the second round, chi1, we do not have that much degree of freedom, so we use a gradient algorithm to choose part of the chi1 condition and add the equations to ey1. And in that case, we have a great ey1 that can describe the propagation of the first round and the partial propagation of the second round. So that is how we construct the 2 round connector. The solution space of ey1 then will let us get message pairs that will follow the first round propagation and part of the second round propagation. So the techniques used to linearize, fully linearize chi or partial linearize chi are directly taken from previous works. So this is a concrete 6-round collision attack on shake 1 to 8. So the first round of the 4-round colliding trail is transferred to the connecting trail. So we have a 3-round connector. To construct the 3-round connector, we first list the equations for the first round. That is similar to the 2-round connector. We need the equations of the capacity and the padding and the chi-0 propagation, and to transfer ey0 to ey1. We fully linearize chi-0. And for the second round chi1, we add those equations to ey1. And for the third round chi2, we do not have that much degree of freedom, so we also partially choose 32 conditions out of the 116 conditions, and add those equations to ey2. And then we partially linearize chi1 according to the chi2 condition selected. And then we transfer ey2 to ey1. So now we have a great ey1 system. And this is how we construct the 3-round connector. So the solution space of the 3-round connector is of the size 2 to 27. And the message pairs generated from the solution space will fully follow the first 2 rounds and partially follow the 3rd round. So we have seen that the 3rd round of the connector, there are still 80 conditions that are not treated, and we move this condition with the colliding trail and treat them with the exhaustive search. So theoretically, the time complexity of the exhaustive search should be 2 to 132, and that is bigger than the birthday bound. So we need to use the early about technique and reduce the practical time complexity to 2 to 123.2. as for the complexity of the connector construction phase, we should construct 2 to 105 connectors. And we use this equivalent conversion method to represent the complexity of the connector construction with the complexity of the shake computation. And we get 2 to 121.2 time complexity for the connector construction. So in total, for the 6-round collision attack on shake 128, we have a time complexity of 2 to 123.5. That is only slightly smaller than the birthday bomb. But anyway, it's a valid collision attack. So for the quantum collision attack, we consider it with the time-space trade-off margin. That means any quantum collision attack with time complexity smaller than the margin would be considered a valid quantum attack. In this work, we assume that all the related quantum circuits exist already, so we can concentrate on the time complexity evaluation. Therefore, the quantum implementation is quite easy. We first prepare message pairs with the connector circuit, and for each message pair, we will check whether their digests are equal with the SHA-3 circuit, and then we repeat those process until a collision is found. The data complexity in the brute force phase is 2 to 206, 6-round SHA-3 computation, and we need to construct 201 connectors. So we use this formula to evaluate the complexity of the quantum collision attack. Their TA and the SA denote the depth and the width of the overall quantum circuit. And we define the depth and width of the SHA-3 circuit as the identity depth and the identity width, meaning that TS and the SS are 1. So the overall depth TA equals to the depth of the SHA-3 circuit, because comparing to the SHA-3 circuit, the connector circuit only consists of linear operations. So its depth can be is negligible. And the overall width of the quantum circuit is 742, and we use this method to represent the width of connector circuit with the SHA-3 circuit, and then we get the total time complexity of the quantum collision attack with this value, and it is smaller than the time-space trade-off margin we have mentioned. So it's a valid quantum collision attack on SHA-3 255. And the collision attacks on SHA-3 224 is similar, with only slight difference on the connecting trail. And its time complexity is this value. So in conclusion, we propose a set-based automatic trail search toolkit and generate better colliding and connecting trails. And then we can improve the previous works by 1 round and present the first 6-round collision attacks in both classical and quantum settings. Thank you.
For this talk?
So I have one question for the time complexity for the 6-round clean attack on shake
Okay.
Yeah, not this one, classical. Yeah, so here you compared it in terms of bit operations, and you calculate the, so you say for 6-round shake, you need so many bit operations, but indeed, it can be implemented in a much efficient way. So do you think it's fair? Because we do not need to do bit by bit when doing the shake comparison. But for this attack, you need to use algebraic technique. So we need to do it bit by bit. So do you think it's fair, or should you compare it with the unit time to perform the Kerchak 6-round Kerchak permutation, the real time, and then compared with the real time for solving the equation system?
So in our understanding, we think the implementation differs. It depends on who implements the algorithm. So it's possible that in one environment, the implementation is better, and in other environment, the implementation is worse. So we do not compare them with exact implementation.
But so I still think it's not a fair comparison, because we did not need to perform the run function bit by bit. So because we can do, maybe it is a 64 bit, so we can in parallel way, we have such a command, maybe, yeah.
Yeah, I get your point.
So I think, yeah, so maybe you should refine something like that. And I have one more question. For the, maybe for the, in the quantum setting, maybe do you, so according to my understanding, you will also involve the phase to build the connector in, maybe you will also use a quantum circuit to build the connector, right?
Yes.
So do you think, and then you also, do you think it is easy to do this?
Yeah, as I have stated in the presentation, we did not consider the quantum implementation, the quantum circuit of the connector of the SHA-3 computation. We just assume we have those circuit, and we concentrate on the time complexity.
Okay, thank you.
Thank you.
Any other questions? Okay, thank you again for the good presentation. Yeah. And this is the end of this section. And so thank you all of your attentions. And so please enjoy your rest of the days. And thank you.